Hello, everybody. Okay. Welcome to our large scale holistic video understanding tutorial. So in this tutorial, we have a great lineup of speakers. I'm gonna share with you just a moment. Okay, checking out. Yeah, sharing the screen. So, holistic video understanding. What do we mean by holistic? By holistic, we mean bringing all the knowledge extraction pipeline under single umbrella. So we want to focus just not only on action recognition in videos, we want to go beyond the action recognition. So having more information, more knowledge for each videos. And in video understanding tasks, we want to not only focus on just single task, we want to go for multitask, multi-label, and multimodal long-range understanding. Therefore, today we have a great lineup of speakers. So each speaker is going to talk about their recent state-of-the-art works regarding the video understandings, various methods they're using, different types of ideas for action recognition, action segmentation, and also holistic video understanding. So the first speaker is Urtasun. I think, yeah, he's already on Zoom. I'm going to, yeah, make him co-host. And yeah, Chen, you can start your talk now. I'm going to stop sharing here and you can go for sharing.
Okay. Hello, everyone. So I'm new to Zoom. So if my voice is broken or video is broken, just shout out to me and I will try to fix it. Can you see my screen?
Yeah, we can see it.
Okay, so let's get started. My name is Chen, so I'm a research scientist at Google. Today, I'm going to talk about action recognition in videos and action forecasting. Most of this work is in collaboration with Cordelia, who is unfortunately cannot make it to the talk today. So we have witnessed a tremendous progress in video understanding thanks to the availability of deep models and big data. So the performance of video level understanding, such as the example shown on the left, or maybe spatial temporal action detection, as the example shown on the right, have progressed significantly over the past few years. And if you go over the vocabulary of those action detectors, most of them are the so-called atomic visual concepts or atomic visual actions. So what do I mean by atomic? They have very clear definitions. Those definitions typically do not rely on long-term temporal context. And some of the data sets, such as maybe atomic visual action dataset, AVA, does not even include any objects in the vocabulary and focus on only the actions. So the benefit of having such a clear definitions is that it is easy to collect huge amount of labeled data, which can be then used to train powerful deep learning networks. And the question now becomes, given those atomic visual actions or atomic visual concepts, which are relatively reliable right now, what are the things we can build on top? Can we offer a deeper and more structured understanding of those videos? And that will be the focus of the talk. So one such example is the human-object interaction, where the goal is try to ground the detected actions with interacting objects. In this example, it will be like the plates on the table for eating and the listener for listening. And we might not only want to recognize what is happening right now, but also using the visual cues or other cues to predict what might happen in the near future, like a few seconds ahead. And we can do it for natural videos like the videos in Ava, but there are also other interesting scenarios, if I may, maybe more interesting scenarios, such as maybe sports games or video games, as I show on the left, or even for self-driving cars, as I show on the right. And compared to human-object interaction, as I mentioned earlier, so one distinct feature of these problems is that to understand those problems and to model the behaviors, we need to explicitly model the interactions of those different agents. For example, for soccer game, it might be up to 22 players. And finally, we're not only interested in understanding short videos, but also understanding long videos. So what is interesting about those long videos? Here is my favorite illustration from the book by Barker and Wright. I think it's in 1954. It shows the spectrum of human activities as a function of time. So we can see that although the action sequence the human performs is exactly the same. And we can see that simply by varying the temporal scale from A to B all the way to A to G. So the interpretations can change significantly from the very atomic ones, such as stepping down, to the very composite and abstract ones, such as getting an education. So of course, our videos, like on the internet, they are not covering the whole life of a single person, but there are videos such as maybe movies and TV shows that if we want to really understand what's going on, we need to have the capacity to understand those, model the long-term relations. So in summary, I feel there are three future directions, given that we have reasonable performance on recognizing atomic actions. The first one is that we want to have our recognition system to be open vocabulary. It can model arbitrary actions, objects, or maybe object states, and their novel combinations, even though we may not see them in the training data set. And the second one is that it should be contextualized. As I shown in the previous slide, the description can depend on maybe the spatial or very long-term temporal context. And we want to take those information into account. And finally, we want the model to be predictive. It can anticipate the possible events in the near future. And ideally, we want to also enumerate all the diverse possible events that could happen in the near future. And one common limitation or one common challenge for those three items is that all three items is really hard to collect manual annotations. And the challenge now becomes like, how can we learn without manual annotations? I think it's a common challenge and common interest of many computer vision researchers right now. And as you can see from many of the awesome papers in this CVPR. So our motivation for the first part of the work is that many people, they upload instruction videos to the internet. They use cameras to capture what they are doing and pair with useful narrations that are closely related to the visual contents. So the question now becomes, how can we distill this useful information from these unlabeled videos? Let's first take a look at what we have from those videos. So we have the frames and audio signals. They are temporally aligned. We can also apply some off-the-shelf automatic speech recognition algorithms to convert the audio into text so we can directly understand what's going on in the text space. And we then want to establish the cross-modal dependencies between the visual and language inputs. And in this particular example, it will be between the middle video clip and the description moving around your cakeboard. We are also interested in modeling the temporal dependencies on how human activities they unfold over time. For example, given the first video clip, what might happen in the next video clip and the clip that goes after that. So our inspiration is from the NLP community on how they model the sequence dependencies. So one simple yet very powerful training objective, as popularized by the Bird paper in 2019, is to predict the missing words that are randomly masked out in the text sequence. And in this particular example, in order to predict the word cute, we humans need to look at relevant words such as maybe dog and likes and play. So we can see that by simply predicting the missing words in a long sequence, the model automatically needs to capture the long-term temporal dependencies. Those sequence dependencies were implemented as self-attention layers. And basically for videos, we hope to do something very similar. And here I'm showing the 6 video clips in a cooking video that are ordered in time. So for example, we randomly mask out the third clip, and we want to also learn the dependencies by predicting what's missing in the mask out frames. But compared with the language case, the main challenge here is that it's unclear how we define the loss function for video pixels. So our first option is to apply a perceptual loss, where maybe people can use a generative model, such as again, to directly predict the pixels. And we can then try to compare the pixel-wise perceptual loss with the ground truth video sequences. But we all know that generating pixels, especially for those unconstrained videos in the world, is pretty challenging. And also, for the purpose of learning, like what we want to learn are the cross-modal dependencies and the temporal dependencies. So many of the low-level details, such as maybe the layout of the kitchen or maybe the color of the shirt, is not important at all. So for this particular example, all we care about is the action heating chocolate. And these 3 video clips, although their visual appearances are quite different, should be considered as equally good. So we can see that it's not only difficult, but also unnecessary to reconstruct those subtle details. So instead, we define a loss function based on the high-level semantic information. For each video clip, we apply a pre-trained deep convolutional neural network to extract the visual features. And we can then try to use a hierarchical k-means algorithm to group different videos into clusters. And our hope is that the semantically close videos or video clips, such as heating chocolate, are grouped into the same clusters. And we call this clustering step as a tokenization. So here are some of the visualizations of the tokenization outputs, each row corresponding to a video. And on the left, I show the keyframes of the original videos. One is decorating a cake, and the other is spreading butter on some toast. And on the right, I'm showing the reconstructed image centroids that are closest to the cluster's feature centroids. So we can see that although they come from different videos in the training data set, and the subtle details, such as maybe the color of the shirt or color of the outfits, are different, but the high-level semantics, such as the toast, the cake board, and also the action rotating the cake board, are preserved. And this is exactly what we want. So here is an overview of our proposed framework. The inputs are tokenized video clips and the outputs of the ASR system, and they are temporally aligned. And then we randomly mask out some of the elements in that sequence. We pass it to the video BERT model to predict the missing tokens, which could be either text, individual words, or maybe some video clips. And here is a more detailed view on the inputs and the target outputs of video BERT. So given some input corpus, we have the ASR on the top and the video clips on the bottom. We can either try to keep the video intact and mask out the words, which we can see is a way to learn object classifiers, because in order to learn those mask out, for example, objects or verbs or their attributes, we need to understand what's going on from the video clips. Or we can mask out the video clips and the conditions on the text information. And finally, there are videos that they don't have the corresponding speech information available, maybe due to it's in a different language, or maybe it's just that we don't have a robust enough ASR system to decode the video audio track. But those videos are still helpful in the sense that they are helpful for us to predict the temporal dynamics by masking out some of the future frames and condition on the past frames to predict what might happen in the future. And this is our experimental setup. So for training, we use 300,000 cooking videos available on YouTube. So we mine those videos using the keywords such as maybe recipe or like cooking show. And then this is a noisy collection of YouTube videos related to cooking. And then we apply the off-the-shelf ASR system to obtain their like transcripts of the human speech. Again, this process could be noisy, but given the large scale of the data we have, maybe the noise. Our hope is that the noise can be surprised by using huge amount of training data. And in this process, no manual annotations was used because all the process were automatic. And for evaluation purpose, we choose several standard academic benchmarks. They are human annotated with clean labels. And we need those clean labels because we need to have a standard proper evaluation. And we also know that for evaluation purpose, only the video frames are used. And we do not require the videos to have corresponding audio tracks, because our hope here is that by doing the pre-training on paired ASR and video sequences, the ASR information is already encoded into our overall model. Even though we don't provide them in the test time, those implicit representations are still helpful. So once the model is trained, we first conduct some qualitative analysis. Here, we ask the model to perform the task of recipe illustration, and each row corresponding to 4 steps of some written recipe. We ask our model to condition on the input text and predict one missing video token at a time. And we then visualize the video token using the images that are closest to the feature clustering centroids. We can see that the resulting video predictions are pretty high quality, that they are quite semantically related to what's going on, what's described in those text recipes. And again, because of the k-means clustering step, the recipe illustration images could come from different videos in the training data. And the natural future work could be like try to train a video generator that aims at generating consistent appearance conditioned on maybe some input observed video sequences, and also on those predicted latent video features. Another qualitative experiment we can do is that whether we can generate realistic futures. So here we conditioned, provide the condition input. The first one is a bowl of cocoa powder. The second one is a bowl of egg and flour mix. And we can see that our model is able to generate realistic predictions at different time scales. For example, for the cocoa powder example, it predicts first it will be put into an oven, and then it might be turned into either a brownie or a cupcake. And similarly for the second example. And finally, we conduct some quantitative analysis. We took a video, cooking video data set. Here we used the ucook2 data set from Michigan and performed the so-called zero-shot classification task. So zero-shot here means that we do not have to know the categories beforehand and directly use our video BERT model to predict the missing objects and actions conditioned on the video inputs in our open vocabulary. And on the right, we show the zero-shot classification accuracy as a function of the pre-training data set size. And we can see that more data, the more data we use, the higher the performance. And once we have enough training data, it even achieves on par or outperforms the fully supervised performance, which is quite promising. Okay, so far we talk about cross-model learning framework, and that has been demonstrated on cooking videos or instruction videos. And the natural question to us is that, can we do cross-model learning beyond cooking videos? Because the benefit and also the limitation of such instruction videos is that their speech information are meant to be illustrative, and they're talking about what they are doing. But that may not happen in the real world, more diverse video cases. And we take a case study for movies that are available in some database. And it turns out that there are indeed examples where human speech are highly correlated with the actions performed in those movies. And here I'm showing 6 examples where people talk about sitting down. And here are another 6 good examples where people talk about taking a photo. But unfortunately, we found that those good examples are rare cases in the overall corpus of movies. And more often, the speech could be completely unrelated to the visual content. So there are several failure modes. First, maybe the actors talk about the events happen in the past or the events happen in the future. So they are not aligned with the visual content. And often people can talk about some stories that occurred off screen. So there's no chance, even by looking ahead or in the past, that we can reestablish the correspondence. And another failure mode is that, as is naturally understandable, many of those atomic actions, like maybe sitting or standing, they occur too frequently and they're too boring to be spoken by those actors. Otherwise, maybe we wouldn't buy those tickets to watch those movies. And this motivates us to build a model which learns when the speech is indicative of an action and which action that speech that is likely to be associated with the speech. And we note that the movie screenplays, which some of them are available online in the database, describe the actions as well as contain the speech of the characters, and hence can be used to learn the correlation with no additional human supervision. And here I'm showing some of the movie screenplays, and we can see that the actions are described in the scene directions. They are marked in red, and also the human speech that are closest to the actions are marked in blue. And this process, by doing this process, we basically have a big noisy paired data of mapping from the human speech to those actions performed by those actors. And this process is a little bit like machine translation. And suppose in a totally made up case that we do not have paired training data between maybe Chinese and German languages, but we can still build a link between the two by first translating Chinese to English, and then from English to German, which we may have the training data. It's a similar case here that we do not have a direct mapping from maybe movie visual information to those high-level actions, but we can first go to the speech information, and from speech go to the actions. And to train this text-only speech classifier, you can pick whatever speech classifier you like to use. And here we train a BERT classifier for its superior performance. And the data set we use is this so-called Internet Movie Script database. It's available online, and it contains a huge amount of sentences. And here we show the visualization of the top speech segments retrieved by the text-only visual classifier. We then show the video clips that are corresponding to those retrieved speech. We can see that although our method operates purely in text, it is able to spot when human speech is likely to describe ongoing actions. And this gives us free annotations for the video clips. Basically, the input to the model are only the text speech information, such as don't move or might run. And then we only use the corresponding video segments for the visualization purpose. But then once we have this correspondence, we can use these video signals to train a classifier for the action run. And here is another example for making a phone call. One benefit of doing this speech to action classifier is that we are not limited to this the training speech to action classifier training data, which in our case is 1,000 movies. We can actually apply this to all the videos or movies that we have available, and we want to apply the classifier onto, as long as they have the English speech information correspond to those. And the benefit of running a diverse set of videos is that we get the diverse, visually diverse actions. And here I'm showing the 4 examples of making a phone call. And you can see that different types of phones show up in those 4 different examples. This is very different than existing data sets, such as maybe AVA, because the videos in AVA were collected maybe from the older movies, and you cannot discover a cell phone in those movies. And one particular evaluation, quantitative evaluation, is that we want to show the benefit of having this automatically retrieved action training data to boost the performance on existing action video data sets, such as AVA. And in the AVA data set, one unique or maybe one most challenging aspect is that the long tail distribution of the actions. And here on the left, I'm showing the distribution of the number of training examples per class on the log scale. You can see that it's quite a long tail. And by doing this automatically mining process, we are able to augment the AVA training data set by 2 orders of magnitude more training examples. Of course, these training examples will be noisy, as our training process is completely like without manual correction in the process, but we'll show soon that this process is actually beneficial. So here are the quantitative analysis on action recognition on AVA dataset. Basically, the take-home message is that when training purely on the automatically mined training examples, where we have abundant noisy label data, for 8 out of the 14 classes that are the tail classes in the AVA dataset, the noisy movie classifier is able to outperform the fully supervised baseline without using a single AVA training example. And you can imagine that we can combine the 2 by doing maybe some transfer learning, first pre-train on the noisy movie examples, and then fine-tune on the clean but few AVA examples. And we can see that by doing this process, our approach exceeds the supervised performance for all of the 14 classes. And there are indeed some of the failure cases, such as maybe hug is often confused with kiss, because naturally they're very confused when we only look at the speech information alone. Okay, so far we talk about learning action classifiers from unlabeled videos, where either they could be cooking videos or maybe they could be movies. But there still could be actions or events that which do not appear in those training data sets, although they can be abundant. And what will happen, how to deal with those cases where there are unseen actions. And for these actions or events, we computer vision people typically use the transfer learning approach, where we pre-train our visual representations on the huge training data set, and then fine-tune our visual representations to a small subset of label examples to target a task. And so this highlights the importance of learning like robust visual representations. And our goal here is that we want to reuse the video BERT model, as I just described earlier, that in an end-to-end fashion, so that we can use it to learn not only the temporal representations or the BERT encoders, but also the visual representations. But first, we need to fix a problem here. That is, the vanilla K-means algorithm is not differentiable, so that we cannot backpropagate the errors to the visual encoders. So we basically propose a very simple fix for this issue, that we can ignore the K-means step and just ask the network to put the representations of semantically similar clips to be as close as possible, and the irrelevant clips as far away as possible. By using this like contrastive learning objective, we can easily backpropagate the errors to the earlier layers of the visual encoders. And you can imagine that we do not have the ground truth of the semantically close or semantically far away examples. So basically, what is the standard approach in all those contrastive learning, self-supervised learning approaches is that they view a different data augmentation of the original video clip or image example as the semantically close example. And they randomly sample the negative frames or negative video clips from a huge database with the hope that on expectation, the chances of retrieving the semantically close negative examples is very small. And let's revisit the Widowbird model a little bit. It basically provides a recipe for self-supervised learning. The training objective is to predict the missing video content from its context. And here we can encode the video inputs using deep neural networks, and then use the Widowbird model to predict the features for maybe the mask clip. Here is E2. And then we can compare the predictive feature with the ground truth features using contrastive laws. And finally, we can update the weights of the widget encoder accordingly. And here I'm evaluating on the action forecasting benchmark, where the goal is to predict what's the future actions based on the previous video observations. And here on the x-axis, I'm showing the observed time, and the y-axis, I'm showing the prediction accuracy. We compare maybe two baseline of temporal modeling. One is simple average pooling, and the other is a long-term LSTM approach. And finally, we show the results of our proposed model. We can see that by our approach is best at utilizing long-term temporal context, especially when it's over maybe 45 seconds long. We also benchmark the visual representations and compare with all the previous methods. And here we are transfer only the visual representations encoded by the convolutional neural networks and transfer it to two video classification datasets, which are UCF11 and HMDB51. And we can see that our method achieved state of art by the time it was uploaded, of course, performance on those two benchmarks. And if we take a step back and revisit our training objective of either like cross-model learning or maybe predicting video-to-video frames, we can see that this can be an abstract view of this training process is that it's contrastive learning across different views of the same data. And the different views of the same data could be maybe video frames and the speech of a multimodal video clip. Or for video-only information, it could be frame at t, and the future frames at maybe t+2 or t+3. And actually, this multi-view perspective is not limited to videos. It has been widely explored in the self-supervised image representation or text representation learning approaches. One such example is colorization, where we can split the image into luminance and chrominance channels. And another example is context prediction, where you can take different crops from the same image or from the same objects. Here I'm showing a cat face. And basically, we want to establish, using the contrastive learning objective, to establish their connection of the same, different views of the same data, and want to make them closer than all those randomly sampled negative pairs. So are there any underlying principles on how to choose those views when we're doing like representation learning? So in our recent work, we conjecture that mutual information shared by the two views should be minimized except for those related to the downstream tasks, such as maybe object detection or maybe image classification. Here, I'm showing an intuitive illustration where the x-axis corresponding to the amount of mutual information shared by two views, V1 and V2. And here, x is the original input before the view splitting. And y is the label, which is task specific, such as maybe the object labels or action labels. And we make a simplification by assuming that there exists a path in the mutual information minimization curve where we can, when we minimize the mutual information between V1 and V2, we go past the sweet spot where the shared information between the two views are exactly the task related information. And this, I'm saying this is the sweet spot because it captures exactly what we need in order to solve the downstream tasks, such as maybe image classification or video classification. And we can see that if we vary the mutual information shared between V1 and V2 around this sweet spot, if we decrease the mutual information, there are missing information needed in order to recover the important task-specific information, Y. And if we increase the amount of mutual information, we get too much noise shared between the two views. And if our model learns to capture those noisy subtlety in their representations, they may solve the task using the so-called shortcuts. And our conjecture is basically we want to minimize the mutual information shared by wheels, except for those that are task related. And we verify this conjecture in 2 steps. For the figure on the left, we explore common image data augmentation techniques as a way to minimize the mutual information shared between 2 different augments of the same image. And on the y-axis, we report the self-supervised classification accuracy on ImageNet, where we fix the weights of the deep neural network and only train a linear classifier on top. And we can see that as the mutual information lower bound increases, the ImageNet accuracy decreases, which supports our conjecture that the more mutual information hurts the performance. And on the right, we basically show learned wheel generator based on only the information minimization process. And we can see that as shown in our previous intuitive example, there exists a sweet spot in the curve, which is around the mutual information 5.5 that leads to the best transfer learning performance. And increasing or decreasing the mutual information shared between the 2 wheels leads to worse performance. And it is worth noting that the learned wheel representations, as I just showed, were basically purely based on mutual information lower bound. And there's no guarantee that the mutual information remaining are related to the tasks. That is, maybe in this case, will be the STL10 classification labels. And if we provide a semi-supervised approach by providing the object labels in this along with the information minimization process, we can see that we are able to recover the optimal wheel split for all the different random runs we have run on this STL10 dataset. Okay, so the takeaway message so far, we want to go from atomic visual concepts to composite events, and for that we propose to use cross-modal learning as a way to harvest free supervision from the speech information. And we show that on not only the instruction videos, but also on more general movies or more general videos. We also show that it's possible to learn powerful visual representations from those unlabeled videos. And we can either capture the appearance information in convolutional neural networks or the temporal representations in the transformer encoders. And as we mentioned earlier, another goal we want to solve is that can we try to predict the actions will happen next in the future? And we have done some previous work in this domain, as so many colleagues have also explored. But our previous focus mainly was on natural videos, such as from the AVA dataset. But in those processes, we found a limitation of working with those natural videos is that their action space are discrete and very sparse, so their temporal dynamics is not super interesting. And another limitation is that the number of agents here, I'm showing there are 2 people inside, they're typically small, and there are not many of the interesting multi-agent interactions involved in those processes. So instead, we look for maybe slightly disjoint or unfamiliar task domain, that is the self-driving car domain, but it's actually quite related to video understanding because all those self-driving car scenarios, they are encoded as videos, but we can also have a structured representation of the maybe vehicle trajectories or the HD maps. And here we focus on a particular task of the so-called behavior prediction for those vehicles, where the inputs are the machine-generated vehicle trajectories, which can be viewed as one layer of abstraction from on top of the pixels. And we also have the scene context information, such as where are the lines, where are the traffic lights. And our desired outputs are the possible vehicle trajectories for the next t seconds. And you can see that compared with the AVA example, the beauty of this task is that there exists a more complex dynamics and state space of the vehicle trajectories. And to solve those tasks, we need to solve a multi-agent, we need to model the multi-agent interactions. So I'm talking about the scene context here. And in the self-driving literature, people have been using the so-called high detailed maps as a way to capture those semantic information or the road information. And HD map here consists of millions of different entities. I'm talking about the whole HD map covering a single region. And they generally model the real physical entities, such as maybe the lane boundaries, traffic lights, or crosswalks. And it is worth noting that there are inherently attributes associated with those entities on an HD map, such as, of course, they're like physical locations in XYZ coordinates, and also sometimes the states of the entities, such as maybe the color of the traffic lights. And how do people working on like behavior prediction use those HD maps right now? So they take a very computer vision approach. First, they rasterize those very structured information into images. Here, I'm showing an example where the image, the HD map is rendered into a top-down view, and the different entities are color-coded. And they then encode this image of HD map rendering using convolutional neural networks. And we can all see that there are several limitations with this approach. First, the convolutional neural networks are not designed to capture the long-range structures, which could be important for behavior prediction if we want to plan for like 3 seconds ahead or maybe even 5 seconds ahead. And second, it is often unnatural to map those structures, already very structured metadata, into images. Maybe we do not know how to render some of the states or the entities leading to missing information or some ambiguity. And finally, if we talk about practical applications, those rendering and encoding with convolutional neural networks could be quite computationally expensive. Okay, so is there an alternative to those rendering and convolutional neural network alternative? To answer this question, let's first take a look at what's inside in a high detailed map. Basically, we have a highly structured representation consisting of points, polygons, and curves. And the points corresponding to maybe traffic signs, such as maybe stop signs or maybe even traffic lights. And the polygons corresponding to maybe entities such as crosswalks. And there are also curves, such as maybe lane boundaries, or maybe if we consider also vehicle trajectories as part of the map, there are also vehicle trajectories or history trajectories. And all those points, polygons, and curves, they can be approximated, represented as the so-called polylines. And polylines basically is a set of ordered points or ordered vectors that if it's a point, there's only a dot, which is A1. And if it's a polygon, it would be a sequence of vectors from A1 to A2, and then to A3, A4, and A5. And of course, for a curve, there we can do the similar approximation. And now the problem becomes, is there any efficient structure to encode those something that is discrete and structured? And there were previous work in the like 3D scene understanding domain, such as maybe PointNet and many of the follow-up works, and they provide inspiration for us. So our motivation is based on encoding those structured representation of scene and vehicle dynamics. And our particular implementation is so-called VectorNet. So the input to VectorNet is a discrete polylines, as I mentioned just earlier. And then we use a hierarchical graph neural network to encode first the local information within each polyline. And then we want to propagate those local information into a global interaction graph with the goal to model the high-level interactions, such as maybe when and how to follow the lanes, and also when and how to yield to other vehicles. So here are some of the details of the polyline subgraph. So we basically group, remember that each polyline consists of a different set, a subset of vectors with directions. And so we encode those vectors in each polyline by 3 steps. The first step is that we project those input vectors into high-dimensional embeddings using a multi-layer perception. And then we basically do this graph propagation in 2 steps. First, we gather the vector embedding for all those vectors in the same polyline using max pooling operation. And then we propagate back the gathered information using this to each individual vector node. And you can imagine that because we are doing this graph propagation step, we can do that in multiple iterations with the goal to capture the higher order interaction patterns. And once we have gathered the information within each graph, so within each subgraph, now we represent each subgraph with a single aggregated feature node, as shown in this example. And we now want to exchange information across those different polylines using this global interaction graph, where the input are the aggregated features per polyline graph, and the outputs are the contextualized polyline features, which has the information from neighboring trajectories or neighboring road geometry. And finally, once we have done this, we encode this global interaction graph with self-attention layers. And once we have done that self-attention graph propagation, we can use the polyline node feature corresponding to the target vehicle history trajectory to do the future prediction task. And you can imagine this is a highly parallel process where if we want to predict multiple future trajectories for different vehicles, we can do that in parallel. And we optimize the vector net model using 2 training objectives. The first one is the standard target vehicle trajectory loss function, such as maybe using Huber loss between the ground truth future trajectories and also the predicted future trajectories. We can also use some auxiliary training objective where we randomly mask out a subset of the node features in the global interaction graph and ask our model to complete the masked node features. The hope here is to encourage our model to capture the useful relations between all end elements in the graph, not limited to the target vehicle. And we apply VectorNet on 2 behavior prediction benchmarks. One is an internal benchmark from Waymo. The other is a public benchmark from Argoverse. We compare VectorNet with a ResNet 18 encoder applied on the rendered maps. And we can see that the VectorNet achieves lower displacement error for both datasets with significantly fewer flop and parameter counts. For more comparisons and ablation experiments, please refer to our paper or we can chat offline. We also present a few visualizations to see why our model achieves better performance. Here is an example for lane change scenario. On the left, we show the roadmap in gray and the non-target vehicles in green dots, the ground truth future in purple, and the predictive future in blue. And on the right, we highlight the polylines that achieve the highest attention weights from the global interaction graph. And we can see that our VectorNet is able to identify the most important context. In this particular example, it will be the current lane and the target lane of the target vehicle. And we can also see that the highlighted lanes are very long-term, which is challenging for a convolutional neural network to capture. And here is another example at the traffic intersection. The vehicle, although the vehicle decides to go straight, I guess we can see on the attention on the shown on the right, to reach this prediction, the model actually attends to all possible alternatives, such as maybe not only going straight, but also the lanes corresponding to turning left and turning right. And it identified the conflicting scenarios, so it predicts that going straight is the most likely future direction. Okay, I have covered several topics in this talk. First, I talk about going from atomic concept that are fully supervised to more composite events, high-level events, where we don't have a lot of supervised information, and we propose a cross-modal learning formulation for that. And we also show that the cross-modal formulation can also be applied to learn representations, either for the temporal representations or the appearance information. And finally, we can go from recognition to prediction and encoding the highly structured interactive information with graph neural networks. And one natural future step would be, can we learn a unified model for both action recognition and structure behavior prediction with a goal to understand and model long-term dependencies in those long videos. Okay, thank you for listening. And if you have questions, please feel free to ask, and please feel free to reach out to me using emails offline. Thank you.
Okay, thank you, Chen. So then virtually thank the speaker and clap for him. So anyone, if has any questions, please write it on our live chat on YouTube. So at the moment we have one question regarding the video birds. So Yasser has asked that for the video birth model, the first question is that how much do you think the proxy, the fill in blank, tasks for recognition are limiting? Is there any way to downstream task without them?
I think that's a good question. I guess a good ablation experiment would be trying to do we need to have some predictive task to train our model. But the question is that whether we can do that in a cross-model fashion or only within videos. So in our video bird paper, we basically only show the cross-model case, and we provide two demonstrations, mostly qualitatively, that is able to capture the temporal dynamics and capture the cross-model dependencies. And in the follow-up work, the CBT work, we also do some experiments with video-only inputs, no cross-modal information at all. And then there, our goal, we do have some quantitative analysis on whether that formulation is able to learn better CNN features. And it's indeed shows that's the case. Yeah.
Okay. Thanks. I hope that Yasser has got his answer. And the second question, again from Yasser, is that can we learn a similar model without ASR?
I guess my previous question kind of also addresses this question. I guess it depends on how similar you want to be. There are a lot of people working on like audio-visual recognition, like where maybe you want to learn the semantic correspondence between pixels and maybe the sound of music instruments, or maybe even the honking sound of maybe some vehicles driving on the road. But at the end of the day, you want to have some interpretability. You want to have a semantic decoder. And if you want that decoder to be in text space, then you need to have some mechanism to establish that connection. And our solution to establish that connection is to using automatic speech recognition system to get the text information.
Great, thanks. So we've got another question from Santosh, if I pronounce it right. He or she has asked that how it's about the future prediction, the forecasting you talked about. The question is, how do you deal with the inherent uncertainty in predicting the future behavior? For example, do you have some type of probability distribution over possible futures? He's asking mostly about this uncertainty. How do you solve it?
Yeah, that's a great question. So, and that's a spot on, because in this particular work I just presented, the focus is on how to encode the structure information from the row graphs. And our prediction is a deterministic regression objective. But we do have a previous work on capturing all those inherent uncertainties in the model, such as maybe using a stochastic variational autoencoder. And we also have some maybe ongoing work. You can imagine that for the particular self-driving case, there are just so many possibilities that an agent can drive to. And then can you build a model to capture those uncertainties in those roadmaps and then use them to generate diverse plausible predictions? Yeah, that's a really great question.
Okay. So thank you again. It seems that there is any other question. I don't see any other question here. So do you have any, what's your suggestion for the people who have started their PhD recently, or maybe master students who want to start doing a thesis, and what they're interested in your recent works or the topics you cover? Do you have any suggestion for them? What's better for them to focus on? Or yeah.
Yeah, that's a very challenging question. I'm not sure if I have answers myself. I guess maybe try to read, but maybe do not read too much, because there are so many interesting papers posted every day online right now. I'm confused myself sometimes, and then maybe it's good to have your own interest, develop your own interest, and dig very deeper, and then believe in your research direction. Yeah, that's one of my suggestions. Yeah.
Great. Thanks so much for joining us today. And yeah, hope to see you in the next big event. Thanks so much.
Thank you.
Have a nice day. Bye.
Bye.
Okay, now we will have about 5 minutes for a break to start the next talk. Our next talk would be from Ivan Laptev, and the topic is about dynamic scene understanding. So this talk is a pre-recorded talk. It's not a live talk. And we are going to start streaming the talk in about 4 minutes. So yeah, and you can have a virtual coffee break or whatever you want to do, and then we will be back again. So I'm going to start the talk from Ivan Laptev, and he will be with us online live for the question and answering session after the talk. And yeah, you can ask your questions on YouTube live chat, and whenever he's online with us after the talk, I will try to address your questions and yeah, get his feedback. So yeah, start sharing. That's it.
Hello, everyone. Thank you for inviting me to speak. I'm Ivan Laptev from INRE Paris, and today I'm going to talk about dynamic scene understanding. So before we start with the talk, let's think for a bit, what does it mean to understand dynamic scenes? Or maybe even more generally, what does it mean to understand? So if you look up Wikipedia, so we see that understanding is a process, of course, which deals with abstract or physical objects, and the purpose of this process is to deal adequately with this object. So this is interesting because it implies that understanding means we are looking for a task, and understanding does depend on the task. So understand also means interpret, or could be a sort of a translation process. So if we now go back to scene understanding, so we could think of this as a process which is task-dependent translation of scene X, which is image or video of a dynamic scene, which is being translated into some modality Y in a way such that Y enables us or some other process to make a task. So this notion of task, I think, is very important, and it relates to what we are trying to do with our research. So let's see examples of dynamic scenes and also tasks which we may want to address in relation to this dynamic scene. So here's an image of children playing chess under the tree, and you can imagine a task where we have a text-based video query, YouTube, any other platform which wants to search such scenes by just typing text, or maybe we want to caption these scenes automatically. So this is one task which implies that we should interpret images or videos or dynamic scenes in relation to text. But this, of course, is not the only task which we may think about. So what about this picture? So here's a dynamic scene, and we all understand what may and will happen if the guy is going to pull the tablecloth. So how can our methods currently handle this? So this is a task of prediction, which can be very important, for example, autonomous driving or in some other scenarios. So here is another example of dynamic scene, which is actually unseen, but you can imagine that a dynamic scene which translates or brings the state of the world on the left to the state of the world on the right. And the task here could be a manipulation. So what kind of actions are required to bring the state on the left to the state on the right? So trying to just think where we are in computer vision and scene understanding. So I think on what we see on the left, so we have addressed these tasks for a while now. And so we have data sets which have labeled actions or videos annotated with text. And I'm going to show some of our work related to how to merge, how to marry the visual input and text. So this is, of course, interesting, important problem It is hard. It is not yet solved, but so people are looking into this. So the two other tasks which I mentioned, prediction and manipulation, again, so they are addressed, but addressing them in the wild is really hard, and I think they've been quite, relatively to the hardness of the task, there's been quite little work done in this domain, and that's, I think, where the future should be in dynamic scene understanding. So let's see, what are the challenging related to all these tasks. So first of all, that dynamic scenes and scenes in general, as we know, they're compositional. And compositional means that it's very hard, it's going to be very hard to exhaustively enumerate or sample all kinds of scenes which may happen. And examples which are here on the screen, they already clearly say, well, they visualize that, yeah, so compositionality and the fact that it's going to be, we are going to exhaustively manually annotate everything in the world around us, this is just not going to happen. And so we need some tools and methods which can deal without manual annotation, which is currently the mainstream, or the behind the methods which work in computer vision. Yet another important point which I want to bring up is that lots of dynamic scenes are about physical interactions with the world, between objects, between people and objects, and so on. And so if we are just going to look at the pixels and try to associate them with words, which is fine if we want to search the videos, if we want to, for example, provide instructions to people how to deal in a current situation, or even further, if you want to learn robots, which will, say, make a pizza for us, or do something else, just associating pixels with letters, with words, is most likely is not going to be enough, and we need more embodied reasoning and embodied interpretation of dynamical scenes. Right, so this is my introduction, and now I want to switch to a few works which we have done in this domain. So I'm going to talk first about how to associate videos with text. I'm going to talk about ICCV19 and CVPR20 work done in our group. And then I'll talk more about embodiment, and in the first case I'll talk about hands and objects and how to model them, and in the second work I'm going to talk about robotics manipulation. So what is, although these three topics seem quite different, so what is similar to all of them is that we are trying to address all of them without assuming we have manual supervision, any manual supervision, almost. And that's reasonable because actually to address them like already now or later, even in a larger scale, it's not going to be possible to do it with a manual supervision. So we want to avoid it as much as possible. Okay, so let's start first from this work, which we published at ICCV last year. So we are looking at, so what is our task? We would like to learn a joint embedding for video and text. So this is not a new task. So it could be useful for, as we said, video search by text, text search by video, video captioning, and many other things. Okay, so you want to learn a joint embedding model. So, and for this, so we don't want to use manual annotation, so we are going to search for resources which are available. And one interesting research which is widely available on the internet are instructional videos. You may have come across them either in computer vision literature or in your daily life. So there are lots of videos which are done by people, for people. They're not done for computer vision research. And these videos are, in these videos, people who made them, so they explain how they perform a particular task, and they also show it. And so these videos we've collected from YouTube. YouTube is now also very good to do speech to text. So actually we can automatically, with a high quality, get the videos and transcriptions of what people are saying. And here what you see, just a few videos. We see example videos. So we see that there are many videos for the same task. There are lots of different tasks. So we've started doing this work actually for quite a while ago, but more recently, so we wanted to go large scale. So we looked at much larger scale than hundreds of thousands of videos. So we looked at a resource which is called WikiHow. WikiHow, it's not a video resource, it's just a text resource which describes how things are done in general in the world. And so it's a hierarchy of tasks. So you can find lots of things like how to be healthy, how to sew an apron, how to break a chain, and so on. And so many of these tasks are not physical. So actually the only manual intervention we've done in the process of data collection was to go through a few thousands of tasks. I think there was a few tens of thousands of tasks, and just say if this task is represents some physical interaction with objects, or is it how do you meet your girlfriend and so on. Right, so we just filter them by hand, but everything else that was relatively small effort, and everything else was done automatically. So what did we get out of it? So first, as I said, so we took WikiHow, we filtered them, and to visual tasks, and then with the names of these tasks, we went to YouTube and collected lots of videos which are transcribed, so we can get aligned transcriptions with the video, and then for each piece of text, we can cut a piece of video, and in this way, we get about 130 millions of short clips with corresponding text, which is supposed to describe what happens in these videos. Okay, so these videos are not random videos. They're seeded by WikiHow, which is a resource of where description how things are done. So these are not necessarily, but often instructional videos in this data set. But this could be also vlogs and some other videos. Right, and so we've done zero manual annotation in terms of video captioning by text. So we have, so here on the diagram, you see that there are different categories. There's food, there's the largest one, there's health, home gardening, pets, hobbies, many others. Right, so here are just a few examples how the data looks like. It is not clean, and I will tell you later what I mean by this, but we also see lots and lots of diverse, realistic examples which represent different scenes, different tasks, different actions. So this is what we want. This seems to be a good resource. So let's see what we can do with it. So first, just what's the size of the data set? It's large. It's about 1,000 times larger than the previous one. With the caveat that the previous ones were manually annotated, or at least verified manually, that the captions for these video datasets were correct. In our case, we don't know, or actually we do know. So we did a small study by sampling random videos from our dataset, and it turns out that about 50% of them actually do not have correct text associated with them. So this is a problem, and I will come back to it. Right, so now in terms of the model, diagram looks complicated. Actually, there's nothing special about it. So we are just having a pre-trained video representation, which was trained on the kinetics dataset. We have pre-trained text representation, and then at the end, our joint embedding is just a few layers on top of pre-trained representations trained with max margin ranking loss. So basically, you want the captions and corresponding videos in this new embedding space to be close to each other, and negative pairs means captions from some other videos they should be far away from the current video. Okay, so this is a standard. So in terms of method, there's not much here. So what's really interesting in this work is how much we can get out of this very large data and very noisy data. And here are a few evaluations. So we see first check on UCOOK dataset, which is a similar domain to our training data. So we just take our embedding method, we train it on. So UCOOK2 has it's a great data set, by the way. So it has a training data set, training set and test set. So we are just trying our methods, well, the embedding with max margin loss. We train it on the training set of the UCOOK. We get some reasonable results, which are comparable to the literature. And now what's interesting that if we take our new data set and we train on it and not looking at UCOOK2 at all, and I think UCOOK2 was specifically removed from our How200M. So we see that this unsupervised data, or self-supervised, or whatever you want to call it, in any way, we didn't do any manual annotation of it, so it's able to outperform state-of-the-art on this data set, which was obtained with the supervised. Now, so so on the low part of the screen, so you see another task, so cross task. So here we see that similarly, so we train on How200M performance outperform. The performance is higher than the state of the art. And if you fine tune on UCOOK2, if you fine tune, so it gives the further improvement, right? So here is a small study of if we train on just part of the data set, we see a logarithmic scale on the x-axis. We see with more videos, the performance goes up. So we can imagine that it will go further as we collect more videos, and as collecting videos is almost free. So we can just increase performance further by getting more data. So what are the challenges and limitations here? So first, as already mentioned, so the data is just scraped. So there are lots of actually noise in the text coming from because of different reasons. So it's because transcriptions are not perfect, text and videos are often not aligned. Sometimes people talk about things before they do it, sometimes they talk about it after, sometimes they never talk about this, what they do, and so on. So there's lots of problems in this way. So that's definitely a challenge, and in the next part of my talk I'm going to we're going to see how to deal with this. So another limitation is that in this work we did not actually train visual representation. So the visual representation, the features, they were trained with supervised kinetics dataset, and which is slightly, well, it's video, but it's a different domain. So it would be interesting to see what happens if we try to learn the video features from our data, and actually also maybe if we can compete for feature learning with other methods which train video features on supervised data sets such as kinetics. So this is exactly the topic of next work I'm going to present. So it has been done in collaboration with DeepMind in London. So let's see. So what do we have here? So we are starting from the same data set, How200M. It's large and should be sufficient to train features. And so, okay, so here is you see video, you see a description of it, and okay, the goal is still the same. We want to learn joint embedding, where the videos and corresponding text are close to each other in the embedding space, and otherwise they are far apart. So here's the actual video with the sound. And what you could observe that actually it's not just one video and one caption, but that's what usually happens in this type of data where people are describing what they're doing. So if they're not just talking about exactly what they're doing, they can be talking about many different things. And as in the previous work, so which I just described before, so what we normally would be taking, we would take this small video clip and would associate it with the closest description in time, which would be the fresh herbs, maybe some oregano. Okay, so this is not very informative, and training on this data will have problems because we will be associating videos with something which is not very related, and we will miss important information which is actually in the text. So here we show not just one, but we show several textual descriptions, and indeed, like the first one and the last one here, they do describe the content of the video much better. So the question is, how can we learn from this data? How can we, during training, pick the correct relations between the video and the text so that we learn correct associations and not the wrong ones? So here is a schematic view of the problem. Again, so we have a video, we have a few descriptions which may or may not correspond to the video, and yes, so we want the corresponding descriptions to be close to the video, which is a green dot on the sphere, and non-corresponding descriptions to be far away. So, and for this purpose, we are introducing a new loss function, which is called MILANC, so multiple instance learning NC loss, so which is of course inspired by the recent literature on NCEs, and so how we adapted here, we instead of learning on single positive examples, we have here in this formula we have a sum. So within the brackets, you see the numerator, denominator, you see the sum, which goes over positive examples where X and Y's, so X is a video, Y is a description, PI, these are tentative positive pairs. So if you have a video which I just showed you before, so then PI would be all pairs of X, a video, and corresponding descriptions, which you're just seeing on the screen. So we assume all of them are potential positives. So this is a standard assumptions in multiple instance learning. You assume a bag of positive, well, I assume a positive bag which has at least one positive example, but you don't require all of them to be positive. So it's represented here as a sum, and okay, sum of what? So here's just we do a dot product of textual and visual representations of X and Y, right? And then so we have positive examples, and we also have negative examples. And the goal, of course, is to learn the representation, which is F and G, right? So G is a text network, F is a video network, and contrary to what I've described before, here the video network is going to be learned from scratch. Okay, so bag of positives, how we sample it, we just take a video, we take all neighboring, in terms of time, we take all neighboring textual descriptions, and these are our positive examples. And for negatives, we just take any random videos. Well, actually, there are different strategies how we sample negatives. They're important there in the paper, you can look it up. But in general, you can think of it as a random video, random description. Of course, you want to also sample hard negatives, and that's some details you can find in the paper. Right, so the architecture is not much different from what we had before, except that now we don't take pre-trained video features, we take a 3D CNN and we learn from scratch. So it's some technical details, so it's 10 frames per second. 32 frames. So it means that we are around, we take a video clip, our video clips are around 3 seconds. So it's already some, it's not 3 minutes, but 3 seconds can already capture quite complex events. All right, and the text representation is initially word to vec, and then, yeah, so there are a few layers on top of it. Okay, so now let's look at the evaluation. So here are our tasks. So we try to, so the hope of this work is to train really generic video representation. So we try to evaluate it on many different tasks and benchmarks. So we take 3 types of problems. So action recognition, action localization, and text-to-video retrieval. And for each of them, we have 2 or 3 different data sets where we test on. So first, let's have a look at comparison to the work which I just described before. So our ICCV19 paper, where we had pre-trained video representations, pre-trained on kinetics. So this is the at the left green bar. So if we test on UCOOC2, so you remember we already, right, so if you take the pre-trained video representation, if you train on kinetics 400, and then we on top of it, we train embedding using How200M. So you remember that we already outperformed the state of the art, yet if you would fine tune it on UCOOC2, so you would get even better results. Now the red bar on the right is our new result, and what's striking is that this result has been obtained without training on Kinetics 400 or any other data set which had manual labels, and it was also not fine-tuned on UCOOC2, and you see that results are much higher, and yeah, so by striking, because these results obtained without any manual supervision. Right, so so a bit of arguing why MIL and C loss is good. So first, let's look at just NC versus other losses. So, for example, max margin loss, which we have used in the previous paper. So here we see that actually it does not perform very well. So we think that it is because we are training it with noisy data. So before the representations were fixed, so it's we are not sure, but we think that the noise in the data was less important when we were just training few layers of embedding. When we now train the full video representation, the training might be much more. Our method might be much more sensitive to errors in the annotation. Okay, so NC versus margin loss performs better. That has been confirmed by other literature, so that's just reconfirmation, interesting. But then, so if we look at MIL and C, which is our new proposed loss, we see that the results improve quite a bit further, and this justifies or validates the importance of the multiple instance learning mechanism, and also not just any multiple instance learning. So for example, if you take max plus NC, which is a standard, I guess one of the standard ways to implement multiple instance learning, so it performs less good than our proposed MIL and C loss. Few more results. So for action recognition, we compare to self-supervised video representations on 2 data sets, HMDB, UCF, standard data sets for action recognition. We see that performance is good, outperforms the other methods. It's interesting in particular because our data set, okay, we wish it to be, well, it is very large and we wish it to be generic, but actually we know that it has a strong bias towards instructional videos, whereas HMDB and UCF, these are sports videos or actions from movies, very different domain, yet training video representation now data gives very high performance, which is interesting. And now, so compared to some other fully supervised representations, well, basically representation kinetics 400 video representation trains on kinetics. They are known to be strong video representations. We compare to these representations on several tasks. And we see here on all 4 data sets, we see a significant improvement with our method, which is also interesting. Okay, and so we've implemented this on search. You can try to solve. The link is on top of the screen, right? So if you just type anything, cut pepper, so in real time you will get answers like this. And it's the demo online is acquiring the UCOOK2 dataset, and again, so we did not train on UCOOK2, and its UCOOK2 has not been part of 100M dataset. So our code and models are online. You're welcome to use them and benefit from new strong representations. So I'm going to talk now about second piece of work, which is now relates to handling reconstructing 3D reconstructions of objects and hands, and this is a joint work with between INRE and Mark Polyphase group in Zurich, Microsoft Zurich. So what's the task here? The task is to, given just one RGB image, to reconstruct objects and hands. Why is it interesting? So first, yes, so there is lots of data. Of course, one could think that if you have RGBD data, the task would be easier. On the other hand, again, if you think of all the instructional videos or other videos on the internet, it's RGB, and if you want to learn from this video, for example, to how to manipulate, how to Kupitz or manipulate objects, we need to be able to do it just from RGB data. So that's the motivation. We had now the problem is that so there are methods, including our method from last CVPR to reconstruct hands and object. The problem is that the supervised approach is complicated because the data is very scarce. So there are 3 data sets which are not without markers and which have objects and hands, like objects manipulated by hands. So they're all done by manually verifying the ground truth. They are not very precise. Some are more precise, some are less precise. And because of this manual verification, so they are limited in number of objects, number of scenes, and so on. And now, of course, the size of the dataset is very small. So in this work, which is going to appear or has appeared at CVPR this year, so we are asking the question, okay, if we cannot, but doing it without annotation, well, we tried, so we didn't succeed. So at least can we do reconstruction with by limiting the amount of annotation? One way to limit annotation, because it's videos, you can say we're just going to annotate maybe 1 frame every 100th frame, and that's going to cut the annotation cost already by 100, which would be a great thing. Okay, so our setup is the following: we take a video, we assume that there is only a few frames annotated in it, and the rest we want to basically you want to learn not only from annotated frames but from other frames as well. So what's our model? So it's a neural network model which reconstructs the hand into a parametric hand model called MANO. It also reconstructs the object into a mesh. So both are mesh models, so both MANO and object, they are mesh models. And yes, you can find details of this in our previous CVPR paper. Things in terms of modeling the hands and object, things did not change. So what really changed is the way we try to deal with the missing supervision. Okay, so assume that we have a reference frame and which has been annotated, and then we have some prediction on a frame reference plus time reference plus k. So what we are going to do, we are going to align the, we are going to estimate the parameters of a hand and the object. And then we are going to, because in both cases, So in ground truth and the reconstructed meshes, objects and hands, these are meshes, so we can actually compute the 3D flow between them. Okay, and that's what you see here on the screen. And the 3D flow is going to tell us how the mesh moves between the ground truth and the and our reconstruction. And we want this so now taking these flows, we are now able to warp the image pixels from ground truth image into the frame where we don't have ground truth, and then we are going to assume that well, the illumination didn't change too much, right? There are not too many occlusions. Okay, this won't be true if we take too long intervals, but if we are in a sort of span of several tens of frames or 1 to 2 seconds, so hopefully we can assume this. And so what makes this model interesting that it's fully differentiable. So it means that we are reconstructing the hands, and we are using the known, assuming we know the camera parameters, we are warping the reconstructed object into the ground truth frame, and in this way we are able to compare the pixels and derive a photometric consistency loss. Okay, so which is shown here on the right. Okay, and so here are some results. So here we are training only with a 65% of fully supervised frames, right? So it's and so we see original frame ground truth. And if we just take this 65% of 0.65% of annotated data, we see that the model which produced with this amount of training data is really not great. So you see lots of errors, and here is the result of when we apply the photometric consistency loss, and we see that results improve a lot. Okay, so now I'm going to switch to the last topic of today, to robotics manipulation. So this work has been done by at INREA. And so the motivating story of this work is to, we wish to find out what actions are necessary to change the world from state 1 to state 2. Okay, so this is a typical problem. You buy IKEA furniture, you want to know how to construct it. Maybe you buy a house, you want to, and you imagine something which looks different. You wonder, how should you build this? So this is an interesting problem. Of course, it's what the examples shown here, they are way too hard, so we are starting something simple, more simpler, but we want nevertheless to have some more generic assumptions. So we want our method potentially to handle complex and diverse scenes, and so we don't want to make an explicit assumption about the state of the world. And you want, in this case, you only want to rely on visual sensors to find out what actions are necessary to bring the state from the left, the world from on the left to the right. Okay, so in this work, we are trying to learn how to build object categories. And categories for us here are defined by geometry. So, for example, an arc. So we take we assume we have some process which tells us, okay, if the robot is building something, is it similar to arc or not? Okay. So details are in the paper. That's not so important. And we also assume that we initiate our process with an arc, with the one example of an arc. Okay, so, and then everything else is open. You want just given an image on the left, we want our robot to learn how to build an arc on the right. So how do we do it? So again, so why this fits the story of this talk is because we deliberately don't want to annotate or provide knowledge to how should the arc be built, because this can be not an arc, this can be anything in the future, hopefully. Right, so what's the approach? The approach is divided into two parts. So first part is we are first going to discover the plans of building arcs in state space. And then we are going to learn visual policies in observation space. Okay, so here are a few examples what our robot can make. So, and what's interesting about the method, so because we are not even attempting to do any recognition or reconstruction of primitives, so we're just giving an RGBD image. And even if the robot is trained on this type of synthetic data, which is here, so it's actually able to handle quite well new primitives, which are given at test time on the table. So here are a few examples. And so here is our motivating example. Okay, so let me summarize. So I've talked about a few things which are related to understanding dynamic scenes. And as I mentioned in the beginning, understanding dynamic scenes means many things, not just associating videos with the text or videos with the labels, but actually understanding is related to different tasks which could be related to dynamic scenes. And this, of course, could be video search, but it could also be providing instructions to people or providing instructions to robots. And for this, we need understanding implies not just labeling or associating text, but also having embodied reasoning. And so that's what we are trying to do in our recent work, and hopefully in the future. So these pieces, they will be connected and they will reinforce each other, which is currently not the case, but that's, I think, where the future is for video understanding, which is combines together video understanding, robotics, language understanding, and yeah, many exciting domains. So thank you for listening, and I will be happy to take questions.
Okay. Hopefully, Ivan is live with us, and thanks him for his nice talk. Yeah, I can see him. So you can. Okay, you're unmuted yourself. So let's see if you have any questions. I see some questions on our YouTube chat. Okay, we've got two questions. Vivek has asked that he's curious about what is going to be the next big thing that you would like to see in the video understanding domain. It's a general question. Yeah.
Okay, so can you hear me?
Yeah, really well.
Okay, great. Yeah. Okay, so for general question, general answer. So I think we are not understanding the physics well. So like this prediction example, which I've taken in the beginning. So I think it seems we are far from handling this type of video understanding. And for this is important for like self-driving cars or for many other things. Like predict what will happen in the future, both in terms of forward physics, but also in terms of social interactions of people, which are not described by Newton laws, and they should be learned. But even things which are pure physical, which we think we understand how it works. So when it comes to real sensors and all real data, I think we will have to learn it. So we won't be able to just reconstruct the world and then apply Newton physics and deal with it. So to me, this is one of the big things which should come some point. And there's a question also, how do we get there? And okay, the possible answer is robotics could be a nice test bed. So obviously video understanding could help robotics, but I think robotics could also be our test bed to better understand video.
So by saying that robotics can really help us in video understanding, and also video understanding can help robotics, you mean that the feedbacks we can get from the interactions of the robots with environment can help us in just having better models for video understanding, or just the people who are working in robotics can help us? Can you elaborate on it?
Both. I hope both. Yes, but I was actually meant first as a just interaction here, because currently when we talk about video understanding, video is pre-recorded and it's fixed, right? So we cannot change it. We don't know, like if the person would move 5 centimeters to the left, what will happen? Maybe something drastic will happen, and right? So there's no. And also another thing, like, so I talked about instructional videos, which is a great source of data. But in all these videos, people, when they record, they usually know what they do. So they usually perform things right. So if you want to understand, if you want to actually provide instructions to people how to perform different things, then obviously we'll definitely need to know. We need to observe situations where things don't go right, and yes, so getting this data is currently not obvious. So I think we need to move from passive vision, I would say, back to active vision, because I think in the beginning, at least in my lab where I did PhD, so from the beginning, the lab like 30 years ago, it was created as an active vision and perception lab, which was jointly with robotics. I think that's one of the paths where vision might be going in the near future.
So you think that RL will really help us in the future? Reinforcement learning, I mean.
Yes, RL is, of course, popular and seems to be suitable, but it seems, so the evidence which we are building is, people around the world are building that just pure RL is hard to, it probably won't solve all our problems, because so if it's well, there are two things. One is reward engineering, which seems to be lots of handcrafting, and like if you have sparse reward, the supervisory signal seems to be very very weak to train, say, CNNs. That's at least our impression. I think people are making similar conclusions. So, but yeah, of course, RL is a powerful tool, so it should be used, but probably one should think of other combinations, not just RL.
Yeah. And do you think that for improving the video understanding, you said that, okay, using this feedbacks we can get from robots, the interactions they have with the environment. So there is this chance that we get better data, so we can learn the physics better. So you think that we need more or better data, or we also need better models or algorithms? For example, at the moment we have, for example, we have this kinetics data set for action recognition. So you say that it's better to invest more on increasing the data, the variation of the data, to make it more general, or also we should somehow change the design of the models to enforce them or structure them in a way to get better representations?
So I think models should model the data. That's their purpose. So here, maybe the answer here to your question is in two things. So one is that we have lots of real videos, and like kinetics, so we can just scrape internet and get even videos with captions. But this is passive data, so we don't have interaction. We cannot we observe interaction with the world, but we cannot drive it. And this data is very diverse. So of course, what people are doing is good to build the models for the data. Now for robotics, so where you have interaction is good, but the data is going to be first limited and probably not at all diverse, because what we are collecting is in the labs, right? So probably it will take some time before robots will get out and everybody will start using them. So probably we won't get active data easily. So and that's maybe the challenge for the models. So how do we build models which combine the best of these two pieces of data streams which we get? So one is active but limited in diversity, and another is passive and but very rich in different environments and so on. So I think there is lots of opportunities for interesting models here.
Thanks. So we've got another question on our YouTube chat from Victor. He's asked, what's your opinion of keep labeling videos? He mentions actions, in particular with grounding them on instances, for example, actors, objects, scene, states. I think he's somehow addressing our dataset for this holistic video understanding tutorial. Anyway.
Right. I'm not sure I got the question. So if we should increase our data sets, so what was about grounding?
I think he means that he says that what's your opinion of keeping labeling videos, the actions, and I think he means adding more knowledge, for example, about adding actors, objects, scene, states.
Right. Okay. So actually, I have nothing against labeling. So if people kind of spend their time and money on labeling, I think this will improve things. The question is how much will it improve in the long run? So I think this path is it's a path. So with kinetics, we've seen great improvements actually. So it's a valid path. It's just not very clear how it's scalable. So I would also, because we know that we can label data and it will bring us something. So, but I hope and think some people share this, that to really get the big improvement, labeling will be a bottleneck. So we would need to do something else. But for example, for like if company is doing a product now and they want to get a precision, so I would still suggest to go and collect the data for the specific domain which they needed, and so there are different needs, right? So if you are short term, so I think yes, labeling is definitely good, and it's also interesting where will it bring us. It's a belief. I think it won't bring us. It will bring us only up to a certain level, and we would need to live without labels to get the big improvements.
Great. And unfortunately, there is a little bit latency between the stream we have on Zoom and YouTube. So I'm getting some more information regarding the question Victor has asked. He says he means labeling at the video level without saying who does the action. And so let me check the.
So maybe the question is about like rich labels, right? So it's not just about.
Yeah, I think because he said we are talking about the holistic video understanding, and a single action label doesn't cover the whole spectrum.
sure, like for example, like many actions. So there are work on from Makaran, for example, so on action graphs, and where they are trying to model the multiple people, multiple actions. I guess also objects. Yes, of course. That's this is an interesting direction, definitely. And I think labeling is also important to evaluate things. So, to make to make progress, we need at least have a good measure of the progress. Right? And so at least so if not for training, I think for training obviously it's also interesting, but maybe limited. But at least for testing, we will need label data sets for testing.
Okay, so it seems that there are no more questions. Thank you again for your great talk, and thanks for being with us today.
Thanks for organizing this tutorial.
You're welcome, and have a nice day.
Okay, bye.
Sorry, Victor. I just got this new question you asked. I'm not sure if Ivan is still with us or not. Yeah, Ivan,
I can come back. Okay.
Yeah, thanks. Okay, Victor says, we know how to label. Do you think we know how to label videos in a general and holistic way? I think he's asking about that. Okay, if we want to label videos, then what's the best way?
Right. Okay, that's
really expensive to do it for frame wise, and I think that having this bounding boxes, and he's asking about the video level labels. So
right. So another thing which I usually talk about is that we don't even know how to label. So we don't know what to label and how to label it. And this starts with the intervals, like if you want to say where the action starts, where it ends, so you know it's very ambiguous. And then labels themselves. So it's like this example of opening. So one can open many things, and sometimes they're completely different. So so language is it's helpful, but it's quickly starts to be very ambiguous. The temporal boundaries are very ambiguous, and yeah, so that's well, these are problems we know, and so I think that's another issue with labeling. So it's not just it's expensive and complicated; it's very ambiguous. So it's very unclear to me if we can come up with a good, in some way, these labels, they're like our proxy task. We hope that by training on kinetics labels that we will be able to do some other things, right? So so there are two ways. One is to try to come up with this labeling, which will be good, or maybe go directly to the end tasks, and or maybe some other intermediate tasks. So since we've tried to label things for a while, so and I'm more excited now of going further, and that's why we are looking at robotics and things like that.
Yeah. Okay, thanks so much again for joining us and also answering these questions. And yeah,
Okay, I hope Victor is got the answer.
Yeah, have a nice day, and bye.
Thanks. Bye.
Okay, Victor, we will also cover this holistic video understanding and also the holistic video understanding data sets in one of the talks. Juergen is going to cover it, so we can have more discussions then. And now I'm going to go for the next talk. Hopefully Andreas is online, And yeah, hi, Andreas. So our next talk is by Andreas Geiger, and the topic is unmasking the inductive biases of unsupervised object representations for video sequences. So I'm going to let Andreas to be our co-host, and then we will go for, unfortunately, I'm not too familiar with this Zoom thing. And okay, so Andreas, you can go.
Oh, I can speak now. Good. It's that I can't speak. Hello. Yeah, thanks for having me. Welcome, everyone. Let me try to share my screen. So I do maybe 40 minutes plus question or something, 45 minutes, that's fine?
Yes, it's fine.
Okay, can you see my screen?
Yeah, we have you.
Okay, so yeah, I want to talk about a particular type of video representations, which are unsupervised video representations, which are actually quite challenging to obtain. So the basic question is that we're asking recently is very fresh results, actually, that I'm showing today for the first time, is what can we extract from a video without any supervision? And there is, in the last couple of years, there's a little bit of progress in that area. And we wanted to find, to base these results on a common ground, and compare these methods on a fair basis. And also we have a few contributions in converting like static image unsupervised learning approaches to video learning approaches. It is joint work with my collaborators at University of Tübingen, Marissa and Kashyap, who are the main students involved, and Yash, Wieland, Matthias Bethke, and Alex. So let's start by looking at the problem of object-centric learning. What is object-centric learning, and why is an explicit object representation desirable? Now, what I would argue is that an explicit object representation is a crucial prerequisite for reasoning and scene understanding. And that is something that is developed by every individual. Maybe some of this is innate, some of this is developed over time. So here's an impressive result, an impressive example of this with an experiment conducted with a cat. Maybe some of you have seen that. That's this a cup experiment. I hope you can see my stream. It's maybe a bit too slow, but it's I tried to follow these cups and I had a hard time with the original video. Okay, cat got it right. Now 4 cups. Here's the ball. Mix them up. Cat, which one is it? Oh, cat got it right. So maybe that's just a coincidence, but there's actually many videos like this on the internet with cats. It seems like cats also develop some sort of object level representations that allow them to solve quite challenging reasoning and tracking tasks. Right? Another reason why you might want to have an explicit object representation is that it's just like the real world is too complex and you want to transfer knowledge about an object from one context to a new context. Here we see an example from Carla self-driving, where you have this car here in different environments, which all look completely different, but it's the same car, right? So it's important, it's actually the same environment, just the weather situation changes. It's important to recognize this, and it's easier to recognize this if you have an explicit representation about object, and not just, I mean, explicit, I mean, it's not just implicitly hidden in a pixel matrix of intensity values, but it's really some object level representation of the scene. And then, of course, the world is very diverse, and if you have an object-based representation, you can collapse the combinatorial large space of scenes. So you can compress the entire world. You don't need to represent the image manifold, which we likely don't do, but we represent the world in terms of its objects, which is a much more compact way that allows us to do inferences and causal reasoning. So if you talk about objects in video, like you talk about one thing that you talk about in computer vision is object tracking. And one of the most dominant paradigms for object tracking is tracking by detection. In tracking by detection, the input is a video sequence. And in the first step, you train an object detector to detect objects in all frames, maybe a faster RCNN on a bounding box loss. And then there's a second step where you take these detections from the pre-trained detector and you train or apply a data association mechanism that gives you then the final trajectories. And that's trained on a video-based loss where you have ground truth for the associations. So this is all fully supervised. Here you have ground truth for the detections. There's a lot of annotated data. Here you have ground truth for the associations. There's a lot of annotated data. And then you have the final trajectories here on the right as an output of this stacked system. Now, the problem with this is, of course, this requires huge amounts of labeled data, and humans are not likely to do this. There's not that level of supervision for all these tasks. So it's more likely that humans develop some of these capabilities in a rather self-supervised or unsupervised way. And that brings us to the topic of unsupervised object-centric learning from videos. There's a large body of literature on discovering objects in still images or on tracking objects in videos without supervision. So that's the important keyword here. It's without supervision. There's no 2D bounding boxes. There's no associations. There's no segments. There's just video sequences as input, like you could obtain them from YouTube. And there's really recent progress recently, as you can see from this line of publication works in major conferences. The problem with this is that all of these papers that I've shown you in the previous slide use very different objectives and evaluate on very different tasks and in very different applications. Some of them focus on model-free reinforcement learning and focus mainly on getting good performance on these reinforcement learning tasks. Others focus on model-based reinforcement learning. Others focus on generative modeling of scenes, and so forth, right? So in generative modeling of scenes, you focus more on the image quality, like the reconstruction loss. As a result, all of these methods have, well, as a result of these different developments, these methods have different inductive biases, which are hidden in their formulation because they are not compared on a fair or equal basis. Some might strongly associate object identity with appearance. They might just learn from videos that it's important if I see a red object that I associated in another frame with another red object. Others might prioritize motion cues because motion is an important cue for association. This is currently not well understood, and there is no common evaluation protocol or benchmark to evaluate these unsupervised object learning approaches. In order to come up with such a framework, we first need to quantify the desirable properties of an object-centric representation. The first thing that such a representation should be able to do so, it should effectively identify objects as they enter the scene. It should also accurately segment the object shape from the background or from the other objects in order to identify individual instances. It should maintain further a consistent representation for each object over time. That means the object identity shouldn't switch. It shouldn't flip between two different objects. So in this talk, I'm gonna present a analysis that uses the multi-object tracking protocol that analyzes the strengths and weaknesses of different kinds of object-centric representations that have been developed for different downstream tasks, but now the analysis is with respect to a particular task, which is this object discovery and object tracking. So before we go into the analysis, let me present to you these different techniques and how they differ from each other. There is a common principle that underlies all these techniques. The common principle is that these techniques try to decompose video frames into a number of slots where a slot is for a single object. So here you can see, for instance, these video frames over time, and there's these input images here. You can see that the objects move. And then for each time step, this is time step t, this is time step t plus 1, the object gets decomposed, or this image gets decomposed into the individual objects. There is typically a mask representation that identifies where this object is located in that frame. And there is a latent representation that is representing the appearance of that object. And then there's a decoder and a combination step that combines these decoded results into the image again. Right? It's a kind of an autoencoder. It takes an image, tries to produce the same image, but goes through this bottleneck of decomposing the object into different components. And by adding this bottleneck, hopefully, automatically object-centric representations emerge. Now, when we have a video, we want to, of course, integrate information over time. So video-based approaches use typically on the latent space a dynamics model that connects these different slots over time, such that objects, for instance, move approximately linearly. These are these dashed arrows that you can see here on the bottom. Right, so this is the common principle. Just to recap, the common principle is to decompose the video frames into k slots per frame with 1 slot per object, and to reconstruct the video frames from this latent representation. And then there's different types of models in terms of dynamics and in terms of this decomposition. Now, let's characterize the different approaches that exist in the literature. There are 3 categories of methods. The first category are spatial attention models with unconstrained latence, which predict a per object attention mask and typically have a VAE for representing this mask and appearance. And a representative from this class of models for single images is Monet. And we extend Monet to the Wyman approach. This is the video Monet approach by adding a temporal component to it. Now, in contrast to spatial attention models with unconstrained latence, which basically model for each slot the entire object, and the location is implicit in this representation, spatial attention models with factored latence explicitly model the position, scale, and orientation of each object and use a spatial transformer model to compose them into the image. Examples of this category are AIR, SQR, TBA, and Scalar. In this work, we take TBA as a representative example of this category of techniques. And finally, there are spatial mixture models. They perform a clustering in feature space and process all of the slots in parallel. And examples of this category are neural expectation maximization, iodine, which is a single image model, or OP3, which extends the iodine model to video sequences. Now, in the following, I will talk about video Monet, TBA, and OP3. Let's start with video Monet. So this is the overall structure of our video Monet model. It's a sequential model which sequentially processes these slots. You can see an illustration here on the right. The input is the image. There is a sequential processing of slots where an attention network always gets the feedback from the last reconstruction. It's actually not illustrated here, but you can imagine there's an arrow here. And then there is this variational autoencoder here. There's some connections along time. And then the output is the prediction in the current time step and the prediction in the next time step. Okay. So for each slot, there's an attention network. There's this slot VAE GRU, this gated recurrent unit that propagates the latent code over time. And then there's the decoder. And then there's a current frame prediction and a next frame prediction. And both of them composite together the frame. So let's look a little bit at these individual components. So let's look first at the attention part here. The attention model is a neural network that outputs a attention mask, MT, for slot, for time step T and slot K. It takes as input the VAE prediction, also the decoded prediction of the mask at that current time step, which has been predicted by the previous time here at time step t+1, we predict for the next frame, right? So this is what goes into the mask, attention mask. Then we, of course, observe the current frame, xt, and we observe the scope at time t for the previous from the previous slot. The scope determines in which regions we have already attended to and which regions we still need to attend to. The scope basically is multiplied with the mask successively, such that starting from an all empty image, we successively cover the entire image. We actually choose the last slot as everything that remains. The last scope as everything that, the last mask as everything that remains from the scope, such that the scope completely explains the entire image. In the beginning, maybe it's just the blue and the red object that are part of the scope mask, then the green object, and then the background, right? And then, of course, the scope is also multiplied to the mask to make a hard decision about which regions the model should attend to. This is the attention model, and it's iteratively applied over all slots, starting from the first slot to the last slot. Then there is this encoder part here. We have an encoder in the model G. This is also a neural network that takes the image and the attention mask M that produces a latent representation C. That latent representation is then propagated along time using a gated recurrent unit combined with the previous information. And then there is a VAE that decodes the image at the current time step and the image at the next time step and the mask at both time steps as well. And we use a standard VAE, so this means we sample C using the reparameterization trick. And then the next frame prediction here, this is this part here. It's not exactly illustrated in this figure here, but what we do is basically we assume a linear transformation A on the latent representation and transform the latent vector to the next time step using this linear transformation, where this is decoded into the image and mask. This is how the next frame prediction works. This is this arrow here, basically. This is an assumption that prior works have shown to be effective. It's actually a regularizer on the latent space to say that, or to enforce that linear motions in latent space correspond to actual motions in pixel space. So this enforces a regular and simple structure on the latent space, and it also makes optimization easy because we just have a linear combination here. Yeah. Then, as I mentioned already, both the latent code from the current time step and from the next time step are decoded here using the VAE decoder. And then at the very end, for each of these time steps, the frame is composite by just summing up the image, the appearance information multiplied per pixel with the corresponding mask. So each of the slots has a mask and an appearance image, and then we multiply them together and sum them up, and this yields our final image. The model is trained using a VAE formulation, more precisely an extended VAE formulation that comprises the common VAE terms. So it has, for instance, a reconstruction term here. You can see this is a mixture model of the likelihoods of the actual observation. So we have the observation at time t and the observation at the next time step here. And we train in a batch setting, so we always have all observations for the entire model. And then we have these KL divergences here, which compare the latent code to a standard distribution and also the masks. The next model that I want to talk about is tracking by animation. This is a model of the category spatial attention with factored latence, because here, in contrast to the previous model, we don't have a VAE that for each slot or for each object represents the entire image. But we have a representation that represents each object in terms of its local coordinates, where it is in the image. What this model does is it assumes that there is a static background, and it pre-processes these images with a background subtraction stage using color histograms. So this is a little reprocessing step that works for the simple scenarios that we consider. I have to remark here at this point also that all of the models we evaluate on very simple video processing tasks, because we don't have any unsupervised model at the moment that is able to work with YouTube videos. This is actually the ultimate goal, but we see that these models already fail for quite simple tasks. So that's where we are at in this community at the current point in time. In contrast to the previous model, it processes all K slots in parallel, so there is no sequential attention mechanism, and it has therefore a shared feature extractor. So there's just one feature extractor that's shared across all slots, and for each slot there is a tracker array, there is a mid-level representation, and there is a spatial transformer rendering that then composites these positional appearance informations into the final image. So let's look a bit at these different components. The tracker is called a reprioritized attentive tracking. So after the feature extractor, this RAT tracking is applied here. So let's look at what this does. It's basically, it's a very sophisticated mechanism. It's taking the features from the input image, storing them in memory and considering them as memory. And then each of these slots, which we see here in this row, sequentially read and write from this memory. So green denotes a read, blue denotes a write. And then we have an RNN update using the modified memory, the memory after the write, which has CTI instead of the original CT. And in order to avoid the low confidence trackers, which are by chance coming first in this process, steal detections from trackers that have a much higher confidence, that's actually a common problem in tracking. Here, there's a learned prioritization of these trackers. So each tracker gives a confidence of how confident it is about currently tracking an object. And this is applied for reordering this read-write mechanism so that basically the most confident trackers are able to grab the detections first. Okay. And then in the mid-level representation, this is now the explicit representation, the factor representation. This latent vector is further decomposed or factored into different components, which we can see here. We have, for instance, the confidence, which I was just talking about, which is used for reprioritization. We have the image layer YL, which denotes basically in which order it should appear. So this tracker has an explicit notion of what's in front and what's in the back. So you can explicitly model with this one hot encoding here for a different number of layers O on which layer each object should appear to model occlusion behavior. And then it also has the pose in terms of the scale and the translation here. And it has the shape. This is just a pixel matrix, a binary matrix, which is 0 or 1. This is basically the mask. And it has the appearance, which is an RGB color values for that particular object. Then in order to composite an image from this representation, a spatial transformer network is applied, which scales and translates the shape representation Y that I showed before using this spatial transformer. So here you can see an example. There is a mask, a color, then there is the location and scale, and then the mask and color are inserted into the image at a particular location at a particular scale. Here, for instance, you can see that the scale is not is different in the different directions. So this object here gets actually squeezed a little bit, or this object here gets stretched a little bit. All right, so stretching and squeezing is modeled explicitly through the scale parameters. And then the final composite frame is composite by synthesizing K image layers by their masks and appearances that I've just shown based on the predicted confidence and layer. So there's basically a depth ordering happening here, or an alpha compositioning, if you will. So the compositioning equation looks similar to before, but it's happening based on these layers. You can see an example here. So for instance, in this case, the green object is inserted in the layer after the so this is the first layer, this is the second layer, so it's inserted in the layer after this purple object so that it occludes the purple object. And then this model is trained using a pixel level reconstruction objective using a mean squared error. And we have another term here that penalizes large object scales in order for the model to yield compact objects. And finally, let me briefly review the OP3 approach. This is object-centric perception, prediction, and planning. And it was first introduced also very recently in the context of robotic learning. So the task originally was robotic learning and not tracking, but of course it does tracking implicitly as part of this process. So again, this model, this is a spatial mixture model, and again, this model, as the previous one, processes all slots in parallel, all k slots, but it has an outer loop. You can see a second plate here, which does m sequential refinements. And it doesn't have this memory mechanism that we've seen before. Instead, it takes the input image and starts with a random guess of the segmentation, processes this into an image, compares this image to the actual image, and if it's not good enough, it starts doing these refinements for a fixed number of steps m. So for each slot, there's a refinement network, and inside there is also an LSTM that propagates latent information over time here. In addition, they have also a dynamics networks introduced that can model more complex dynamics as the previous approaches. So as you can see, all of these approaches are quite diverse. So OP3 starts from an initial guess of latents for the whole image and iteratively refines this guess m times with a CNN for each time step. And this is what you can see here. So there's the iterations. It's actually derived from the iodine model, where in the first the current latent representation is decoded into an image. It's compared to the observation, and then it's refined and passed on to the next iteration with the LSTM. And then after m iterations, there's a dynamics network that propagates to the next time step. The dynamics model models individual dynamics and pairwise interactions between all combinations of objects and also initializes the posterior for the next time step. The difference to the previous approaches is that this is explicitly taking into account pairwise connections between models, between objects. As you can see here on the bottom, on the left, there's the encoding, there's a unitary processing, and then there's this pairwise interaction matrix. As you can imagine, this only works for a small number of objects, but all of the examples that we see here in our results actually work with relatively few number of objects. We typically go up to 6 or 10 slots in our experiments. As we're not interested in action prediction as in a robotics task, we don't consider the action intervention component here. So we have removed this component for our tracking setting. The model is trained similar to a VIE, also here using a VIE decoder for the masks M and the reconstructions, similar to the video Monet approach I've shown in the beginning. And an elbow is minimized over M iterations and T dynamic steps. So you can see T and M appearing, and you have the slots K inside here. But again, you have a reconstruction loss in terms of this mixture of likelihoods here, and you have the KL divergence between the encoder and the encoding distribution and the latent distribution. So let's look at the experimental study that we conducted. As already mentioned before, the evaluation protocol is derived from the MOT, Multi-Object Tracking Challenge, which quantitatively evaluates different performance aspects of object detection, tracking, and segmentation. In particular, it considers objects as detected if they have an IOU of bigger than 50% between the predicted and the ground truth object mask and the considered match. Now, in contrast to the classical MOT evaluation, which uses which considers bounding boxes, here we really consider the actual object mask that is predicted by the model and the ground truth object mask, which is a harder task than just getting the bounding box right. As error matrix, we consider the fraction of misses, the number of ID switches, the number of false positives relatively to the number of the ground truth masks. And we have the standard clear mode matrix MOTA, which is the multi-object tracking accuracy, which measures the fraction of all failure cases compared to the total number of objects present in all frames. There's 3 different failure cases, and it's basically dividing by all possible. So in effect, 100% MOTA denotes perfectly tracked objects without any misses, ID switches, or false positives. And a good MOTA requires good detection and tracking, but not necessarily good segmentation. In contrast, multi-object tracking precision, which is also a standard metric in MOT, is the average IOU of segmentation masks for all matched objects. This means that 100% MOTP indicates perfect segmentation, but not necessarily good detection and tracking. Right? It could be that there is a lot of detections missed, objects missed, or not correctly tracked, but the segmentation is still good. And then there is mostly detected and mostly tracked, which measure the fraction of ground truth objects that have been detected and tracked for at least 80% of their lifespan. If an ID switch occurs, an object is considered detected but not tracked, for instance. We evaluate these different approaches on 3 synthetic data sets to cover multiple levels of visual and motion complexity. As you can see, this visual and motion complexity that we have here is still far from the visual and motion complexity that we'd like to have on real data sets like the Kitty dataset. On the other hand, it's a very challenging task, and it will be exciting to see how we can scale this model to real-world scenarios. The first dataset we consider is the SpritesMod dataset, a dataset that has been proposed before, which has 4 templates in 2D, simple linear motion, and which has a fixed orientation for the objects. It's quite simple, minimal size variation only, and 6 colors. The background doesn't move and is black. For the video, we have created 2 more data sets for evaluation. The video object room data set that we've created is a data set of 3D scenes using an OpenAI environment that contains static object motion. So the objects don't move, but the camera moves. It's a moving camera. It contains a varying number of objects and moderate size variation of the objects due to the camera motion and the perspective projection. Random colors and 6 colors random orientations and up to 6 different colors. And finally, we have the video multi-desrites dataset, which is a more challenging dataset than this one here, which has, in contrast to the SpritesMod dataset, nonlinear motions. It has moderate size variations, has random orientation, random color, and also random background color. So it's much more challenging for the trackers. So let's look at the results. We show the results as the mean plus minus standard deviation over 3 runs using different training seeds. What we can observe is that on SpritesMod, all methods perform comparably well. You can see all methods have a relatively high MOTA performance. Even the Monet approach, which considers each frame independently, has an inductive bias to correctly track these objects. For instance, by classifying objects that are read always in the same slot. So this is an artifact of the simplicity of this data set. What we observe is, Monet correctly detects and segments objects, but fails in assigning them. So we have a high detection rate, but a slightly lower tracking rate, which also is visible here from the mostly tracked performance. So while it can track objects to some extent, it's compared to these other techniques, it's much worse. And that's also what we would expect from a single object approach. In contrast, Wyman and OP3 perform much better in tracking. So we have 92 and 89% performance. And they also perform better than TBA. However, what I want to highlight here is that some of these approaches, because they are quite sophisticated, fail in actually training for some of the runs. So for instance, TBA, which takes long for training, fails in one of the runs, so that we have a larger standard deviation here. So that's we are coming back to the optimization properties of the different approaches later. Wyman has the best segmentation performance here. 91, which is derived from Monet, but can even improve on the single frame variant. So let's look at the results of this three-dimensional video object room dataset. Here we cannot evaluate TBA because we cannot segment these dynamic backgrounds. So we only compare Monet, VD-Monet, OP3. What we observe is that tracking does not automatically emerge in image-based models. Here, the tracking performance of the single image baseline reduces significantly with respect to the previous dataset, and also the accuracy of tracking now decreases. So it seems to be relevant to have a temporal component as we approach more challenging datasets. Wyman and OP3 are similarly good on segmentation, as you can see here. But Wyman is better on tracking compared to, for instance, comparing the MOTA and the mostly tracked performance here. This means that Wyman can better handle the camera motion and 3D scenes than the OP3 approach that tries to iteratively segment the image. OP3, in contrast, produces many false positives and splits objects and background segments. And here are results on this more challenging sprites dataset, the VMDS dataset. Here we can observe again Monet fails in tracking and also in segmentation. OP3 outperforms all methods, and it seems to handle nonlinear motion and random size, orientation, and color, which is the prominent property of this dataset, very well. So performance on all of these is very good. Wyman performs slightly worse than OP3 on all three metrics, and Monet and TBA fail or suffer from training instabilities for some of the training runs. Particularly here, TBA fails in one of the training runs. The next question we ask is, well, how well do these models now accumulate evidence over time? How much are they relying on temporal information from the past? We conducted a study where we plotted the MOTA performance on VMDS, the most challenging dataset, after the warm starting of the approaches. And we observed these results here. So you can see how many warm-up frames we use on the x-axis and the different approaches here on different colors in terms of their performance with respect to nominal performance with warm start 2. What we observe is that Wyman in blue improves with longer warm starts, but then saturates at some point. TBA seems to not be relying on temporal information beyond 2 or 3 frames, indicating that its temporal model cannot cope with temporal information well. OP3, in contrast, strongly relies on past information and seems to improve performance while not saturating, here in green. We also investigated the dependency of the performance on the number of objects present in the scene. Here we can see the distribution of failure cases on VMDS based on the number of objects that are observed. What we observe is that more objects increase the number of failure cases for Wyman and TBA. As you can see here from the blue and the orange plot, which grow with respect to the number of objects in the scenes. OP3, on the other hand, accumulates more false positive in the beginning for a small number of objects, but it handles larger number of dynamic objects more gracefully. Let's look at some qualitative results, in particular, some challenging cases for these techniques. Here, what we can see is the ground truth sequence. Let's look at this for a few moments. We can observe that this heart moves behind the blue square, which moves in front of it, which makes it very hard. So there's strong occlusion happening. And it turns out that occlusion is challenging for all models. For instance, we observe that Wyman breaks the segmentation into 2 pieces, OP3 as well, and TBA completely fails at some point. We also observe that similar colors are challenging for all models. Here we see the ground truth where this square and this ellipsoid have similar colors. We can also see the reconstructions, by the way, that the methods produce. And here we see the segmentations in the last rows respectively. We observe that in this case, Wyman merges some of the segments, but does not merge the similar color objects, so can handle this relatively well, while OP3 merges the similar colors very rapidly, and TBA produces or loses some of the objects. We also observed that TBA struggles with dark objects and OP3 with similar object colors, as I mentioned before already. So here you have a ground truth sequence where you have these two objects of similar color, and we observe that, for instance, in the case of OP3, the objects are merged into the same in red here, and TBA ignores some of these objects completely by producing this one object reconstruction. OP3 also sometimes misses objects with similar color to the background. Here we have an object that has a similar color to the background, and OP3 just does not reconstruct it, which you can also see from the segmentation mask. TBR tends to compose larger objects using multiple smaller components. Here we have an example of this. There's a large heart that's moving. It's actually a quite simple tracking scene. We can observe that the reconstruction, while the reconstruction looks reasonable, the object is implicitly split into two slots. So the implicit representation is not right. So in order to investigate this a little bit more systematically, we created a VMDS challenge dataset that contains the most challenging scenes or sequences from the VMDS dataset. For instance, scenes that have large motions, where objects frequently occlude each other, small objects, which might be difficult because just objects are small and harder to detect, which have strong occlusions, or which have objects of the same color. Here we see the results on this VMDS challenge set relative to the performance on VMDS, which is the 100% line. What you can observe is that, so we have the occlusion, the same color, the small objects, and a large object data set here on the x-axis for motor and mostly tracked metrics. What you can observe is that the occlusion reduces performance of all models. You can see that it's worse for all models. OP3, however, is the most robust, and we attribute this to this dynamics network that it uses. TBA performs worse despite the explicit occlusion reasoning, which is surprising to us. Despite explicitly building in a component for occlusion reasoning, TBA performs worse than all the other approaches on occlusions. And OP3 relies most on object color. OP3 relies most on object color and suffers in the presence of similar colors. You can observe this here by the same color experiment. Smaller objects are easier for TBA due to less occlusion. So here the performance even goes up, but that's an artifact of the fact that with smaller objects, we simply have less occlusions. The performance of the other methods remains unchanged. We also tested these techniques on an out-of-distribution test set, where we have basically novel sizes of objects, novel rotations that haven't been seen at training time, or novel colors. The performance of the out-of-distribution set is surprising to us because all of the methods seem to handle unseen sizes and colors relatively well. You can see that the performance is almost not degraded despite the out-of-distribution test set. However, Wyman suffers in the presence of unseen rotations quite dramatically, as you can see here on the last column. We also looked at the runtime of the different approaches, and they are actually quite computation heavy, in particular considering that these are relatively simple sequences that we consider here. For this experiment, all methods were trained on VMDS for 1 hour, and we report epochs and memory consumed. And for inference, we evaluate the models on VMDS with a batch size of 1 and 10 frames. We observed that TBA trains fast and requires less memory than Wyman and OP3. So it's by far the most, you can see this here, by most the efficient model. However, unfortunately, some training runs converge to suboptimal minima for TBA. So it's actually hard to train. OP3 is also sensitive to the hyperparameters and interestingly diverges in almost all our runs. This means the results that we reported on the previous slides are results from the last iteration, which is actually the best result before the model diverges. This indicates that unsupervised object representation learning is really a hard optimization problem at its core as well, given the little supervision. To conclude, we studied the strengths and weaknesses of three unsupervised object-centric video representation learning methods, TBA, which trains fast, scales well to multiple objects, and is most robust to out-of-distribution changes of the objects. However, its overall performance is limited, and surprisingly, it struggles with occlusion, despite its built-in depth reasoning. It's further unable to handle dynamic backgrounds and objects of different sizes. OP3, in contrast, emerges as one of the most powerful models in our comparison, but suffers from long and very unstable training that often diverges. However, it handles occlusions and models object interactions comparably well. Its strong reliance on prior segmentation leads to superior tracking performance. Wyman shows good performance on all datasets, but lacks explicit occlusion reasoning. Training is more stable than both OP3 and TBA. We never observed divergence or instabilities, but it takes longer, a little bit longer than TBA. Wyman emerged therefore as the most robust model on average. In general, we conclude the following insights. None of the models shine in all respects, suggesting that future work should focus on combining the transformer-based efficiency of TBA with the stable training of Wyman and the occlusion interaction handling of OP3. Key open challenges for scaling these models to natural videos include their computational inefficiency, complex training dynamics, as well as overdependence on simple appearance cues like color. One critical question to ask now is, well, can we model the performance, improve the performance model, for instance, by adding some annotating data, right? It's not unreasonable to assume that some annotations are available. So how much can the performance be improved? And there's no systematic study on that. However, we are interested, of course, in the most unsupervised approach, and we are interested in particular in scaling these methods to more photorealistic scenes. And that's another question that we ask. How can we actually scale these models to more photorealistic scenes? We don't have a good answer to this yet. So one particular scenario that we might consider is a scenario like the Kitty dataset. And in the last few minutes, I think I still have a few minutes, I want to briefly present a dataset that we have actually developed already for the last 3 or 4 years, but it's only coming out now. As you know, the last 10% often take 90% of the time. So we had to fix a lot of things until we could actually release it, and we'll release it this summer. This is basically a successor of the Kitty dataset with new data and new annotations. In contrast to the Kitty dataset, it has semantic annotations, both in 3D and in 2D, for all points in the dataset. Here you can see some of the sequences of the dataset that have been annotated. In contrast to the Kitty dataset, it not only features front-facing stereo camera, but also 360-degree fisheye cameras, which might be quite valuable for video analysis in terms of providing a full viewpoint of the scene. This is why the dataset is called Kitty 360. In addition to the Velodyne laser scanner, it also features an additional SICK push-broom laser scanner that provides a better coverage of buildings, for instance, compared to the Velodyne, which has a very narrow field of view. And it has the original IMU GPS localization system from the Kitty dataset. We have recorded 80 kilometers of driving with that vehicle, the Kitty vehicle. This is already data from 2015, actually, which we are just releasing now. And no, actually, it's data from 2030. So it's data that recorded like 2 or 3 years after the original Kitty dataset. And it has 4 times 83,000 frames, so 1 for each of these camera modalities. One interesting feature of it is also that now, in contrast to Kitty, all frames are accurately geo-localized using a global bundle adjustment, such that you can actually use OpenStreetMap information as a course prior for navigation or as a course prior for video analysis tasks like segmentation. It also has semantic labels everywhere where the definition is consistent with cityscapes. It has 19 classes for evaluation, and we can do cross dataset evaluation now. And furthermore, each instance is labeled in 3D, which means that all the instance IDs are consistent across all frames, in contrast to the cityscapes dataset. Here are some examples of the dataset. You can see the free reconstruction on the left. Some of the bounding boxes, we do have actually more. We should visualize them as well for the road and for the sidewalk and for the driveways, etc. And then here's the inferred semantics. We have an approach similar to this earlier paper that we published at CVPR2020, which does joint reasoning in 3D and 2D space to infer the most accurate labels in 2D and 3D, both on the semantic and instance level. And we have then also, through this approach, the coarse, rough semantic annotations in the image domain, which you can see here. We have the instance labels, and we have a confidence on how confident we are for each of these labels. As you can see, they are less confident at some of the boundaries. And of course, we have all the free bounding box information. So we'll hope that this is really becoming a valuable data set for the community to investigate novel video representation tasks. Yeah, there's a little video, but I thought I think I have not shared my audio. Let me quickly stop my screen sharing and reshare again. Let me see. No. Now, okay. So I want to quickly show you this little video. I hope it plays well. Which is like a cinematic trailer that we've created for this data set.
Okay.
I realized I didn't have my mic on. I hope that didn't happen for the entire time.
No, it was just final seconds.
This is the end. I just wanted to thank you for your attention.
Thank you for your really nice and great presentation. So actually, I have some questions, and I see there are lots of questions. I try to somehow summarize the questions. Anyway, so one of my questions is that how does your models, all of them, handle the cases that you have similar instances of the same objects in the scene? So based on the figures I was seeing, always the objects were different. They were coming from different classes inside each.
Yeah.
So what if we have?
I think for some of the data sets we had objects from the same class so we had investigated that. I can't recall by heart what exactly that property was, but the methods in general, the methods use, of course, like location features and appearance features and geometry features, right? They all build internal representation of these features. All of the models have different ways to do it, and probably these different strategies should be combined. Some of them have better dynamic models than others, so it's really a diverse set of models, but all of them build these internal representations. So if their models are not of the same color, or if they are not at the same location, then the model still has a relatively easy time to distinguish them. So that's possible. Of course, if you have the same object in this simple scenario where there's not even texture that overlap each other, then there's no way to for the model that it segments this correctly. Then occlusion is always a big problem for these methods we observe.
I think one of the reasons that the occlusion is a huge problem for your work is that you have 2D figure shape objects.
Yes.
And so when there is an occlusion in the 2D world, then I think it's really hard to.
Yeah, well, I think we played with, I think the next step will be to extend these models to even longer scenes, right? So not only these 10 frame like scenes where we have then the chance that an object which, I mean, there's a good possibility for these models to learn about occlusions, because some of them have, like an ideal model would basically utilize this layered representation that it can utilize in order to put these different objects at different layers. And it would do that because it would find, it's all bottleneck models, right? It would find the most compact representations by representing the scene with the smallest number of slots. That means if you have the same object that goes into an occlusion but appears again, you still need to represent the appearance and the shape of that object only once, right? That's one of the inductive biases that these methods are using. And so this would be the most compact representation. Now, because this is all a complicated optimization process and there's so little supervision, it's not always happening. That's the case, right? And so, for instance, also what's very challenging for the nonlinear data set, if an object goes into an occlusion, but then in a nonlinear trajectory moves out of it, then of course it's very hard, because then the only cues that are left are maybe the color or the shape, right? And you have no motion cues anymore.
Yeah.
Yeah.
And another question regarding the TBA method. You said that you're using these spatial transformations, and you said you're just using scale and translate. So isn't it a bottleneck, or is it because of the data set you're using, or your model couldn't handle the other type of transformations? Because definitely a scale and translate will not work in real world scenarios, or even the scenarios you have simple shapes, but more real world type motions. And
yeah, first of all, I mean, this is not our model, right? We're doing a survey of different models. It's not our work. We're just like providing this analysis basically, and we have this extension, this Weimann extension. Like I think, yeah. The problem is that it's difficult to scale these models to the real world. I think for this type of for many simple tracking scenes, just the translation and the scale would be sufficient. But then if the shape changes adaptively, right, then you would need to at least track the shape changes. Like you could imagine that in the autoencoder, the latent representation changes, and then the decoder decodes another shape, right? So that would handle some of the transformations. You don't need to explicitly model, let's say, not necessarily explicitly model perspective effects like affine or perspective effects in order to handle like slight perspective deviations, right? So they can slight perspective deviations, for instance, often handled by affine or by like similarity transformations, and that is yeah. So I think that the answer to this is these models are really in their baby shoes, and we all like to see them grow up. Yeah, so that's, I mean, of course you can add these parameters. It's already hard to train the models like that.
Yeah, definitely. And other question is that have you tried this, for example, the performance of the models for how do they handle the dynamics of the scene. For example, in videos, I'm not talking about the real world videos with real world shapes, just the simple shapes. But for example, we have different velocities of the objects, and objects move in different directions. But anyway, one of the most important is the different velocities of the objects. And so I saw in some of these methods, they are just focusing on the next frame, and from the next frame, they go to the next frame. But if the velocity of the object is too high and the frame rate is too low, then definitely the object would not appear in the next frame. Have they tried to answer such questions in the simple data sets, or is it?
If the object moves out of the frame, and then you cannot track it. No, that's clear.
Yeah, but yeah, that's the question. Why they just focus on the next frame?
No, wait, maybe that's a misunderstanding a little bit. So all of these are not online models, right? So all of these models are trained in a batch fashion, and also evaluated in a batch fashion, right? So it's not like making them online is yet another complexity to the problem. You can imagine them as hidden Markov models, right? So there is a hidden Markov chain on a latent space that basically considers all of the, like ideally, the model develops an internal representation of motion, and in particular, this model, the sophisticated dynamic model with the interaction, we see that it works actually quite well in that regard. So ideally, it develops this representation, and so this representation in latent space tracks the objects then. So this is it can definitely do that, yeah, and it can track through. It can potentially track through occlusions. It's just very little supervision to learn this.
Okay, and let's go through some of the questions from the YouTube chat. There are people asking about how do you decide on how many objects to create. Actually, one of them has asked in a real video, so we are not working on real video, but
yeah, well, I think we went only up to, in our experiments, up to 5-6 objects, because these methods really can't handle more. And also remember, these methods train like for days, right, on 32 by 32 or 64 by 64 images, right? So there's not that many objects that you can fit in these small images. So yeah, so that's basically a limitation of the current resolution that these methods can process. And we went up to reasonable numbers and tested for 1, 2, 3, 4, 5. Yeah, that's just how far these models are currently working. Yeah, there's a lot to be done.
And Fatma has asked, why are you not explicitly? Can you hear me?
I want to just say hi because Fatma was a former PhD student.
Okay. Yeah. Fatma has asked, why are you not explicitly reasoning about depth for occlusions rather than only relative depths?
Well, yeah, I think, these models would work probably quite well if you would have the depth as an input modality, but these are assuming only images, and then inferring them to be on a discrete set of layers, and there's just 2 or 3 layers, right? Is easier than inferring an absolute depth, but we haven't tried it, and that's basically how the model architecture was defined, and so we were just using that architecture. It's definitely very interesting to look at these, yeah, and I assume Fatma has probably better models.
Hi back. Okay, we're out of time.
Yep.
Thank you so much for your nice presentation, and yeah,
Thanks for having me.
have a nice evening.
Yeah, you too. And looking forward to some other talks. I have a break now.
Yeah, there we go. Okay, then bye. So our next speaker is Juergen Gall. Okay, I'm going to make him the co-host. So he's online. I'm just waiting to see if he can hear us. Okay. Okay, just let's see what's happened to you. Okay. Okay, I'm going to. So there is a problem with Juergen microphone. Let me unmute him.
Okay, so audio works. Now let's see if the sharing works.
Yeah, we can hear you.
Okay, great. So let's check with the sharing. Okay, so do you see my slides?
Yeah, we can see the slides, yeah, and hear you well.
Okay, so before I start with my introduction talk, I also want to make the opportunity, as the speaker before, to also introduce a data set. So this data set, it's called Holistic Video Understanding, which is also the title of the tutorial what we actually have today. And I want, before I talk about the introduction lecture on temporal action segmentation, I want to also briefly introduce the data set. So this HVU data set is also, it's a very large scale. So we have like 500,000 of frames of video clips. And the essential property is that we have different kind of labels. So if you think this is like a video clip, it's not only the action. So if you're like, the action would be like a jet skiing. So we have not only actions, we also define what are the objects, like a person and boat, and also like what is like the scene. So in this case, the video clip has the label like C and channel, but we also have additional parameters like the attributes annotated. In this case, this can be like the day, or can be also different kind of colors like blue, and also like event, which are a little bit different to actions. So for instance, like this is more kind of an entertainment event, and some of kind of concepts, which are a little bit not directly like attributes, which is some kind of labels what you would give to a video, like this video is an example of fun and the people might have joy. So overall, we have 3,000 different kind of classes among this kind of the 6 high-level categories. And overall, we created like nearly 8 million annotations. So to give a little bit idea regarding the data set, so again, so why do we need actually additional data sets? We have seen there has been a huge progress in the field of action recognition. And this large-scale data set have, and in the same time, also improved models. We got better 3D CNNs, and that had a big impact on the community. So there has been also like another data set where also additional annotations are available. This is the egocentric EP Kitchen data set, which in the current version has around 300 different object categories and around 150 different actions. There is also another data set, which is also very related to our data set because it also has additional annotations of the scene. So there's something what you can see here, object annotations and action annotations. The problem is, however, so far as I understand, due to legal rights, it's not possible to make this data set public available. So that means there's a problem that this data set cannot be used for research. With our new data set, which is already available, here we not only make the data available, but we also have like again an improvement on the number of classes. If you just think about the sheer size of the annotation. So we have nearly 250 different categories of scenes, 1,600 categories of different objects. Then similar to the previous size of the data, a little bit more activities, actions. Additional, we have 70 events, around 100 attributes, and then the additional class of concepts. To see a little bit the distribution of the annotations among the classes, so we just count how often a video clip gets a label, which can also have multiple labels, for instance, for objects and so on, how many annotations we have. We see also like a different distribution, but for all of the categories, we have a reasonable size. I mean, obviously, dominant one is like we have objects, because objects occur most frequent in videos, but we also have a large number if we look at the annotated actions, but also like from the attributes concept and also the scene labels. So we think this kind of the data set will be very useful if you want to do kind of a better understanding, which goes beyond just recognizing actions. If you want to get a better understanding of the content of the video data. And I think also other interesting experiments you can do with the data set, for instance, like transferring learning. So how can you actually learn something from the video data, or what we've seen in the previous talk, also unsupervised learning is also an interesting application what I can use with this data set. So just a little bit more regarding the statistics. So what you see a little bit here on the right, so this is the different colors for the different, let's move it right. So for the different kind of the high level categories. So at the end, we have overall 3,000, more than 3 million annotations of different labels for objects. And here this 1.5, nearly 1.5 million for different kind of actions. So obviously these labels are distributed among the classes. So we have this 1,600 around action classes. So at the end, if we compute the average samples, what we have for a single class for the object category, we have in average 2,000 instances. So for other categories like the attributes, here we have 5,000. So this is really a large scale holistic data set for getting better models for understanding. So, and interesting is also like, do we have all the categories labeled for all the video sequences? Because sometimes it doesn't make sense to, the scene is not really clear, but if you just look at the videos where we have at least one label regarding from the action category, one label regarding attributes, at least one label for concept, event, object, and scene, then we see like over 16% of the videos have all the classes. And if you now look also at the rest, technically for all of them, we have in most cases 3 different kind of labels. There are only very few video sequences where we have only labels of 2 or less categories. So the data is already available. It's actually in 2 forms. We have a large data set and a mini data set, which the mini data set was already previously available. And if you want to use it, feel free to use then also on the link and start downloading the data set. I also have to mention that generating such kind of data for the annotation is a lot of work. And I think the most of the work has been done by Ali from KU Leuven, Moslem, who is currently also like hosting this kind of the tutorial, and Vivek from Karlsruhe Institute of Technology. So this I just wanted to mention regarding the data set. I think if there are also questions regarding the data set, you can also directly ask Moslem, and I think he will be very happy to answer your question. So now I want to actually talk about the tutorial stuff, giving more kind of an introduction. And I already changed a little bit the title. So usually at the beginning it was called from fully supervised learning until unsupervised learning. I now reduced it a little bit to the lack of time to just go to weekly supervised learning. So the purpose of this tutorial is giving just kind of a basic background and give a little bit of intuition what kind of the things work and why we need actually temporal action segmentation. So obviously what we have seen before, I mean, we have a lot of data sets for action recognition, and this HVU data set extended by adding additional annotation, what at the moment we do not have. But also kind of a side additional remark, there's the website called actionrecognition.net. So if we actually want to know a little bit what are kind of the current state of the art for some of the action recognition data sets, you can simply look it up. But I also have to say you have to be a little bit careful, because at the end, the results are based on a submission by the authors. It doesn't mean that the results what you see on the website, that they're complete. But at least this gives you some kind of a first way to see a little bit what is roughly the current state of the art for different action recognition data sets. But in this tutorial, I will actually focus on continuous data streams and not on single video clips. So there is actually like 2 tasks which seem to be very similar, but actually there are some difference. And one is the action segmentation, and the other task is action detection. So for action detection, we have data sets, for instance, like ActivityNet is an example, also like tumors is an example, where the goal is actually you want to actually find the starting on the end of a single or multiple activities. But some of the property is also like that in either the sequence are relatively short, or you have large region which simply like are not labeled because they're considered as background and unimportant. In action segmentation, the task is a little bit more fine-grained. So in this case, actually, you want to do a labeling of each of the frames where you exactly want to know the annotation. So the data sets are also different. So for action segmentation, the data sets are more fine-grained annotated, and you have each of the action are detailed annotated. And the focus is more to have a very good frame race and predictions. So if you want to have some kind of equivalence for the image domain, so action detection is a little bit closer to object detection, where the goal is actually you want to figure out where certain objects are. You have also large region which you actually are not really interested in. And also the similarity measure, what you do is also like the standard intersection of a union measurement. So the action segmentation, this is actually more closer to semantic segmentation, where you want a prediction for each pixel. In this case, you don't make a prediction for each pixel, but you make a prediction for each of the frames. So all of those tasks are very important and highly interesting. Due to the lack of time, I will only be able to talk about the action segmentation task. So first, why do we need such kind of action segmentation? Is it not enough to have like the action detection part? There are actually like a wide range of applications where you really want to have a detailed protocol of the activities, what, for instance, a person is doing. So this is, for instance, like in health is like a typical example, but they are also the same if you make study. So for instance, like if you have a vaccination regarding a virus, you can also want to make like a test. Does it actually change the behavior, for instance, of the mice? And this means like you need a very detailed protocol, because a change of the behavior can simply mean that the pattern or the time what the mice actually spends for eating can change. But there's also some other industrial application where you want to, for instance, optimize the workflow in logistics or in manufacturing, or you simply want to measure like the time what each of the workers need. And the same is also like in wet lab environments, where you also need specific detailed protocols in order for reproducibility. So now we can also give like an overview of some of data sets. So I will not describe the data sets in detail, but I provide here some of links, and some of the data sets I will also mention during the presentation. So there's the breakfast data set and the 50 salads data set. So both are more in the kitchen environment. Then there's the von Georgia Tech is an egocentric data set. And there's also the more recent is the coin data set. So the coin data set, however, also contains a little bit larger fraction of background. So let's start. How can we build a first model for temporal action segmentation? So this is the task as described before. So I have what you see is here, this is a black bar. So this black bar simply shows like where's the current frame. I actually want to do my prediction. So for each frame, what is actually the label of my activity? And I want to be as accurate as the prediction what I have in my ground truth. So to build the first baseline, we will actually not use a neural network. So we actually will start to use a baseline using techniques what we had before neural networks. And we see a little bit how well they perform compared to the current state of the art. So the simplest way how to build a model for temporal action segmentation is to use a hidden Markov model. So a hidden Markov model is relatively straightforward. That means we estimate for each of the frames what are my states, which are simple like the labels of my current activity. And this is for the first frame, the second frame, and so on. And this is for my entire video sequence. And what I have is my observations. So this can be any kind of features what I extract from a video signal. So do the graphical model, the joint probability of my features and my state, which obviously I don't know, but I want to recover. This is exactly given by the probabilities of my likelihoods. So simple like measure given my estimate of my current state. So what likely is the observation of my features and the transition probabilities between neighboring frames. So if you're not familiar with hidden Markov model, you get a very easy introduction by the book by Simon Prince, where one of the chapter is actually dedicated to hidden Markov models. So we actually know how to do the optimization. If we want to do inference, we have our observations, and actually what we want to do is we want to actually maximize the probability, or if we take minus the log, we want to minimize minus the log of the joint probability. So the good news is, because we have products and everything becomes very simple, which means like we have unitary terms and binary terms. And since it's just like a chain, there's no loop, we can actually easily solve the inference problem by dynamic programming very efficiently. So we also need some kind of features, and what I mentioned before. So we start without neural networks. So the first features, we use the good dense trajectories with Fisher vectors encodings. So this kind of the features, we simply extract and use it together with our hidden Markov model. So we then train a hidden Markov model for each action class. So what we actually do is like, so we look for all my training sequences where we have a segment, which for instance, in this case has been labeled by spoon powder. So we take all this kind of the segments, we can bring them together, and we train in a single hidden Markov model for each action class. So for each hidden Markov model has its own states. S1, we always have a starting state, and then we can have multiple states in between and an ending state. And during training, we learn the transition probabilities. If I'm state S1, do I stay in my state S1, or do I move to the next state? So when I have trained all my hidden Markov models, now I can then actually do the inference. So what I have, I take my improved dense trajectories features. As it's quite common, I actually use them to learn a Gaussian mixture model, which is quite common for hidden Markov models. And now I can do inference after I have also trained my transition probabilities by simply using dynamic programming. So that means like when we actually get a solution in each of my hidden Markov model, I have to go through all the states. So this is my state S1, this is my state S2, this is my state S3. And now I have to really talk about how can I actually get a transition from one hidden Markov model to the next one. And this is actually straightforward. So if we don't know anything else, we can simply say, if I'm in an end state of a hidden Markov model, I can continue with any starting state of another hidden Markov model, which is not the same. So for instance, I can continue with the blue or with the red hidden Markov model. If we have additional information, we can also use a grammar. And a grammar, so here we also define it by a starting symbol for the sequence and an end symbol for the sequence. So the grammar symbol defines what kind of ordering is allowed. So for instance, if I have poor coffee, I'm allowed to continue with the hidden Markov model for ace spoon sugar, poor milk, or poor sugar. But I'm not allowed, because there's not directly connection, to directly continue with steer coffee. So this is some kind of an example what you can use as a grammar. And the good news is this grammar in the hidden Markov model, it does not change anything how you do inference. You simply apply dynamic programming. So this gives us the baseline. So here we simply pick the breakfast data set, which is roughly 65 hours. So very small compared to the current HVU data set. But remember, this is really a dense annotation where each frame is annotated. So obviously now we expect that a hidden Markov model and a Gaussian mixture model, this is just like a baseline. Let's see how we can get better if we now continue with neural networks. And in particular, we will start with recurrent neural networks. So in principle, let's go a little back. In principle, what we now do, we replace the Gaussian mixture model by a recurrent neural network, but we still combine it with a hidden Markov model because this still helps to have a modeling of the different activities and also allows to still use some high-level information, for instance, if we know something like a grammar. So for recurrent neural networks, we don't do any specific. We simply use a standard RNN with a gated recurrent unit. So this is just like a default gated recurrent unit. However, we have to consider a hidden Markov model is a generative model. A recurrent neural network, how it's trained, is in a discriminative way, which means for each of my frames, I want to actually predict the correct probability of my class. So we only have to do a small transformation, and it turns out this is actually good enough. So the only thing what we have to do is like we take our prediction from the RNN, and then we simply normalize it by the probability for each of the classes. So this also gives us some balancing. And then we actually use this kind of the probabilities and use this as an input for our hidden Markov model. It turns actually out that this kind of a transformation works actually quite well with hidden Markov models. So just for completeness, if I want to look it up, so gated recurrent units, it's technically very similar to LSTMs. They simply are a little bit more simple and they don't simply use not additional memory cell. But if you want to read more, please have a look at the reference which are given at the bottom of the slide. So let's look how much they improve. They actually improve as expected. So at the end, what we go here, we go from 56 to 60, a little bit more than 60% in accuracy. It's maybe a little bit less than expected, but at least there's a clear improvement. Also remark, so this the first number is from the paper from 2017, and then the new number, which is here, this is like an extension what we did for a journal submission. So this is like if you want to know the last results for this hidden Markov model with the RNN, I recommend to look it up, the journal instead of the conference paper. So recurrent neural networks give some improvement, but it's actually not that impressive. And recurrent neural networks are maybe not the nicest way always to train. Let's have a look at different kind of networks. And the different types of networks are temporal convolution networks. So in the context of action segmentation or action detection, in this work by Lea et al., this actually has been proposed, and it uses encoder-decoder structure. So the story is again, so we start with some kind of features. So we, for instance, we can still use improved dense retractors or other features. And then at top, at the output, we want to do the prediction of the labeling for each single frame. So do the encoder structure means like we now have temporal convolutions, which is more or less the same like one-dimensional convolutions. And we also have pooling layers because the information of the entire sequence is then mapped to a low-dimensional space, which is more compact and represents the entire sequence. But then again, we also have to go back to the original resolution, and then we use this kind of the decoder, and this decoder uses deconvolution and upsampling until we are back from the original resolution of my input sequence. So unfortunately, the temporal convolution networks at the beginning were not working as well as expected. So just to a little bit make it clear, this number here is not from the original paper. This is simply taken from the paper by Ding and Xu. But these numbers are more or less consistent with the numbers reported on other datasets. So this actually shows that the temporal convolution network seems to actually perform worse than the RNN and actually also perform worse than a simple hidden Markov model with a Gaussian mixture model. So in the work von Lea, they also looked at different types of temporal convolution networks, which actually uses delayed convolutions. So this has been also used, for instance, like for synthesizing audio signals. And you can also use the same if you want to do actually labeling each of the frames in a video sequence. So in this case, you have the delayed convolutions, which are also commonly used, for instance, for image segmentation, where at the starting point, you have the convolutions just like with taking neighboring pixels, neighboring frames. And if you now a little bit move to the next layer, though this frame takes now the input of the same frame, and now we have kind of a gap between the two green pixels. That means my prediction of this kind of the green pixel here depends then on the 4 frames. And in this case, actually, there was also like the causal convolution, because we have a time sequence. You see it that whatever I predict for this frame, I only take information which is actually before the current frame. In this case, no information is taken which actually comes after the frame. But it was also evaluated the impact, and there's actually not that a big difference between causal and acausal convolutions. So the dilated temporal convolution, however, even performed worse as the encoder-decoder structure. But nevertheless, it's like the temporal convolution networks have many big advantages compared to RNNs. For instance, it's much easier to train and they are much faster. So therefore, this was actually the reason why we also looked into it. But in the work by Leo et al., there was also additional measurement introduced, which was actually done by a previous work of the same authors. And this is so-called the edit distance. Because when I have, let's say, a segmentation, so let's say I have my segments, let's say this is my ground truth, and I just make a wrong prediction of a single frame, this will not change my frame-wise accuracy because only one frame has changed. However, let's say if this is my label A, this is label B, then I maybe have D. This single frame corresponds to the label frame F, and then again I have D. This actually makes a big difference because if I now look at the sequence, my ground truth might be A, B, and D, but now the prediction what I get is A, B, B, D, F, and D. And you can now actually use and compare the ground truth string and the string what it gets symbolized by the sequence of the action labels what we have, and you simply use a standard edit distance. That means like you simply count how many, when you have like 2 strings, how many changes you have to do to convert one string into another string. And you have some operation like you can insert a character, you can delete a character, or you substitute some characters. So I'm not describing like the full norm because at the end, this is also normalized. So it's like the normalized edit distance, and the reported one is 1 minus the normalized edit distance, which means if the value is high, that means it's actually better. And we also see that in both kind of the distances, actually the encoder-decoder structure is better. And the reason why actually this edit distance has been used, we see it also later, is the edit distance is sensitive to any kind of over-segmentation errors, while the frame-wise accuracy is quite, it doesn't matter if we have just like small changes or wrong labels of the frames, even if completely divides a long segment into many smaller ones. So therefore, we actually went back to look at dilated convolutions and temporal convolution networks. So we also started with the dilated convolutions. So we have, again, we start the first layer. Here we have the acausal version, which means like the frame here also takes the frame, one frame in the future into account for the prediction. And we also go for the next layer. Again, here we simply increase the gaps between the input. But the nice thing of them dilated convolutions, I can have a very large receptive field without not increasing the size of my convolution kernels. So the detailed building blocks are actually a dilated convolution, rectifier linear unit, a 1x1 convolution, and I have here the additional skip connection. So it actually turns out if you do it in this way, as it was observed in previous work, it will not work as well. So we had to do some kind of changes to really make this temporal convolution networks work. And one of the changes was actually to use some kind of staging. So if we just use a single stage where we have the loss at the end, we see later the results will be not good, which is similar or consistent with what has been reported in previous work. However, if we have here at this last layer, we have the prediction of the class probabilities, and we now feed it into the next stage where we again start with the dilated convolution where they are very small and then the gaps are getting larger. here and so on. Then at the end, we get a huge improvement, but we see a little bit later. And now after each stage, again, we use a loss function to also avoid kind of vanishing gradients. So there is, however, another issue. What I mentioned is the over-segmentation problem. So hidden Markov model, we don't have a problem because we have to transfer different states. So we don't get a result not so often where it's just like a single frame. However, if we have an RNN or if we have a temporal convolution network and we simply use the standard class entropy per frame, then we can have some over-segmentation. What we also see here, so the gray segment is actually split up into 4 segments, 2 gray segments and 2 red segments. And this actually, depending on the application, this may be something what you don't want to have, in partly if you want to generate an automatic protocol afterwards. So to address this over-segmentation problem, we also introduced an additional loss term, which is actually straightforward to add. So what we do is like we look at the probabilities, what we get between neighboring frames. And then we simply compute the difference of the log probabilities between the previous frame and the current frame. And then we simply sum it up and take the squared value. So we also make a cap because at the end it's clear quadratic functions are not very good. And the thing is like we still want to allow a transition between activities if there's a real change. And this is usually if we have a change in the segment, the probabilities change a lot. If there's just like small changes in the probability, it means often that we still have the same action class. And on the right here, you see it's simple like an illustration or visualization of this additional loss term. So to put all the loss function together, we combine the standard classification cross entropy loss with this additional term, which actually minimize or actually penalize only during training to have too much changes of the probabilities between neighboring frames. So this is not a regularizer or smoothness term, which will be then used for inference. So it's only for training. And we have the loss for each S denotes the different stage what we have in our network. So how does it change it? So let's have a look at the situation where we had a problem, and this actually nicely reduced some of the problems. Not all, we still have a few over segmentation, but some of the things are fixed. So if there's kind of an issue that we get this kind of additional wrong labels, this is not affected. So the additional loss just reduces the effect of over segmentation. And what I mentioned before, over-segmentation is not really reflected by the frame-wise accuracy. So there is some improvement, but it's actually not that much. But if you look at the edit distance, here you see a clear difference. And this is also the reason why looking only at the frame-wise accuracy is misleading. So one should also look at least at 2 different measurements, one measurement which also takes into account the over-segmentation error. So what is the benefit of having multiple stages? So the first, what I mentioned before, if you use a single stage, the edit distance or this kind of accuracy based on the estimate distance, it's actually very low. So this is actually not really a good result. However, we see when we now add more stages, so effect on the frame-wise accuracy is not that much, but if you look at the edit distance, we get huge improvement. So if we have 3 stages, we are 64 and so on. And also like the frame-wise accuracy also improves a little bit. Obviously, this comparison are not fair because for each stage, I simply also increase the amount of parameters. Therefore, you should always check if you add more parameters, do you get the gain because of the structure or do you get the gain because of additional parameters? And this is exactly what we check in this experiments. So instead of using multiple stages, we simply add more layers with dilated convolution to a single stage architecture. So this is like the standard stages, they have a thing around 10 layers. But if you also combine with all the additional parameters, if you have like 48 layers, this corresponds from the parameters roughly to or very similar to exactly a setting where we have, does not work here, where we exactly have 4 stages. And you see it like that's a big difference in accuracy. So this actually shows and actually supports the previous results. If you just use delayed convolution for the temporal domain, they don't really work so very well. But in this case, this staging of the network, this gives the huge boost in performance. So now if you compare the results, this again, I use for illustration just a breakfast data set. Here, if you compare the results from the hidden Markov model combined with the RNN, and now the temporal convolution neural network, now we have a huge gain in performance. And remember also like this kind of the results. So if you would use a single stage, the results will be also worse compared to an RNN. So the experiments so far have been done. I think here was a little bit different features, but in most cases, the improved denser attractors have been used. So obviously you can say why you use improved denser attractors. Why not take any kind of 3D convolution neural network, which has been pre-trained, for instance, on kinetics. And this is exactly done here. So here we take the I3D, so using simple the network to extract the features, pre-trained on kinetics. And this just gives a little bit improvement, which is actually not surprising, because technically if you're, cannot really remove it. So it works. It's not really surprising because the data sets, what we get here, because the data sets, if you look from the data what we have in kinetics and the data set what we have in breakfast, which is simple like some kitchen scenarios which were recorded by different students, it's a big difference in the content and in the type of the audio of the video data. But we'll come to the feature discussion back a little bit later. So this shows some results. So this is a video from the Georgia Tech egocentric data set. So the person are doing just like random stuff. So there's not really anything meaningful, but you see it also like the difference between the prediction, what you get with the temporal convolution network, and the ground truth. So there's still a few minor errors. So for instance, if you look a little bit here, there's kind of a slightly wrong prediction. Also like here at the beginning was like a slight error, but overall it's actually very accurate. So nevertheless, this kind of the temporal convolution network, giving now having a starting point where we actually were able to make them work, now we can do very easy, straightforward improvements. And one of the improvements, what we also did is like looking a little bit again back to the delayed convolutions. So when we look at the first layers, we use we actually just take the neighboring frames. So the first layers, they have no context, which in principle is fine because in the image domain, it's also very common. So you start with some kind of convolutions, and there you also have at the beginning a very small spatial receptive field. But we were a little bit wondering what is happening if I give my network also some kind of context information directly from the beginning. So that means like instead of starting with a convolution where I take just the neighboring frames, what about if we also start in addition by giving a delayed convolution where there are large gaps? And this actually, we actually combine them because we let simple like the network decide which types of convolution it actually prefers for the task. And therefore what we do is like we use the so-called dual delayed convolution layer where we actually have two types of convolutions where L, the big L, though this is actually corresponds to the overall number of layers what we have at a single stage, and the small L here, this is technically just the current layer. So that technically means that the one we start at the beginning with just like the neighbor frames, and the other one here we have a large one. So here I actually have crossed a little bit here. So the right one is starting with like the neighboring frames, and the left one is actually starting with taking like a very large receptive field. So in the next layer here, this will increase, and here we actually decrease it. Oops, it's drawing like here. And it actually turns out that this dual delayed convolution layer gives a huge improvement for the first stage, but it doesn't improve for later stages. This is a little bit expected because at the end, the later stages anyway have already access to more information and have a larger receptive field. However, we found actually out that adding this kind of dual delated even to the refinement stage, it even decreases. So we assume this actually starts to have some overfitting problems. So if we now a little bit look at the results, so this actually looked like just a small improvement, but at the end, if you want to look it up, for the other data sets, the improvement are actually much larger. And you can also do some additional sharing of the parameters that actually the number of parameters can be even like smaller than in the previous temporal convolution network. So if we now compare two sequences, so this is from the 50 salads data set. At the bottom, we have the ground truth. We see that some kind of the mistakes are actually corrected by the improved version. And this is like one of the examples where symbol like the network get a little bit confused between salt and pepper. But most of these results, we get a very good accurate result. So another thing which is also a little bit corrected is exactly like the length of the red activity. Okay, so I will then directly continue because at the end I also want to talk a little bit about a weakly supervised setting. But in principle, it's like based on this kind of temporal convolution network, it's now relatively straightforward to do some kind of changes to the architecture and improve the results further. So far, the training was based on fully supervised learning. So this is obviously like very expensive if you want to actually acquire such kind of the data during my training time. And this is also the reason why for action segmentation, the amount of hours is usually a little bit less compared to other data sets, which are just like sparsely annotated. And therefore, you can also do and try to learn the models without fully supervision, but only with weak supervision. That means instead of having a label, a label for each of the frames, what we have here, we only have the information of the transcript, which tells us the order of the action that are in my training video. In this case, A, C, F, and so on, but I don't know when they start and how long they are. So to do the weakly supervised learning, we actually go back in this case for the approach with the hidden Markov model and the RNN. We will see next why hidden Markov models are very convenient in the weakly supervised setting. So to do the learning, so far we assume we had a labeling. And in this case, we don't have a labeling. So what we actually do is like we have here 3 training video sequence, for example, and each of the training video sequence, we now start to do initial labeling. So the first training video sequence has the transcript of the 4 activities. Since we don't know when they start and end, we simply say, well, we label the first quarter by the first activity, the second quarter by the second activity, and so on. And this is the same we do for the second and actually all training videos. This is just a starting point. So now we can actually train the RNN and the hidden Markov model as in the fully supervised case. And then after we have done the training, we now can try to readjust the boundaries. So technically here in this case, the boundaries should change. But since we know the transcript, the order of the action, this is not allowed to change. And this is the point where hidden Markov models become very convenient. Because in a hidden Markov model, or if you remember the grammar, I can a little bit tell the system, well, because this is my action transcript, my hidden Markov model for action 1 has to actually be followed by the hidden Markov model of action 2, and then by the hidden Markov model of action 3. And this is a very simple way how we can actually directly enforce that the prediction directly follows the transcript or the annotation what we have in our training videos. So this needs a few iterations, but not many. So we start with like a linear segmentation of each of our training videos. We also then define the states of each hidden Markov model. So we simply divide the average length of each segment by a fixed number or a fixed size. We then train the RNN and the hidden Markov model. We do this kind of then again, this decoding using the transcript, which actually what you see here, it changed the boundary. What also helps is to adjust the number of states per hidden Markov model. So for instance, some states get very small, and it's not very useful. They have a state which only consists of a single frame, and some of the states get very large, so we actually split it into multiple states. And this can be continued until a few iterations. Usually it's done until 4 or 5 iterations. So now we can a little bit compare what do we get compared to fully supervised learning. So again, that's the last time, though this were the number of the CVPR paper, and this is more or less the accuracy what we have from the extension, what we have in the PAMI publication. But you see, there's still a large gap, but I want to actually a bit focus on different aspects. So the first thing is like the training so far is offline. So at the end, if you get like new training data, we have to train it again on the entire data set. And we see a little bit later that actually but partly this approach is very sensitive to the initiation. So to fix this kind of the problem, we actually use incremental learning. So this actually has the advantage that I actually can process a batch of sequence and don't need to process the entire training data. But the principal idea is actually relatively straightforward. So given any kind of a training video, I don't use at this point any transcript. I simply do the prediction of each of the class probabilities per frame. So now comes the questions like, if I would have the additional annotation of my transcript, how would it change the prediction? And that means, again, we simply use the transcript to do dynamic programming to resolve the best solution given the predicted probabilities and the transcript. So if this does not change my prediction by my network, I don't have to do anything because all information what I have from my labeled data has been already taken into account. If, however, there's a discrepancy, then it's straightforward, we have a loss, and then we use standard backpropagation to update the parameters. So the nice thing of this formulation is you can use it for fully supervised learning or weakly supervised learning, straightforward. So this gives a high flexibility. So let's have a look, how does it actually change the results? And we see it actually like this gives a boost on performance, but we see there's still a gap between fully supervised learning and the weakly supervised learning using transcripts. So I'm already nearly at the end. Just give me a few minutes because I want to actually have, because showing a little bit of video with some results, I want to also point out some kind of issues which are not really mentioned in some publications. But here you see a little bit of difference. The first approach where we start with like an initiation compared to the incremental learning is like the lengths of the segments are different. And we see it actually that short sequence are longer than expected. For instance, like the red estimated is longer than the ground truth, while large segment like the green one is actually shorter than the label. Because at the end, due to the initiation, and we use this uniform initiation, there is a bias towards the uniform length of the activity. If we do this incremental learning, we actually adapt faster and we have less problems, but we still get stuck in a local optimum. So there's something what I actually want to mention, and this kind of evaluation is used in the context of the weakly supervised learning. So the reason is actually we also get some kind of requests also from other groups. And they also said it's like technically, well, if I run your public available source code, I don't get not exactly the same numbers. And the reason is actually like, which is not surprising, partly weakly supervised learning, what I mentioned before, they are sensitive to the initiation. So what we actually did is like, so this is our work, which actually was the neural network with Turpy, but we also used some other approaches, which also use the same task, and the source code is publicly available. So here, this is the numbers which are reported in the publication. And this is actually like the numbers what we get by running 5 runs on the same hardware, which also means like the way and the same of the source code, because sometimes operation also sometimes change depending on the current version of CUDA or whatever library is used. So what we observed, there is actually also like a big gap between the max and the minimum value. And this actually also means that technically for the weakly supervised learning to have a fair comparison, I think it's very important to compute the average over multiple runs and also compute the standard deviation. Another issue which we also observed, and this is actually, we don't have a full explanation for it. So the weekly wise supervised learning, we use the improved dense rejectors. For the fully supervised learning, I already mentioned before, if we take the temporal convolution neural network and we take pre-trained features, for instance, like I3D, pre-trained on kinetics, we got some kind of improvement, not much, which is expected because there's not much similarity. However, in both cases, we get a drop in accuracy. So for the CDFL, it's actually less problematic, but we also wanted to look a little bit closer. And it actually turns a little bit out, well, one of the difference is the dimensionality. So let's look what is happening if we reduce the dimensionality to have the same dimensionality than the improved dense retractive features. However, this improves the accuracy, but if we actually look a little bit closer, we actually see that there's still kind of a gap. It's a little bit better for CDFL compared to into the neural network with Turby, but there's still kind of a gap. To be honest, we don't really know exactly why it is the case, but just like if you also observe the surprised information, this just for the tutorial, we provide some kind of an archive version. It's just like a few pages. So if you want to get a little bit more details regarding it, feel free to read it. So it's not a paper, it's just like 2-3 pages where we actually summarize this experiments with some results where we actually don't have the full explanation why this is the case. So I'm now nearly at the end. I just want to mention, but I don't have so much time left. I just want to mention there's also possibilities to use weaker supervision. So instead of using transcript, you can also say you simply have the action in the video. So here you don't have the order is unknown. So this makes it much harder. And you don't know for each of the action how often it occurs. So for instance, like here we know the action A occurs twice, and here the action occurs only once. So if you want to get a little bit more details regarding this paper, feel free to ask Mosan. I think he's very happy to answer all questions what you might have. So I just want to more or less summarize the difference of the different supervision to make a little bit clear that there's still large gaps. So if we have the full supervision, taking like the temporal convolution network, here we're around this 67% on here, just for example, one data set. If you use transcript, here's 43%. There are, however, also approaches which actually get higher approaches. So for instance, CDFL gives better results, but we have seen that CDFL also has some issues. And if we have even weaker supervision, we get actually surprising, not too bad, but there's still a gap where we get only 30% accuracy. So just for completeness, we will also provide the slides. If you want to have access some source code, here's just like for a summary links of some of the approaches. So for the SCT, the source code I think is not yet available, but will be also available in the next week. So this is already for me, and maybe there are some questions.
Okay, thanks Juergen for his nice talk regarding the action segmentation and also covering an introduction for the HVU dataset. So we are somehow running out of the time. Let me check if we have any questions regarding the action segmentation. So there is no question regarding the action segmentation. And there are some questions regarding the dataset paper, dataset. So since we are somehow running out of time, the questions regarding the dataset, we have the archive version of the paper publicly available on archive, and we are also going to update the paper, adding more information. These questions are covered. And if you have more questions regarding the dataset, feel free to just write me an email or ask on our Twitter account or our GitHub. And also maybe if we find free time during the tutorial, we will cover the other questions. Thank you, Juergen, again for your nice presentation, and yeah, have a nice evening, and bye.
Bye.
Okay, our next speaker is Cees Snoek. So he's going to talk about knowledge supervised video understanding. And I think we, yes, we have him here. Let's me, okay. So, yeah, we have your video and.
Hello, can you hear me clearly?
Yeah, we can hear you.
Great. Well, thanks for having me. As you can see, the evening has started in Amsterdam. Not sure what time zone you guys are, but we'll try to entertain you for the coming hour. I also changed my title a little bit, but I promise you that the content is the same. So let's see. Let's first highlight some accomplishments in video understanding. So I think we have all seen results like this. So fabulous results on classification of actions in trimmed video clips. So what you see here is the most likely action on top, and then the second most likely action. So from the confidence, you can tell that the neural network is pretty confident. Now this all seems very simple, and how come a machine cannot do this? But when I started 20 years ago doing video, this was really this was considered a miracle. Here is another picture with video with progress. So this is tracking an object in video. And what you see here is three modern trackers, or maybe already a little bit outdated. But as you can observe, as the camera viewpoint changes, the tracker is still able to track the object, even when the object disappears completely. So Yoda is gone here. And he reappears, and the tracker can find the object of interest. Mistake, but this, I mean, this is quite remarkable. Here's another example from a CVPR paper from one of my students. Apologies for the low-res video, but here what we are doing, we are trying to segment the pixels that belong to the sentence that is given above. So here we are looking for a woman in a purple dress who is running. Now, it's not a perfect segmentation, but it's quite reasonable. And the beauty of this approach is that if you change the sentence, like all of a sudden you're looking in the same video for a great dog running on a leash during a dog show, it can also segment that object. It might seem easy, but it's not so easy after all, because there are many dogs also in the background. So it really had learned to localize the dog that is running on a leash. Now, how have we reached so far? So the state of the art can do pretty good video understanding, as long as there are huge amounts of supervision, right? So all these examples I showed, they really depend on large amounts of examples. And we are slowly moving into this direction as a community by adding huge data sets. And this is a great contribution. So I'm very excited about the holistic data set as well. But at some point, there's a barrier. And I would like to show you this video understanding paradox. So here you see an example video showing a real problem from Amsterdam. And it's not only in Amsterdam, because this video is actually from New York. And what you see here is an individual that is walking around with a crowbar. He sees a nice bike, breaks up the lock, and takes the bike away. Now, this is a very detailed, specific description of what's going on in this video. And if you would like to learn this by labeling examples, it's actually pretty hard. So the point of the person who's stealing the bike is that he doesn't want to be caught on camera, right? So you won't find an awful lot of videos on the internet or on whatever archive that shows people stealing bikes. So it will be very hard to build an action recognizer for this particular activity. Not to mention when you're also interested in localizing the bike thief, or even having pixel precise labeling for the bike thief. So the paradox is that as understanding becomes more and more specific, it is unrealistic to assume that ample examples to learn from will be commonly available. So in the end, if we want to reach a complete video understanding, whatever that may be, we won't reach it by simply labeling data. That is a dead end. And well, one can argue that the mission of video understanding should be to really move to the bottom right corner of this diagram, where we have complete understanding with as limited supervision as possible. Now, this is a holy grail, and we are no way near, luckily, so that leaves a lot of work to do for us. But what I would like to discuss the coming 45 or 50 minutes or so is a topic that I've called knowledge transfer, and it is approximately positioned over here. So the idea is that if you reduce information from the supervision, you have to replace it with some other source of information to make up for the loss in supervision. And now this insight is not new. This is well known. There's also an interesting debate in artificial intelligence between Gary Marcus and Joshua Bengio. Basically, the divide between the symbolic and the sub-symbolic approaches in artificial intelligence. On the one hand, we have the logical approach, which is explainable, but maybe not as effective. And on the other hand, we have the deep neural network machine learning approach, which is very effective, explainable, and maybe also less suited in compositional problems, causality, and higher level reasoning, or the simple, or basically the divide between fast and slow systems. So knowledge transfer is not new. Many have studied this in the past, so I will quickly go over some related work. Already more than a decade old is the work on attributes for knowledge transfer. So basically the idea here is that you, rather than labeling an image with a category, you can also label a category with its attributes, right? And the idea is that then with a restricted set of attributes, you can describe multiple objects. So here in the example, black and white applies to both a zebra and a panda. The downside of attributes is that you still have to label the attributes and the individual videos, and you also need to map the attributes to a category. So you also have to know that an object has black and white stripes, no tail, and lives on land. An alternative is to learn from labeled resources on the web, and they are typically noisy. Consider, for example, videos on YouTube. They come with tags, they come with title descriptions, and those serve as sort of like a soft label. Now, individually, those labels might be very noisy, but if you accumulate large amounts of them, you can easily filter out the noisy ones from the more reliable ones. And here is an illustration from a paper from a while ago where we tried this. We collected a huge amount of YouTube videos and we learned an embedding that balanced the predictability of a tag, of a label, and we combined it also with its descriptiveness, right? So we wanted to build an embedding where only those labels are included that are predictable and also descriptive. This embedding could easily be converted into a textual representation based on the tag labels. And from this representation, you can then do traditional text-based retrieval using cosine distance. And this gives you zero-shot results. So you don't have to see any training example of the activity you're interested in. At ICV, we introduced object knowledge transfer. So rather than using attributes or tags from the web, we considered object annotations for images, in particular the ImageNet object annotations. And well, it is well known that ImageNet has 1,000 classes in the ImageNet challenge, but in the entire ontology, there are more than 20,000 categories defined and labeled. And here we selected those 15,000 that had more than 100 positive examples. And we trained, I believe it was an AlexNet by the time, with a 15,000 element vector as output. And then we could represent each frame as a vector of 15,000 object classification scores, average that over the entire video. So you get a 15,000 element vector representation per video. And then for each test video, which you could also represent in these 15,000 object scores, you could measure an affinity between objects and actions. And here you could use an embedding like Word2Vec. So you just use the dot product between the two vectors. And based on these affinities, you could then compute what is the most likely action that can be associated to this video given the object representation. And this is also allows for unseen or zero-shot action recognition. At ICV 2017, we extended this to localized objects. So here we could rely on MS Coco. This dataset had 80 object categories, so a little bit less than the ImageNet one. Nonetheless, we were able to get some nice results. So basically, how did it work? We identified the person detector as an actor detector, as a strong prior for an action. Then we also measured relevant objects out of a total of 79 remaining from Coco. And here we could apply the Word2Vec embedding again. So given an action like kicking a ball, the Word2Vec embedding can return the most likely object from the 79 that are in Coco. Excuse me. Then from Coco, you can also learn spatial relations. So here you see some statistics from the bicycle, traffic light, and skateboard. And what this tells you is that compared to a human actor, a bicycle tends to be on the bottom or on the left of the right on the image. A traffic light is typically on top, and a skateboard is typically below a person. So these kind of spatial arrangements, these spatial priors, you can learn from image collections, and they generalize also to video. And taken together, you can build a loss function that combines them into the most likely box for an individual frame. And you can use Viterbi linking to create a tube, so to say. Now, this has also applications in retrieval, where you can ask queries like, find me all those videos where a backpack appears on an actor. And then what you would get back is the object location and the action location as tubes over time. That's old work. In this talk, I would like to focus on some recent work that appeared at CVPR this week. And I would like to discuss 3 types of knowledge transfer. And I've generalized them to physical knowledge transfer, hierarchical knowledge transfer, and temporal knowledge transfer. And I think these are general topics, and we just provide one simple first instantiation of these types of knowledge transfer. So the first one is work with Tom Runia, Kirill Gavrilyuk, and Arnold Smulders. And this is about physical knowledge transfer. And the idea is here that we took a look at computer graphics community. So we might be very happy with our own progress, but also in computer graphics, the progress has been quite astonishing. Let me play this video again. So this is from SIGGRAPH 2018, and you can see from the water, it's really like a realism that is becoming pretty good. Here's another example. So look at the realism of this knitted sweater. And this provided inspiration, this progress provided inspiration for an idea we had, and it was the following. So we started from the question, can we predict latent physical properties for real-world phenomena through simulation? So we want to predict in a given test video whether a real-world phenomena exists without ever having seen a real video example before. Now, this is the grandiose question. So we had to shoot it down for quite a bit. So we started with a case study, and the case study centers around cloth in the wind. So here, what we want to achieve is, you see here a video of a flag, a cloth in the wind at our local science park in Amsterdam. And given the video, we want to predict properties, intrinsic properties from the flag, like its stiffness or the weight of the fabric area, and extrinsic parameters, like the wind speed. So judging from the video and the behavior of the flag, we want to estimate the wind speed during the day. So that is the goal. And we learned this week that there's actually, we were not the only one who was interested in the physics of cloth, because there was concurrent work by Abdullah Haroun Rashid et al. Who looked into the friction coefficient of cloth. So that's worthwhile to mention. So the key idea that we had. So if you look, let me get my pointer. During training, we compute a physical similarity embedding by creating a huge amount of simulations of the phenomenon of interest. In this case, flags in the wind or hanging cloth. So from this, this embedding measures how similar two physical simulations are. The more similar, the closer they are together. And then what we do at inference time, we have a real world video observation for which we also compute its location in the embedding. And then we seek to find in this embedding a simulated video that is as close as possible to this real world simulation. And because the simulation is generated with parameters related to the parameters we are interested in, once we have found this simulation that is closest to the real world video, we also know the intrinsic and extrinsic properties we are interested in. So how do we go about? Where does the knowledge come from? So as it happens, there exist physical models of cloth. And actually there has been quite a lot of work in the computer graphics community on this topic. So reliable models are available. And these are all based on a mass spring model. And people have looked at this for quite a while. And the simulation parameters that you need to generate flags or hanging cloth are well known and are available. So here you see them summarized in a table. So 15 parameters are sufficient to capture the bending stiffness. For the fabric area weight, we took the most common material that we found in stores where you could buy flags, and we took the corresponding weight of the material. And for the wind velocity, we compared between 0 and 10 meters per second. So from this physical model of cloth, we can enter it into your favorite simulation engine. So we used ArcSim. What it will do, based on the simulation parameters, it will create 3D meshes. And here you see some 3D cloth meshes as example. Then the render engine will actually make it look more realistic. So we use Blender. Blender has as input some parameters related to the camera, the texture that you want to have on the flag, scene geometry, lighting conditions, and so on. And it will output a simulated video clip, for example, the one over here. Here you see some simulated flags based on these rendering parameters. Now, you can still see that they are not real flags, but you can also see that they start to look realistic. And indeed, here you see an increase in bending stiffness, and on this axis, you see an increase in the wind speed. The video, so yeah. So this helps these are the rendered videos from which we were going to derive later the real world properties. So now we want to measure an unseen video by using an iterative simulation to real procedure. So let me go over it once more. So we have simulation parameters. So we start from the ones that we have from our external graphics model, physical model, goes into the simulation engine, creates 3D meshes. Then the rendering engine creates simulated video clips. We use a neural network to project the simulated video clip into a physical similarity embedding. We do the same for the real video clip. We measure the distance, and then we do some parameter optimization, here implemented as Bayesian optimization that selects the most likely next pair of parameters to iteratively go through this procedure till eventually the real and the simulated video clip are as close as possible. And then we report the final intrinsic and extrinsic parameters of the simulation, and they should correspond to the real world video. That's the idea. Okay, so let's go a little bit more detailed. So for the flag in the wind, we start by, during training time, we first create a dataset of random flags. Right, and we take some variation in background texture, which we take from the sun data set. We have a total of 12 countries for which we have the flags, and we generate a huge amount of these simulated videos. Then we map these rendered videos to an embedding, and we use nothing special, just like a Siamese network that we train with contrastive loss. So all pretty standard, where a positive pair of simulated flags with the same parameters is compared with random other flag simulations with different parameters. Now, then what is, this is how the embedding function works, so the neural network. So we start from an input video, be it a simulated or a real one. We perform some zeroth order and first order Gaussian filters. So that we look like this. And then we introduce a new spectral decomposition layer. And essentially what it does, it applies the Fourier transform and selects the maximum power and corresponding frequencies. And it does so densely for each spatial location in the image. The output of this is essentially a two-dimensional feature map, which you can then process further with standard convolutional neural networks. So here we opted for ResNet blocks. And then we compare the distance in the embedding space with the squared Euclidean distance. So again, here we have the complete pipeline. So new video comes in, compute the distance. If it's not close enough, we pick new parameters, find a new simulated video that is closest to the real video. If it converges, we return the intrinsic and extrinsic parameters. So the data sets that we used to evaluate here. So we created the simulated flag and cloth videos. So here's the examples of the flags, but we also had the hanging cloth. We recorded ourselves over a period of 10 days, over an hour of video containing flag in the wind with varying wind speed. And we were able to measure the wind speed by putting anemometers in the flag pole. Actually used, we got some help from the local terrain masters who helped us get the meters inside the flag poles. So this was really like in the field science. So this allows us to evaluate how good we could predict the wind measurements. Then for the hanging cloth, we used the data set that was proposed by Baumann et al. At ICV 2013. And for this data set, we don't have the wind measurements because they were not provided, but they did provide the fabric measurements. So we could evaluate the intrinsic properties. Now, in the paper, we have done all kinds of ablations on the spectral decomposition layer and how the embedding, how the flags are positioned, so the simulated flags. But I think this is the main point of the paper, and I think also the main point I want to make in this talk is, so here you see what happens, right? So this is the real world video, and this is the wind speed that corresponds to the video. And as we perform the simulation, the flags change, the parameters of the flag change, right? So this is the distance, this is the wind speed, and this is the weight of the fabric area weight. Now, as you can see here, is that the distance is sort of converging, right? And the wind speed is also converging to 2.35 meters per second. So that's actually, well, still some gap with 2.46 in the ground truth, but if you think of it, not completely, not bad. And the fabric area weight is estimated as 0.11, but we don't have the ground truth. So this is 0.11 kilos per square meter. So the exciting thing here is that the wind speed converges to the true measurement, right? So without ever having seen a real flag video during training, based on simulations only, we can predict to some extent the wind speed. And here's an example for the hanging cloth. So here we have, we don't have the annotation for the wind speed, but we do have the annotation for the fabric area weight. And well, what we see here again is that the physical similarity measure converges, right? So it quickly goes to 0. And also the wind speed is sort of constant around one meter per second. And also the fabric area weight is constant, but it seems a little bit over more heavy than the ground truth. So approximately to the true value. So again, without ever having seen any video of cloth hanging on a rod, we can still predict its intrinsic and extrinsic properties. So I think that these physical models are interesting, and we have only scratched the surface of what is feasible. So that brings me to the next topic, the next source of knowledge that we can transfer, and this is hierarchical knowledge transfer. And this is a paper with Teng Long, Pascal Mattes, Hengtao Chen, and myself that also appeared this week. So here the motivation is as follows. Activities have a compositional nature. So things we want to recognize in video, like activities, can benefit from knowing this compositional nature, from knowing this hierarchy, right? So if you want to classify an action like balance beam, and you recognize a bait and twirling instead, or the other way around, you can treat that as a real mistake, but you can also say, well, if you confuse a bait and twirling with a balance beam, that is less hurtful than confusing bait and twirling with a household activity, right? And maybe because they share the same parent class, that can actually help to find what you're interested in. So rather than using a one-hot encoding where it's either correct or wrong, if you can embed the hierarchy in some way in your representation, it might actually help you. Interestingly, action hierarchies exist. So the activity net is probably the best or most well-known example. It has created this nice hierarchy of activities, not only household activities, but also sport activities, outdoor activities, what have we. And it created a huge data set also with videos and untrimmed and so on. Many people have been using the data set, especially the videos and the annotations, but the action hierarchy has hardly been exploited in the literature. There has been work on embedding hierarchies in visual representations. And they have used either like Euclidean space, simplex space, basically the one-hot softmax encoding, or recently also hyperspheres. So the deep visual semantic embedding, or device, that was proposed quite a while ago in NeurIPS, used this Euclidean space together with Word2Vec to create an embedding between essentially visual and textual information. I'm not aware of any approach that also includes a hierarchy in this embedding. Then there was a paper at CVPR last year by Lee et al., who constructed a 3-layer hierarchy on top of a softmax cross entropy output embedding. So this is a bit rigid and could not completely leverage variation in depth of hierarchy. And then there's the hyperspheres. So there is a paper from my lab on hyperspheres and using Word2Vec to position prototypes nicely in this hypersphere space. And there is also a very nice paper from WEC-V 2019 by Bartz and Densler, who combined hyperspheres with WordNet hierarchies. to do visual semantic search in images. And our proposal is to introduce hyperbolic action embeddings. And hyperbolic embeddings have recently been very popular in the natural language processing community. So the hyperbole is nice because it nicely allows to incorporate hierarchies into the embedding. And as you can basically fill, and the one that is particularly useful or popular is the Poincaré disk. So that's also the one we are using. And it allows to project a hierarchy nicely inside the space. We thought to be the first to bring hyperboles into the vision community, but we learned this week that there are at least two other papers we noticed. One by Xiaoteng Liu et al. On hyperbolic visual embedding learning for zero-shot recognition, and another one by Valentin Krulkov et al. On hyperbolic image embeddings. I guess we are still the only one who tried this for video. So the idea is as follows. So we have an action embedding represented by the hierarchy, and we have a video embedding, and we want to match this in this hyperbolic space. That is the main idea. So how do we go about? So the action embedding simply takes the action hierarchy and then builds a discriminative embedding on this Poincaré disk. And now the trick is, how can we get the video embedding there too? So we have videos, we process them with a standard C3D ResNext model. That creates an Euclidean output space. So we need to use an exponential map to convert it also into hyperbolic space. Now we introduce two losses. So the normal Poincaré disk paper has one loss that basically says that it pulls hypernym and hypernym relations together and pushes the others away. So that is the loss that is visualized here. And what we introduce is a second loss that basically treats each action as a prototype. And then what we try to achieve is to give each prototype, given the constraints of loss one, as much space in the Poincaré disk as possible. So essentially what we're trying to do here is maximize separability. So you get better discriminative ability. Or at least that is the idea. Now, this is what I said before. So this is the video embedding. We project the videos on the same hyperbolic space. So again, because it's Euclidean, we have to do exponential map projection. And then there is one parameter here that is of interest, and that is the C parameter that denotes the curvature of the hyperbolic space. Then we also have to match actions from the hierarchy to the videos. And that's essentially softmax loss, but then with a distance function for hyperbolic distances. And now, once we have this joint embedding of hierarchies and videos, we can queries based on an action name or a video example in this hyperbolic space. And the matching is simply based on the cosine distance. And how you should perceive this, when you search this way in the hyperbolic space, you essentially search in a cone inside the hyperbolic space that captures the hierarchical relationship. So the broader the cone, the more and deeper and broader the hierarchy grows. So this is visualized here. So you have the target cone that is really looking for the action, the direct action of interest. Then you have the sibling cone, essentially closely related actions, and eventually a cousin cone with still related but further away, so to say. Now, we created an experimental setup, and we took existing video datasets like ActivityNet, mini-kinetics, and moments in time. And all we had to do is take the existing hierarchy annotation or add our own hierarchy annotation on top of these datasets. And this is a lightweight effort because it essentially boils down to the number of actions in the hierarchy that you need to, or the number of actions in the dataset that you need to put in a hierarchy. So for ActivityNet, only 200. For mini-kinetics, I'm not even sure, 400, I guess. And for moment in time, we had a total of 340 actions. For ActivityNet, we changed it a little bit. So we updated the hierarchy slightly. We also only kept trimmed videos because we didn't want to go into the untrimmed variations. The mini-kinetics hierarchy, mini-kinetics comes with a hierarchy, but we have expanded it a little bit. It comes with 3 levels. We have expanded the levels. And for moments in time, we have, it's based on VerbNet, it's a subset of WordNet. So we have used that one as the hierarchy. We report for our experiments traditional mean average precision. We also report a sibling mean average precision. So essentially considers an action correct if it's within 2 hops away from the ground truth. And we also have the cousin MAP, which considers 4 hops away from the ground truth. So this is the first task that we can do. So essentially query by video. So on the left, you see the query videos, and on the right, the results. And we have note that we added the class names here only for illustration so that you can see what's going on. So this is the query video. It comes from the marching class. Green means correct, also marching. Lighter green means sibling, and here is the reason for why it is a sibling. So it's not marching, but it's cheerleading. And orange is then a cousin class. For example, for high kick, cheerleading is related, but not so close by. Some ablations. So here we study the effect of the curvature. So if the curvature is 0, we are in Euclidean space, and then results are much worse. Once we add curvature, results increase, not only for the mean average precision, but especially for the sibling and cousin MAP. So the higher the curvature, the more emphasis we place on the hierarchy. So the higher the sibling and cousin MAP. The standard MAP goes down a little bit. And when it's larger than 1, we have some numerical collapse. So curvature is preferred, but too much leads to instability. Then the effect of the hyperbolic space on the dimensionality. So the normal ResNext with softmax has a 200 class output for ActivityNet. If we use 200 prototypes in our hyperbolic results, we get much better results, as you can see here. But interestingly, actually, if we use only 50 prototypes, so a much smaller dimension, we are as good as this result with 200. So we get high scores at few dimensions, and there's no real benefit after 50. Now we use 2 loss functions. So the one from Nickel and Kila on the Poincaré disk that optimizes for the hypernym and hypernym relationships, and the other that tries to emphasize this max margin principle, so that give each prototype as much space as possible. Now, if we only emphasize on the Nickel and Kila loss function, we get good results. If we increase the weight for our discriminative prototype loss function, you can see that the MAP goes up, but at the same time, the sibling and cousin MAP goes down, right? So this is a considerable loss compared to here. So what we find is that balancing both losses gives you the best of both worlds. So if you take lambda is equal weight, you get pretty good numbers, both for MAP and also for the hierarchical MAP measures. This is what happens if you visualize pairwise action similarities using the one hot output and versus our hyperbolic result. So on the left, you can see that it does find some structure and relationship between actions. So here's an area of related actions. But if you provide the hierarchy a priori, you get a much better matching. So it is much better to impose the hierarchy than letting your neural network figure it out from scratch. Some failure cases for query by video. So belly dancing is confused with hula hooping and singing, although it also finds some sibling classes. And this one, playing cricket, the method has a hard time. So what we see here is that in our representation, still the visual similarity is much more important than the hierarchy. So if the visual query is sort of like a bit of an outlier or on the edge of the distribution, it is hard for the hierarchy to compensate. That is something that we have not yet under control. Then we also have the other task, query by an action name. So you ask for air drumming, and this is what you get. You ask for laughing, and you will also get some crying because that's considered related. And passing football not in a game is sufficiently close to passing in a game. Here's some comparative evaluation comparing our output space, so the hyperbolic output space with hyperspheres, simplex, Euclidean. For all the data sets and for all metrics, the hyperbolic embedding is a better choice. And this also holds for unseen actions. So when you train on a set of actions and you test it on an action you have not seen before, it also works much better than This hyperbolic embedding for including hierarchical knowledge in video representation is of interest. That brings me to the third type of knowledge. So this is what we call temporal knowledge transfer. And this is a paper with Mihir Jain, Amir Godrati, that was also presented earlier this week. So we are interested by the properties of time in video. So video has a temporal asymmetry. There is a clear distinction between the forward and the backward arrow of time. So if you look at these video examples, forward and backward have a clear characteristic. The one is much more likely than the other. And then there's also temporal continuity. So future observations are expected to be smooth continuation of past observations. So if you look at those two videos, you will see that one of them is a bit weird because the continuity property is broken, right? Simply by swapping two frames in the billiards scene. So our minds are not used to it, right? So we anticipate a smooth transition. And then we have temporal causality, right? When we observe an event, we observe a chain of causes and then effects. So this is an example video from the something something dataset, pretending to put something into something. And the left one is in ordered fashion and the right one is in shuffled fashion. And that doesn't make much sense. Now, for this paper, we actually looked into the temporal continuity property, where we exploit the property that video is locally smooth. So the key idea is as follows. We want to exploit the temporal discontinuity, basically, in short trimmed videos to guide localization of actions in long, untrimmed videos. So in this paper, we learn only from short trimmed videos like kinetics, and then we can build an action localization model, or to use the terminology of Juergen, action detection, that we apply on datasets like TUMOS and ActivityNet. So this is how it works. We have trimmed videos, we perform our temporal knowledge transfer, and at testing times we can localize actions in long untrimmed videos. So the benefits are that we only need action labels, no boundary information, right? So that is a big annotation advantage. And we also don't need any long videos. We just need short trimmed clips for which an action label needs to be provided. And luckily, our community is very good in collecting huge data sets of trimmed video clips. So again, the holistic video data set is a good resource also for this type of work. So our proposal is what we call action bytes. We're going to find action bytes in short trimmed clips. And what is an action byte is a sequence of an interpretable video segment with meaningful boundaries. And how do we define meaningful? So essentially, we're trying to represent each video frame with a set of latent concepts, about 2,000 of them. And when there is an abrupt change in the representation of these high-level concepts, we mark it as a boundary. And by doing so, we get chunks of video, and we call them action bytes. Now here you see some more examples. So they have some nice properties. They are class agnostic, they are interpretable, and they are also temporally scale invariant. So here you see some action bytes from a baseball video, and we have added these labels ourselves just to give them sort of like an interpretable definition. So this corresponds to getting into the wind-up position. Here we have loading to deliver. Here we have the actual delivery, and this is the length of the delivery, and this video it's longer. And here we have follow through, and then in this video it's longer, and here is shorter. So this is the basic idea. Now, with these action bytes inside a short trimmed video, you essentially have defined a localization problem in a short trimmed video. So but we don't have annotation, so that is what we need to resolve. So this is how it works. So we have a trimmed video dataset, we apply a deep convnet, and then we train our localization model with the aid of video labels. So we have action byte extraction. So here we have a video from the dataset, and this is an action byte, here's another action byte, this is an action byte, and this is an action byte. Then what we do is we cluster all these action bytes, and then we can use the cluster centroids as pseudo labels for each video. So each video is represented by a vector that indicates to what action bytes it belongs. Now, then these pseudo labels from the action bytes, together with the video labels that we have for the trimmed videos, go into the training localization model to do another iteration of action byte extraction. So here it comes a little bit more involved. So we have classification loss and a localization loss that is trained with the pseudo labels. And this is essentially a mechanism that is similar to what you find in weakly supervised action localization on untrimmed videos. And then we also have the action class label that is added on top of that. And we do several iterations until this converges. And then that is the final localization model. And then at test time, we do a similar principle as, for example, the WeTalk paper from weakly supervised on the test set with this training localization model. So that is over here. So if we have a target action class that corresponds to an action class that is also in the test set, then we don't need any action class transfer. If we have action classes in the test set that we have never seen before, then we can use like word-to-vec mappings to find the action that is closest to the new ones. Now, this has a number of nice properties. So action bytes enable a zero-shot temporal action localization by simply avoiding the class overlap between trimmed and untrimmed videos. Action bytes also form good action proposals. So you can simply merge consecutive proposals one by one with some temporal jittering, and then you will get quite good action proposals. And action bytes also enhance weakly supervised localization because they essentially, with the aid of the proposals, they essentially they create more locations of possible actions, as we will show. So we did some ablations, maybe in the interest of time, not the most interesting now. Let me end with some results. So essentially we have defined a new task. So in the paper we call it from moving from what to when. This baseline is also from ourselves, where we don't have the action bytes and we don't have the action, using the action bytes as proposals. And when we add all the bells and whistles that we introduce, we get a good increase over this baseline. And it works for single label actions, but also multi-label. So multi-tumors, we also get some results. Now, nobody can compare this because it's a new task. So we also added it to weakly supervised. And we compared with the then state of the art by the time of submission. And by adding our approach on top of the WTalk work, we get an improvement over the state of the art. And also, to the best of my knowledge, we are the first to report weakly supervised result on multi-tumors. And last but not least, we do zero-shot action detection. Number very modest, but it's a start. So this is now a problem that people can also improve upon. So we can localize an action in a video that we have previously never seen. So that brings me to the end of my talk. So knowledge transfer is key for unseen video understanding. We highlighted physics, ontologies, and time as a potential knowledge source. And the nice thing is that they are naturally embedded in common self-learned representations. And I feel that we have only started to explore the opportunities that this reuse or smart use of knowledge sources provides. And with that encouragement, I would like to thank you for your attention.
Okay, so thank you so much for, so can you hear me?
Yes. Let me
Okay.
stop this here. Yes, I was looking for
My
button,
Zoom is a little bit unstable. I was not sure. Okay, thank you so much for your nice presentation. And,
my pleasure.
Okay, we have one question regarding your talk. Victor has asked that how many levels do you have in the hierarchy? They look shallow. Did you study if perturbations in the hierarchy affect the results significantly?
So no, so we created, let me look it up. So the hierarchy, so we have, so for ActivityNet, for example, we have 3 levels in the hierarchy. Okay. 6 actions at the first level, 38 at the second, and 200 at the third. We did not vary with changing how, no, we did not do any ablations on changing the hierarchies. So we only reported with the 3 fixed hierarchies that are reported in the paper.
Okay, thank you. And let's.
But note that the hierarchies for ActivityNet and moments in time are quite different in terms of how they are distributed.
Right. Okay, so it seems that there is no more question regarding your talk, and we are running out of time.
Okay.
Anyway, thank you so much for staying late tonight until now. And oh, sorry, one other question regarding your talk just received. Victor is again asking, all the instances are in the leaf node or are there videos in the intermediate nodes?
Also in the intermediate nodes. So for ActivityNet, we have 3 levels, for Minikinetics 3 levels, and for moments in time 4 levels.
And another question from Dima. She's asked, so you presented one work in retrieval and one in recognition localization. Where should we put our effort in video understanding, retrieval or classification?
Both. I think we should not focus on one.
So you say both, but fine.
Yeah. I think we should focus on more tasks. We should not constrain it to a limited set of tasks.
Right. Okay. Anyway, we're out of time. Thanks so much again. It's 11 p.m. in Amsterdam now.
No, it's okay. It's Friday evening. It's okay.
Okay. Anyway, thanks so much, and have a nice evening or have a nice night.
Thank you. Thanks for having me. Take care. Bye-bye.
So we are going to our next talk from Raquel or Urtasun regarding holistic understanding for self-driving. This is a pre-recorded talk. I'm going to just start the video and then I will share the screen with you. So.
Hi everyone, my name is Raquel Urtasun and I'm the Chief Scientist at UberETG as well as a professor at the University of Toronto. Today, I will cover holistic understanding for self-driving, both in the context of data that has been captured by the fleet and offloaded to the data center, as well as in the context of real-time reasoning that needs to be done online in the vehicle to drive safely and smoothly to its destinations. Let's start with offline works. Modern self-driving vehicles are equipped with a plethora of sensors, including high-definition cameras, LiDAR, radar, ultrasonics, microphones, etc. Each self-driving vehicle typically captures more than 1 terabyte of data every day. And another question that arises is, what can we do given the fact that fleets of vehicles are typically in the hundreds these days, but will be in the thousands or millions soon into the future? In this part of the talk, I will show how to address the storage issues that arise because of the extreme large scale that we have in self-driving. I will then show how to intelligently access the data to retrieve important video snippets or perform question answering. Finally, I will touch on how to use this amazing data to perform realistic sensor simulation with very little domain gap with the real world. Let's start with the storage. A self-driving car acquires a massive amount of data every day. A single Velodyne sensor produces over 3 billion points an hour, translating to 1 terabyte of data every day. A suite of cameras can acquire over 2 terabytes of data every day as well. This amount of data is really expensive to store. So we need good compression algorithms to reduce the storage requirements. This can include both lossy as well as lossless compression, but today I will mostly talk about lossy compression. The unique aspect of compression in the self-driving setting is the rich multimodality of our sensors. Not only do we have multiple cameras capturing the video, we also have LiDAR strips as well. We build our work on top of entropy coding. A key concept in information theory is that the better we are able to predict the probabilities of a set of symbols by allocating fewer bits for frequent symbols and higher bits for less frequent ones, the better we can compress the distribution. The practical implementation of this idea is in the form of entropy coding, which is a lossless compression process that takes a set of symbols and encodes it into a bit stream. Entropy coding algorithms generally require a probability model to approximate the true distribution of the latent symbols. The better this model can predict the symbols with high probability, the lower the entropy and the smaller the number of bits required. Our compression approaches use neural networks to learn the distribution over images, video, and LiDAR. We first talk about a compression algorithm we designed to compress stereo images. The stereo images are typically present in the frontal cameras of self-driving cars. They are also present in other settings such as drones or 3D movies. Our approach is based on a key insight. The first image should improve the reconstruction of and reduce the bitrate of the second image in the stereo pair. We do this by adding parametric skip functions to do dense disparity warping between the encoded-decoded feature maps of the two images. We also reduce the joint bitrate with a conditional entropy model. Our final approach obtains a 10 to 50% reduction in the joint bitrate compared to single image compression approaches and video compression baselines. While stereo image compression compresses an image pair from two cameras at a single snapshot in time, each camera itself also captures the visual scene at high frequency, producing temporally related image sequences. Hence, we develop an algorithm for compressing monocular video. Unlike stereo image compression, video compression has been extensively explored with deep learning. However, many of these learning-based approaches contain complex architectures or autoregressive dependencies that are not ideal for practical use. In contrast, we develop a very simple entropy-focused video compression algorithm. Unlike previous works and video codecs, we do not do any explicit transformations across time, such as motion compensation or residual coding. Instead, we encode every frame independently with an image compressor and then fit a super lightweight and a non-autoregressive entropy model between frames. We additionally develop an internal learning extension that allows us to do additional encoding fine-tuning during inference. The end result is we achieve similar state-of-the-art performance with prior works while being much faster, and that's much more practical. Another important sensor for self-driving is, of course, the LiDAR, which produces billions of points an hour. We have developed a novel approach for LiDAR compression, which is presented at this year's CVPR. A key challenge of representing LiDAR is the sparsity and non-uniformity of point clouds. Towards this end, we first serialize and quantize the point cloud as an octree. The octree contains intermediate nodes storing the child occupancies, as well as leaf nodes. The nodes contain numerous patterns across ancestors that can be exploited. We designed a novel tree-structure entropy model, parameterized by neural nets, to exploit these patterns and reduce the octree bitrate. Our final approach is really fast and has a 10 to 45% improvement over the state-of-the-art methods, such as Google's Draco. Thus, we show that by deriving dedicated entropy coding algorithms, we can reduce the storage requirements for the sensors significantly beyond the state-of-the-art. We have also developed techniques to compress HD maps or high-definition maps improved by the self-driving car. Unfortunately, I don't have time today to show you all this cool work, so please read our papers if you're interested in map compression. Now that we have discussed efficient storage of our self-driving data, let's move on to the problem of efficiently leveraging this data through data understanding. A powerful log understanding system has many applications within self-driving. First, log search enables the retrieval of thousands of variations of interesting scenarios, useful for stress testing an autonomous system in simulation. Second, automated log tagging enables developers to automatically find common causes of failure by visualizing the tags most correlated with the system's failure. Finally, some approaches to log understanding can additionally provide a learned semantic space for driving scenes that can be used to cluster common scenarios and, more importantly, ensure that current training and evaluation datasets cover the full space of real-world scenarios rather than that overfit into a particular subset. Let's consider some potential approaches for building a log understanding system. The simplest option is to use humans to manually tag the scenes with descriptive annotations that can later be used for log retrieval and analysis. While this approach can be effective on very small datasets, it does not scale to driving datasets containing millions of miles, as it is far too expensive and time-consuming to use. Alternatively, the outputs from the onboard perception system can be reused to heuristically reason about different scenarios based on the detections over time. Unfortunately, this approach requires extensive engineering, often returns noisy results, and cannot generalize to many scenarios which require reasoning beyond more than the detected actors. Finally, we could consider building a natural language Q&A system. While in theory, natural language can express questions related to any attribute in the scene, it also introduces extra complexity and is therefore ill-suited for the real-world setting of log understanding. Motivated by the shortcomings of these approaches, our goal is to build a system which takes only raw sensor data as input, learns a single model for a complex and varied set of questions, yet uses a structured format to avoid the complexity of natural language queries. To achieve these goals, we introduced the novel task of structured question answering for self-driving. Given raw sensor data from a self-driving log, our task is to answer structured questions represented by three components: QX, QR, and QP. QX is the question attribute, which can be any continuous or discrete attribute in the self-driving scene. Examples of these attributes are vehicle actions like turning or map attributes like intersection types. QR is the question's region of interest. As an example, the user can set QR to be the region in front of the SDV, shown in the figure on the right. Finally, QP references to a pooling function, which specifies how values are pooled across the region of interest. Depending on the context of the query, we may either want to sum or pool values across QR. This task introduces many interesting challenges. First, sensory inputs can be noisy, especially at long range, making it difficult to accurately recognize many attributes in the scene. Models must also support a diverse and complex attribute set, which can be both related and unrelated. Additionally, these attributes can be both continuous and discrete. It is also critical that our model can efficiently scale with the number of questions so that our system can be used for real-world log retrieval. Finally, our model should support explicit spatial reasoning about the given region of interest QR. Our approach is carefully designed to overcome these challenges. We learn a single data log embedding from raw sensor data used to answer our queries. Attributes are represented by learn embeddings, allowing similar attributes to learn similar attribute representations. Both embeddings are combined together with a simple element-wise dot product. And our design ensures that our model can be used to efficiently answer many questions, since log embeddings can be pre-computed once and cached for future queries. Finally, our embedding maintains special dimensions so that the question's regions of interest are pooling functions can be applied directly. Let's now showcase some examples of attributes QX we want our system to be able to reason about. First, we consider the active density of the scene. For any spatial region, we can count the number of vehicles or pedestrians. Here we show an example of a particular dense scene with many vehicles and also many pedestrians. These scenes can be particularly interesting for the evaluation of prediction and motion planning models. We also consider the actions performed by any agent within the scene. This includes whether each vehicle is stopped, braking, parked, lane changing, or turning. For pedestrians, we consider actions like walking along the sidewalk and crossing the street. In addition to actions, we consider a diverse set of labor interactions, including stop for, braking for, and yielding to other actors. Along with these discrete attributes, we also consider continuous attributes of the scene, such as each vehicle's current speed. And finally, we consider questions which relate to the map topology. Next, we will describe our model, which can efficiently answer questions related to this diverse set of scene attributes from only raw sensor data and HD maps. Our log embedding network learns a universal spatial embedding for each timestamp. The fully convolutional network takes a series of voxelized data strips and a rasterized HD map and produces an embedding. Importantly, our embedding is spatially aware and maintains the original spatial dimensions downsampled at a rate of R. We use this embedding E to answer all the questions. Now imagine we are given a structured question which encodes, is there a vehicle turning left in front of the SDV? First, we encode the question attribute QX, which in this case corresponds to a predefined left turn attribute. To represent the attribute, we simply look up its corresponding row in a learnable matrix K. Our answering module takes both the universal embedding E and the attribute embedded as input. Using a simple element-wise dot product, we obtain a spatially aware answer map, capital A. Finally, we pull results over the spatial region of interest. In our example, this corresponds to the region in front of the SDV. Results are pulled using a pooling function specified by the question, returning an answer, lowercase a. Our approach is trained end-to-end to minimize supervised query loss across the 15 attributes described earlier. Our model can also be extended to handle compositions through the use of compositional functions. Compositional functions take a set of spatial answer maps from multiple attributes as input and returns a new answer map. Compositions enable our model to naturally handle more complicated questions that relate to multiple attributes. For example, finding scenes with vehicles turning at a three-way intersection. As shown in this example, we also use compositional questions to break down the recognition of vehicle actions and interactions into two simpler subtasks. First, recognizing the existence of a vehicle at a particular location through vehicle density, and two, reasoning about the vehicle action condition of a vehicle being present at that location. Let me now play you a video.
In this visualization, we show the rasterized map given to the model as input. On top of the map, we overlay the ground truth actor bounding boxes, which are not given to the model. First, we show a video with 2 seconds of context surrounding the scene. Our model is trained to answer questions relating to the center of the snippet. Question 1, is there a vehicle turning left in the intersection? Both our model's answer and the ground truth answer are yes. We can see the vehicle our model classifies as turning left in yellow. Question 2, how many pedestrians are in the intersection? To obtain an answer, our model first regresses a density at each spatial location. Here we overlay our pedestrian density estimates at each spatial location. By pooling over the intersection region, we obtain our model's answer. Our model, 17.8, ground truth, 17. Let's move on to another scene. First, we'll show 2 seconds of context. Question 1, is there a vehicle braking for another vehicle behind the self-driving vehicle? Both our model and the ground truth answer yes. Question 2, how many vehicles are in the entire scene? Once again, we overlay our model's density predictions at each location. We sum the values over the entire scene to obtain our answer. Our model, 48.6, ground truth, 45. Let's move on to a final scene. Again, we'll show 2 seconds of context. Question 1. What is the maximum vehicle speed in the scene? We can answer this with a compositional query. First, we compute the vehicle speed at each spatial location. Next, we compute density at each spatial location and use a threshold to mask out regions without vehicles. Finally, we multiply the two answer maps and max pool over the scene to obtain our final answer. Our model, 15.9 meters per second, ground truth, 15.8 meters per second. Next, we'll show a failure case of our model. Question 2, is there a vehicle performing a right lane change anywhere in the scene? Our model answers no, while the ground truth is yes. Let's rewatch the scene to see why this question is difficult for our model. Pay close attention to this actor, as it will perform the missed lane change. Notice that for some frames, the actor is fully occluded. Also notice that at time t equals 0, the vehicle is just at the beginning of changing lanes, making this classification more difficult. If we ask the same question 1 second later, our model correctly answers that the vehicle is changing lanes. Thanks for watching our video.
Next, we test our model in the retrieval setting. For example, in the first row, we show logs that our model retrieves when asked to find examples with more than 10 vehicles around the SDB. In the second row, we show visualizations of retrieved scenes that have a three-way intersection directly in front of the SDB. Finally, in the last row, we show examples of other actors turning in front of the SDB. We compare our approach, which learns a single embedding for all questions, against one where the embedding is separated by question category, each outputted by an independent trained model. Our results show that for small embedding dimensions, our model clearly performs the separated embedding approach for questions related to both continuous and discrete attributes. In fact, we found that the separate model was unable to learn to answer density questions in this limited data setting, resulting in extraordinarily large errors. As we increase the embedding dimension to 16, we continue to see our approach significantly outperforms the separate approach. These results showcase that our approach effectively learns to use the dimensions of the embedding space better than using prior human knowledge to divide embedding memory based on, for example, question categories. Finally, given enough memory, both approaches perform similarly. We can see a slightly higher performance in the separated model, likely due to the fact that it has 4 times more model capacity, and thus this is not necessary for comparison. In a real-world setting, the questions that need to be supported by a self-driving Q&A system will grow as requirements change and new supervised data becomes available. Ideally, models should support continuous learning, in which new questions attributes are trained on top of a learned model. Therefore, we also explore whether our learning embeddings can boost performance in this setting when a new unseen attribute is added with limited supervision. For this experiment, we selected a single attribute, shown on the x-axis, to remove from the first stage of training. Then, we add the held-out attribute with only 10% of the original data, simulating a limited data setting, and continue training. In blue, we show the performance of a baseline model trained only on the held-out attribute. In red, we show the performance of our continuous learning model after training. For additional context, we also compare against a model trained on 100% of the training data, 10x more data than the models in blue and red. Our model always outperforms independently trained baseline, and for some attributes, it has up to 32% relative improvement. For turns, braking, and lane changes, our model performance is actually closer to the performance of a model trained on 100% of the data than the independently trained baseline. Finally, we show a TSNA visualization of the universal embedding space. Each point corresponds to embedding vectors at the spatial locations with vehicles. We color each point with the primary action of or interaction of that vehicle. 3 dominant clusters are apparent: vehicles keeping lane, stop vehicles, and park vehicles. We also see smaller clusters appear for more rare actions such as left turns and right turns. This visualization demonstrates that the embedding captures the high-level semantics of each spatial location. In conclusion, in this work we introduce the new task of structured question answering for self-driving. We propose an approach capable of answering a variety of complex set of questions relating to real-world self-driving scenes. Our approach learns a universal embedding for all questions with a strong generalization properties demonstrated in the continuous learning setting and a semantically meaningful latent space. There are many extended future directions to explore. Future models should explore leveraging information from more sensors of the SDV, including the cameras and radar captured by the vehicle. Models should also explore more complicated architectures to enable better spatial-temporal reasoning. Finally, we are excited by the prospect of learning a set of compositional functions in order to improve the performance of the systems on computational queries. Tons of things to do. Along with compressing the data we collected and mining the data for key events, we can also use larger-scale data to create new data via simulation. As Richard Feynman once said, "What I cannot create, I do not understand." And simulation, in particular sense of simulation, help us better understand different self-driving scenarios and how to evaluate autonomous systems. Before we discuss sensor simulation, let's discuss briefly the different ways we evaluate SDVs and the value sensor simulation provides. The self-driving industry uses a combination of 3 different approaches for evaluating and testing SDVs. First, there is structured testing, which tests the SDV under a set of reproducible scenarios. This is typically done at a test track facility. This test setting is considered high fidelity, since we can evaluate the full autonomy system and hardware of the car in the real world on a particular scenario. We also consider this testing to be reactive, as the SDV perceives the scene and performs a maneuver. The other agents in the real world can respond to its behavior, and the sensor observations are accordingly updated. While effective, structured testing currently has many limitations. It's difficult to test extreme or dangerous situations, such as high-speed avoidance maneuvers. Additionally, larger-scale testing is simply impractical. We can also evaluate the SDV on pre-recorded real-world data. This potentially provides a more realistic setting for urban driving scenarios compared to structured testing. However, this situation is not reactive. The sensory data and other actor behaviors are not updated according to the SDV's actions. It's also still difficult and potentially unethical to collect and test safety-critical cases at scale. The third method is to use simulation. While simulation systems have a domain gap with the real world, simulation has some significant advantages. The agents and the environment in simulation can be reactive. Simulation allows testing any safety-critical scenario easily. And excitingly, simulation has the potential to be scalable. Not only can we perform millions of different evaluation tests, we can also use simulation for training different autonomy algorithms. We now review the self-driving vehicle autonomy system and how we can inject simulation for evaluation. Every fraction of a second, the vehicle senses the environment. The perception system is then responsible for estimating where the objects are in the scene. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning model focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicles will do in the next few seconds. Traditional simulators only simulate bounding boxes or trajectories, enabling only motion planning evaluation. This is the typical approach in industry due to ease of running and relatively low overhead. It makes the assumption that the self-driving stack is modular and just uses active dynamics for traffic simulation. End-to-end closed-loop testing of the full autonomy stack requires going farther than just simulating bounding boxes and trajectories. We need to have a complete simulation system that models the real world accurately. To build such a complete simulation system, we need to estimate the dynamic state of the environment, where we have actors including vehicles, pedestrians, and cyclists, construct the geometry of both the static environment and the dynamic actors, and finally simulate the sensor observations that the SDV might receive on that particular scene. Here we show a LiDAR sensor on one of our vehicles. LiDAR generates a 360-degree 3D geometry point cloud of the scene, along with information about material reflectance, objects through intensity. I will now discuss how typical simulation environments simulate LiDAR through standard graphics, and how we instead use real data to simulate LiDAR. Recall that we have millions of miles captured with these petabytes of data, and this is going to enable us to create simulation at scale through scene understanding. The standard graphics, such as simulation based on game engines like Carla and EarthSim, simulate LiDAR by designing 3D assets by hand, building a virtual world, and then physics rendering the LiDAR. The advantage and disadvantage of graphic-based engine simulation is explicit world and physics modeling from the ground up. This allows for total control of the world and precise definition of all the assets. But unfortunately, it is expensive to create these assets as they are done by hand. It is not scalable to have virtual worlds for the numerous cities we want to test, and the simulated LiDAR is typically unrealistic. Our work at this year's CVPR, called LiDAR-Sim, leverages both graphics and real-world data along with machine learning. LiDAR-Sim builds assets at scale using a fleet of self-driving cars with standard sensors, and then uses physics with machine learning to generate realistic LiDAR simulations at scale of new potential scenes. I will now discuss in more details the different components of LiDAR-Sim. LiDAR-Sim leverages millions of real-world miles collected by our fleet of self-driving cars to help build virtual worlds for autonomous vehicle testing. On the right, you can see the reconstructed background scene of an intersection and a collection of the different dynamic objects created from LiDAR data. Here we show how LiDAR-Sim generates realistic backgrounds. We record real LiDAR data by driving in an area and remove moving objects. We aggregate and align the LiDAR, combine across multiple trajectories, and create a mesh software representation. A similar process is done to generate dynamic objects. We utilize a symmetric prior to get a complete shape of an object. Leveraging real data allows us to inject the diversity of objects seen in the real world into LiDAR-Sim. From left to right, we can see cars with open hood or trunk, bicycles on top of the car, flatbed trucks with construction cones, and trailers with extended cars. Making sure we can detect these rarer objects as vehicles is important, and by leveraging real data, we can simulate more situations that are in the long tail. You often don't see this diversity from other 3D assets or CAD model datasets that are available out there. Once we generate our assets, we can place them in a scene configuration, just like in a video game. We now have scalable and diverse scenes. We then perform realistic sensor simulation with a combination of physics and machine learning. LiDAR generates point clouds by shooting light into the scene and measuring the travel time to determine an object's distance. To mimic this process, we raycast our scene and generate a simulated point cloud. However, raycasting generates more returns than real LiDAR, since the return light does not always meet the detection threshold in the real world. We call this phenomenon ray drop. Ray drop is complicated to simulate for physics alone because we don't know the physical parameters of the real world. Fortunately, using a ray drop network, we leverage real-world data and machine learning to bridge the sim-to-real gap. We convert each LiDAR strip into a spherical image representation, encoding features related to ray drop, such as range values, incident angles, semantics, and pulse intensity values. We then feed these features into the network and predict how likely a ray will be dropped. The labels come from real LiDAR ray drop patterns. We sample the ray drop probability to generate the final point cloud. We now show results. Green boxes indicate vehicle detections from a model trained on real data only. This side-by-side comparison shows that LiDAR-Sim generates realistic point clouds with a small domain gap for downstream perception tasks and autonomy testing. We now compare LiDAR-Sim against Carla, a state-of-the-art sensor simulator. A model trained on Carla data and tested on real data has a large sim-to-real domain gap. But a model trained with LiDAR sim has just a 1% domain gap, significantly outperforming Carla. The small domain gap means LiDAR sim is effective for data augmentation. By combining LiDAR sim data with real LiDAR, we gain a significant performance boost for vehicle detections with both small and large amounts of data. LiDAR sim also allows us to evaluate a perception and motion planning system, maneuvering safety critical scenarios in a closed loop setting. Here we see a simulated scenario where a vehicle turns into the SDV lane, occluded by a bus. The system, trained only on real LiDAR data, is able to process LiDAR sim data and safety brake to avoid collision. With no additional training or domain adaptation, we can directly use LiDAR sim to test an autonomous system end-to-end on millions of different scenario variations, achieving results that match closely with the real world and allowing us to gain new insights and to test the performance of the safety of our self-driving vehicles. But modern autonomous vehicle car platforms are not only equipped with LiDAR, but also equipped with multiple high-resolution cameras, covering different viewpoints, the front view, side view, and rear view. This means we need to also simulate camera images which are consistent across viewpoints and time. Let's review the standard graphics-based camera simulation, as well as the recent progress in using neural networks for camera sensor simulation. Graphics-based camera simulation relies on classic rendering techniques. On one hand, real-time rendering is cheap and efficient, but does not produce photorealistic sensor data. On the other hand, high-fidelity rendering is very expensive and hence not scalable, as it usually takes a few hours to render a single image. Recent neural net rendering formulates the camera sensor simulation as the process of conditional image generation, either through semantic layer-to-image translation, domain adaptation, and image manipulation. However, these single image-based methods cannot be directly applied to create a virtual environment for self-driving cars, as the simulated camera images are usually geometrically inconsistent. Other methods insert 3D vehicles into the scene by encoding and manipulating semantic image representations, or manually specifying vehicles in new locations and rendering them. However, this requires very expensive manual editing and hence is not scalable. In addition, these approaches do not have a 3D scene representation, making them difficult to extend to video or for handling interactions with other actors in the scene. In contrast, I will present now a novel effort towards photorealistic camera simulation by leveraging existing camera sensor data that, as we saw, we have millions of those miles recorded, and the 3D geometry of the scene, and inserting dynamic objects into the scene in a geometrically consistent and physically possible manner. We can then create a great amount of scenarios that potentially capture the diversity in the long-tail distribution of driving data. As an example of this, let's play a game. Which of the objects in the depicted images are fake? Did you guess correctly? What you just saw is GeoSim, a novel approach that leverages graphics-based rendering, real data, and machine learning to simulate camera sensor data from multiple points which are geometrically consistent. GeoSim takes advantage of recorded camera data, LiDAR scripts, and 3D bounding box annotations to aggregate real-world sensor data for dynamic objects encountered in the world. Such data is readily available in modern self-driving datasets. We first used the real data collected to create a large-scale and diverse 3D object bank with precise geometry, high-definition appearance, and accurate 3D poses. To build our assets, we developed a 3D reconstruction network that takes camera and LiDAR sensor input from multiple viewpoints for a given dynamic object and outputs a high-precision 3D shape. Specifically, we process and combine crop LiDAR point clouds and images into a single feature embedding, which we then use to predict deformations to a mean template shape prior. We then perform energy optimization on the predicted shape to make sure it agrees with the input LiDAR images. Note that we don't require any ground truth 3D shape data. Here are some examples of 3D assets with the corresponding images. Know that we can model vehicles of very different shapes as well as sizes. We then place 3D assets onto the high definition map so that they reflect the traffic and 3D layout in a realistic manner. Note that our object placement is not only 3D aware, but is physically plausible and temporally consistent. We leverage an intelligent driver model for simulating the vehicle trajectory over time and making sure it has realistic acceleration and braking, such that the full scenario is coherent. Once we have selected an object from our asset and decided where to place it, we use novel view rendering with 3D occlusion reasoning with respect to all elements in the scene to create the appearance of the novel object in the new camera image. Finally, we generate photorealistic camera simulation using a post-completion image synthesis network that adjusts lighting and resource boundary artifacts. Unlike existing work on neural image synthesis and manipulation, which either requires human interaction, is not realistic, or only models it to the context, our approach is fully automatic, photorealistic, and 3D layout aware. We compare the proposed GeoSim with the state-of-the-art 2D neural rendering methods, as well as a retrieval-based copy-paste baseline. Compared to 2D-aware image generation models, such as Pix2Pix HD or guided editing, GeoSim produces much more realistic augmented images with little to no distortions or aberrations. And compared to a simple copy-paste baseline, we can see the value of GeoSim's 3D-aware placement and occlusion reasoning for creating a reasonable image scene, and the effectiveness of the post-completion network to seamlessly fuse the source and target images. We also measure the perceptual realism of the simulated images using FIT. Our method is capable of producing significantly better quality images than other methods. To further verify the realism of GeoSim, we conduct a human A/B test. We show a pair of images generated from different approaches on the same background real image, one from GeoSim and another from one of the competing algorithms. We then ask the human judge to click the one that they believe is more realistic. From over 20 users and close to 5,000 image pairs, we can see that GeoSim images are preferred more than 94% of the time, and even sometimes 99% of the time compared to some of the baselines. This confirms that there is a significant gap between other baselines and GeoSim that is immediately noticeable. But perceptual quality metrics are not enough. To verify we can use GeoSim for autonomy evaluation, we take perception models trained on real data only and perform inference tasks on image segmentation, 2D object detection, and monocular 3D object detection on the simulated images, and compare the performance with real images. As we can see, qualitatively, a model trained on real data can still segment, detect out the GeoSim added cards, just like other real cards in the scene. We now show how perception algorithms trained on real data perform on images generated from the different simulation baselines. We first show the results when evaluating on real images. The numbers in the parentheses indicate the performance gain loss using different simulators. Here are the results of the different image generation baselines of the different tasks. We want to emphasize here that a higher IP or mean IOU perception metric on simulated data is not necessarily better. Instead, we want the perception metric to as closely match the performance on real data. This difference is reported in the parentheses. The closer the metric on simulated images matches with real, the more likely the perception algorithm considers the simulated image as from the same distribution as real data it was evaluated on. As we see in the table, there is a clear difference between using real images and synthetic images generated by 2D-based neural in-painting methods. In contrast, perception algorithms trained on real data alone will generate consistent results reflecting the correct semantics in both GeoSim and real data. We now show some more examples of GeoSim. Here's an example of a simulated object. Can you tell which one is simulated? Notice that we can simulate objects at different and diverse viewpoints, front or back, far away or close. We can accurately handle occlusion with static background objects, other vehicles, and even pedestrians. Even more explicitly, we can extend our geometry-aware image simulation by composition approach to video simulation. Notice that our simulated images are temporally coherent and that the added objects obey traffic and have reasonable motion. Multiple objects can be added to the scene and interact with each other, for example, performing light changes. Being 3D aware also means we can also do multi-camera simulation that is physically possible. We use GeoSim in the next. We hope GeoSim is the next step in providing realistic camera simulation for autonomy testing. Now that we have covered different approaches to do holistic understanding offline of data captured by driving millions of miles, we turn our attention to real-time reasoning that needs to be done online in the vehicle to drive safely and smoothly to its destination. A very popular approach in academia is to train a neural network for the task of driving. The input to such a system is a set of sensor measurements, for example, LiDAR or images, and the output is the information necessary for the self-driving car to drive, for example, a steering command and acceleration. The advantage of such an approach is that it is very easy to create a prototype with just a few lines of code. Furthermore, the system is trained for the end task, which is the task of driving. However, this paradigm has several key disadvantages. It is difficult to incorporate prior knowledge and thus make this system respect the rules of traffic. It also has no interpretability, which poses a problem for the system validation and safety. An alternative is the traditional software stack, which is composed of a set of modules executed one after another. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene, here depicted with rectangles for vehicles and circles for pedestrians. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then, the motion planning model focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This full process is then repeated every fraction of a second, typically every 100 milliseconds. The advantage of this popular paradigm lies in the fact that we have interpretable intermediate representations, and it's easy to incorporate prior knowledge. However, reaction time is typically large as computation adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for those changes. Furthermore, the different modules are not trained for the end task, and thus improvements in model performance do not translate to better driving. Our vision at UberATG, which is different from any other competitor, has the advantages of both end-to-end and traditional engineering approaches, but without inheriting their respective drawbacks. In particular, we believe in having a single AI system that can automatically adjust itself to any changes, thus increasing significantly developer productivity. As computation is now shared across modules, the resultant reaction time is also much lower. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge, for example, to guarantee that we follow the rules of traffic. And finally, since our approach is trained for the end task, every improvement results in better driving. In the following, I will introduce 3 efforts from our lab that align with this direction. Our first work is the end-to-end interpretable neuromotion planner, published at CVPR 2019. It uses a deep net to produce a learned cost volume and improve the power of the deep network with detection and prediction tasks. Later, we propose the SDNet, Deep Structure Self-Driving Network, which further improves performance and interpretability by outputting a non-parametric multimodal prediction and planning condition on this prediction. The third work investigates how to bypass detection post-processing, which may lose useful information. We propose to perceive, predict, and plan through interpretable semantic representations, where we replace instance predictions with an instance-free semantic occupancy representation and use learn interpretable planning costs over that to produce planning. Now, let me briefly explain the main idea behind each of these works. Here's the model of the end-to-end interpretable neural motion planner. More specifically, we feed LiDAR and HCD maps into a backbone CNN and extract a feature map. From there, our model decodes detection bounding boxes of actors in the scene, as well as the predicted feature motion, as shown on the top right. To conduct planning, the core idea is to generate a cost volume using the convolutional networks. Each channel in this volume represents a feature timestamp, and each pixel in the volume represents the cost of traveling to that location at that timestamp. Then we use a physically valid trajectory sampler to sample a wide variety of trajectories given the current ego pose. These trajectories are guaranteed to follow vehicle dynamic constraints. The cost of a sample trajectory can be obtained by indexing the learned cost volume and the waypoints along that trajectory. The minimum cost trajectory will be our final planning output. Importantly, all computations from raw data to the final trajectory can be done in a few milliseconds. We evaluate our approach in our challenging ATG4D dataset. This dataset contains over 1 million frames from more than 5,000 snippets collected from multiple cities across North America. It provides point clouds from a 64-beam LiDAR sensor and high-definition maps. It contains challenging urban scenes with many actors, making it interesting for interactions and motion planning. Here we show our results. Compared with the state of the art, our model achieves on par or better detection and prediction performance at the time of publication. More importantly, as we can see in the figure, our planning results have a much lower collision and lane violation rate, which indicates safer planning. Here are some interesting qualitative results. In all 4 figures, blue boxes depict detections, red boxes depict the ego car, and the colorful region in the cost is the low cost region predicted by our model, describing what the ego car should drive. On the top left, we show an example of following lane, and on the top right, we show an example where the ego car encounters an intersection. Here, our model shows nice multimodality. The bottom 2 figures show that our model can navigate along the lanes as well as avoid collisions with other cars. Now let me show you a short demo. Our model takes LiDAR and HD maps as input and outputs detections, predictions, as well as motion planning cost volume. We highlight low-cost regions for different timestamps using different colors. Our planned trajectory is shown in red, and ground truth trajectory is shown in blue. As we can see, it follows the lane perfectly. Note that our cost value captures multimodality. In this case, we can either go straight or change lanes. When approaching an intersection, we can either keep lane or turn right. We can also handle blockages. The cost volume shows a preference to lane change in order to avoid collision. And here are 2 examples of super nudging into heavy traffic, which is one of the most difficult maneuvers in self-driving. However, there are still drawbacks. First, planning is not conditioned on the prediction results, which may cause inconsistencies and potentially dangerous planning. Second, the model only predicts a single mode of the future, but the future is actually uncertain. And I'm talking here about the prediction necessary of the motion planning, which as we saw was multimodal. To address these drawbacks, we propose the SDNet, a deep structure self-driving network that jointly raises about perception, forecasting, and motion planning. Specifically, our method has several advantages. First, Computation is shared between models and thus allows for real-time inference. Second, our method explicitly models socially consistent multimodal uncertainties in the future. And finally, our learning-based planner leverages the power of deep learning and takes traffic rules into consideration, as well as in order to guarantee safety. Now let's have a look at how the model works. Given data point clouds and an HTML as input, we have a neural network to produce background features, which will be shared with other models. We first use such features to predict the detection results. Our next step is to predict the future behaviors of all actors, as well as the uncertainties, which are shown as colorful regions in the figure below. Here, different colors mean different future timestamps. This is a non-trivial task, as we expect to predict a multimodal non-parametric distribution which can capture complex situations. More importantly, behaviors of all actors should be socially consistent. For example, they shouldn't collide with each other. To construct such non-parametric distributions, we first sample a set of dense and diverse trajectories for every actor. Then we use a neural network to predict an energy for each trajectory based on the input data. After normalization, this becomes a distribution. Although we can do this for all actors, we can see here that the resulting predictions are not consistent. For example, two distributions may overlap, meaning two cars will collide with each other, which is not realistic. To tackle this, we propose to conduct message passing between all actors and encode their socially consistent interactions within pairwise energies. This gives us multimodal, socially consistent predictions. Finally, our model plans a safe trajectory with a cost minimization procedure, which ensures the produced planning will have minimal expected collision rate and suits the current scenario. Here we first report our prediction performance. We compare our multimodal socially consistent prediction method against several state-of-the-art methods on a number of datasets. We show the results on two public available datasets in particular, Newsins and Prico-Carla. We achieve significantly better prediction error. Our method also achieves a near zero collision rate among predicted trajectories, which corresponds to more realistic human behaviors. Here we show our planning results. Again, we compare against end-to-end imitation learning methods, as well as our previous NMP method. Our DSD approach achieves significantly better performance in terms of collision and in violation rates. This is due to the fact that now our model explicitly considers multiple future possibilities and then plans a safe trajectory that is compliant with the actor's future behavior. Here we show some interesting qualitative results. We visualize the uncertainty through a dense color map. Different colors represent different time steps. This is the uncertainty at 1 second into the future, 2 seconds into the future, and then 3 seconds. As you can see, our algorithm really captures all the uncertain futures for the car in the circle. Here are some more examples. The top left shows that our model is certain about the vehicle that follows a straight line. Simultaneously, it is also certain about a faraway vehicle that is turning. The remaining three figures show some interesting driving behaviors, such as perfectly following a crop lane, turning left, and nudging around a parked car. Here's a short demo of our model. As you can see, our model nicely captures multimodality, especially for vehicles that are approaching an intersection. When a vehicle is driving in a straight line, our model is certain about its direction, but uncertain about its future velocity. Here is an example where we perfectly predict that the leading vehicle is stopping, and we plan a nudging trajectory to avoid collision with the parked car. As this shows, our model can follow the lane perfectly. And that's the nudge. So far, we have discussed two efforts on how to improve interpretability. Both of these works detect surrounding actors first, and then conduct planning based on detection and prediction results. For example, in this case, the ego car will know a coming vehicle is crossing its left turn lane, and thus yield to the car. However, detection requires post-processing, typically NMS. and only reflects an actor if its detection score exceeds a certain threshold. But what if the detection score flickers a bit and then suddenly is below the threshold for this bug? In some cases, this will cause a very severe collision. Therefore, just relying on detection like this is not necessarily safe. To address this, we propose to perceive, predict, and plan through interpretable semantic representations. Rather than performing object detection and then predicting trajectories for each object, this model directly generates semantic feature occupancies. Furthermore, the occupancy forecasts are scene-based and instance-free, and hence do not require thresholding of detection scores or performing any MES post-processing. The planner uses these non-parametric spatiotemporal occupancy maps, along with other interpretable costs, to plan a trajectory that is safe, comfortable, and respects traffic rules. Note that the entire model can be trained end-to-end since all the components are differentiable. Let's dive a bit deeper into the semantic occupancy representation. We consider vehicles, pedestrians, and bikes and as the classes for which we want to predict this occupancy. To make the representation more interpretable, we further subdivide these classes semantically as shown in this hierarchy. For example, for any given pixel in the region of interest, we predict how likely it is occupied by a vehicle on conflicting lanes, parked vehicles, or any other semantic classes. In terms of the inference process, we take data strips and an HD map as input and extract backbone features with a two-stream CNN network. Then a recurrent occupancy update network predicts semantic occupancies into the future. As you can see, there is no post-processing at the actor level. This is beneficial since the computational cost doesn't increase in cluttered scenes and is not a function of the number of actors. Finally, we conduct the planning step. The planner samples a set of trajectories. A cost function is used to evaluate each trajectory, considering different aspects of driving. The best trajectory is then selected for execution. Here we show some examples of our interpretable cost function. For example, the spatiotemporal occupancy maps are used to penalize trajectories that overlap with potentially occupied regions. We use the map data to penalize trajectories that are not close to the line centers or violate boundaries or do not follow the given route. We also take into account the smoothness and comfort of the trajectories in the cost functions and penalize, for example, trajectories that are turning at high speeds. So as you have seen, the trajectory cost function in our planner considers various aspects of driving. The relative importance of these sub-costs are learned jointly with the rest of the pipeline, including detection, including the semantic occupancies. Here are some quantitative results from open-loop experiments. That means that we enroll the predictions and motion plan for 5 seconds into the future without replanning. In other words, in these experiments, the SDV does not get any further observations within the future horizon of 5 seconds. The results show that our proposed model is much safer than the baselines. For example, we get a 40% less collisions than the best baseline through the 5-second future horizon. Also, the generated trajectories of our model are more similar to the driving behavior of humans. In this video, we visualize our interpretable semantic occupancy, as well as our planned trajectory. We unroll our planning into the future as shown with the black solid box, and ground truth is shown with an empty box. We use different colors to indicate different semantics that are predicted by our model. You can see them in the legend. As you can see, our semantic occupancy really captures where the other actors are. And as times go by, the occupancy map changes to provide information of where the other actors will go in the next few seconds. And then our planning can use the interpretable cost to produce a safe and compliant trajectory. Thanks to LiDAR Sim, our state-of-the-art LiDAR sensor simulation that was just presented as an oral at CVPR2020, we can further do closed-loop end-to-end evaluation for the planner. We ran 80 challenging scenarios, each of a duration of 10 seconds, with our closed-loop simulator. Those 80 scenarios are particularly designed to test the safety of our decision-making when facing critical situations, and therefore they are extremely difficult. We collected various planning metrics as shown in the table, and compared our method to a method that detects objects, and then to these trajectories. The results show our end-to-end planner is much safer and generates significantly more comfortable trajectories. In conclusion, in the offline setting, we have seen that to even begin understanding our data, we need to first properly store and compress the large-scale datasets. I show recent state-of-the-art algorithms for compressing sensor data by taking advantage of multiple viewpoints and temporal redundancies and entropy coding. Once we handle the storage, we can then begin log understanding of the previously recorded data by generating useful learned representations for a structured question and answer. With our compressed real data and ability to store meaningful representations for mining relevant logs, we can then perform simulation to generate new sensor data for better understanding and evaluation of the autonomy system. With the offline setting providing support, we can improve our perception and planning algorithms' understanding of the world and perform safer self-driving. Most of the material shown today is new and has not been shown before. Stay tuned for a series of archives revealing all the details of this work that we have shown you today. This is all for me. Thank you very much.
So thanks, Raquel, for her nice presentation. She's online with us, and I don't see any questions on our YouTube chat. So Raquel, if you want to add up something, yeah, you can go on, but just we are a little bit out of time.
Yeah, I think I talk already too much. So I'm just here in case somebody has questions. Otherwise, happy to address, afterward via email or via whatever form makes sense.
So Raquel, I have a simple question here.
Here we
so
are.
I wonder, as automotive industry is expanding, right?
Mm-hmm.
What in automation industry, what you really want is to minimize the cost of every little bit of things. That's what you want to do also. But at the same time, with the boom of computer vision and machine learning, everything, things are becoming much more computationally expensive. How does the automation industry going to incur those costs?
I mean, there is two things here, right? There is the sort of the computation that goes online, and then the computation that you can afford offline. And this is why the talk sort of is split into the two aspects, right? And the amount of data and the kind of things that you can do offline are very, very different than what runs on the the hardware that is in the car. Now, the other thing that is interesting to know is that for self-driving cars, not ADAS, but self-driving cars, what happens is that the model of car ownership is going away. That's not going to exist. Instead, there's going to be fleets of cars that are managed by whatever it is, right? And you're going to contract a service that will pick you up when you want to go to a destination. And under that model, these cars will be driving around 24/7, potentially not even requiring parking, right? And they will be shared. And as a consequence, you can actually have more compute, right? You can have much more expensive hardware on those vehicles. So it's interesting how, when we say traditional, oftentimes we think about, it's the car that I purchased today, right? And it has to be quite, scrappy in terms of, the computation that you can do. But self-driving vehicles really opens the possibility. The economics are very different enough, having very, very sophisticated robots. But I mean, at this point also, it's not necessarily about cutting costs, not at all. It's about finding a solution that is safe. And once you have a solution that is safe and you can prove that it's safe, right, then you can start asking the question into, do the economics work? Do I need to reduce, costs, etc. Okay, and in order to do self-driving, right, where there is, you cannot rely at all on the human driver. There is, machine learning is a must, right? And there is a lot of very, very sophisticated, holistic scene understanding, holistic understanding in general, not just scene, right? That you need to do. And I hope that today, I show a whole bunch of things, right? There is many, many, many more things, obviously, that you have to do, but it's an extremely exciting area, and definitely one that I recommend everybody that, to work on if you are excited about it.
Cool. Oh, thanks. I just was wondering that. Thanks. Yes.
Okay, thank you so much, Raquel, for joining us. And yeah, bye-bye. And
My
yeah,
pleasure. Ciao.
I hope to see you in next event. Ciao. So our next speaker is Christoph Feichtenhofer. Sorry, I hope I pronounced it right.
Hello,
so,
it's okay.
With us, and yeah, we can hear you and we can see you. Just go on.
Perfect. I try to share my screen. Hopefully that works too.
Yeah.
You can see the screen?
Yeah.
Great. Okay, just pulling this out. All right. Great. Trying to deal with this Zoom panels. All right, so hi everyone. I'm Christoph. I'm a research scientist at Facebook AI Research. And in this talk, I will discuss some basic and recent architectures from our lab for efficient video recognition. So this is a course outline of the talk. I will first talk about representation learning, then a lightweight modeling architecture called X3D from CVPR20, then a method to accelerate training of video models called multigrid. Then I will talk a bit about multimodal and self-supervised learning with this audiovisual slow fast work. And then I give a brief outlook. So all the code for the method I present today will be available at this GitHub link, is already available or will be available within the next weeks. This is our PyTorch code base called PySlowFast for video understanding at Facebook or Fair. So for the first part, I talk about slow fast networks. And for this, I will first briefly introduce the task I will talk about in this, or one of the tasks I talk about in this talk. The task is human action classification and detection. And here the goal is to detect all atomic actions that people are performing in the scene. So this is the image shown here is a sample from the AVA dataset where the ground truth actions are shown at the bottom. So these are annotations with this GT prefix of the dataset. For example, the person on the left is standing, carries an object, talks to a person, and also watches a person while doing so. And note that many of these actions are not able to be recognized from a single image. So for example, if the person on the left would talk or the person on the right would sit down, only a method that uses 3D spatiotemporal information could really extract this information. Now, what you see on the top when I play these videos, I hope the video works on the stream. So what you see on the top are predictions of slow fast or the slow fast method that I will describe in the talk. And yeah, the prediction scores are shown, basically softmax output scores of the model. So first, I will talk about how this is typically done, not slow fast, but typically in the field. So in the field, video classification is typically done by using 3D convolutional networks on short clips that we use for training. So the basic idea of these models is to have a spatiotemporal filter bank that spatiotemporally filters the input image, the input clip. And the output of each of these filtering stages, of course, are feature maps or feature tensors. And now, different from image classification, these feature tensors are 4-dimensional. So they have a shape of t times h, w times c, where t is the temporal shape, h the height, w the width, and c the number of feature channels or filters in your filter bank. Now, what is shown here are just 4 sample filters. These filters are from one of our work on visualizing what is learned inside of a ConvNet. So these are actually receptive field responses of filters in a motion convolutional network. But here it's just shown for illustration. So when you go from shallow to deep, these filter receptive fields, of course, they grow in size. both in the spatial and the temporal dimension. I hope it works fine on the video, with the video on the live stream.
Yeah, it's working fine.
Okay, thank you. So yeah, so at the output of the network, a prediction is formed, and usually these models are trained in a supervised manner, just like image classification tasks. You have your cross entropy loss, and that's how it's done. So now a question we could ask is this actually an efficient and effective way of treating the spatial temporal domain? Because the spatial and temporal dimensions are quite different in its nature. So maybe it makes sense to capitalize on that and have different methods that exploit the fact that the spatial and temporal dimensions are different. So slow fast itself is also loosely inspired by neuroscience. And here is a video that I like to show in my talks from an experiment around 50 years ago. And I think the amazing thing is from that video that we can really guess these actions that the person shown by these few dots is performing. And that's quite remarkable. So just motion information actually gives us a very good guess or a very good hint of what actions are performed here. So for the human brain, motion is a very rich source of information. Now, what do we know about the brain? So, and that was also a bit of an inspiration for this work. We know that there are two pathways. So the ventral stream, or the what pathway, this one is responsible for object recognition. And interestingly, this one builds upon P cells or parvo cells. Now, these cells are able to process color information and detailed shapes, but have small receptive fields. But the most important part, or the most interesting part of those, is that firstly, the majority of the cells in our retina, and second, they're quite slow. So they have less myelin. Myelin is a substance that's responsible for how fast information can propagate from one nerve cell body to the next. So it means we can only slowly recognize like that semantic information. And on the other hand, there is the whir pathway or the motion pathway or the dorsal stream. And interestingly, this one responsible for motion recognition and location recognition, it's like building on M cells. And these M cells are a minority of the cells in our retina, but these cells differ from the P cells in the sense that they can only process grayscale information and very coarse information, but they are fast, and that's important and interesting. So they have more of that myelin, and they can react quickly to changes at the input. And there are roughly 20%, so that's also like there are fewer of these. And there are some lateral connections shown here in this plot of the primate visual system between these pathways in the brain. So for the slow fast work, the basic idea is very simple. The basic idea is to have a slow pathway that operates, that is tasked to capture semantic information, and it operates at lower frame rate. And the fast pathway will operate at fast frame rate. So the slow pathway is a spatiotemporal residual network with low frame rate, and therefore it has a low temporal resolution T, shown here in these tensors. So this means it just processes a few frames, and it also does not perform any downsampling in the network hierarchy. So it has this T number of the T number of frames in the feature dimension at every layer. In contrast to this, the fast pathway operates at alpha times higher frame rate. And despite the higher temporal resolution that this pathway has, it's actually made very lightweight. And this is also in relation to this neuroscience motivation by just having around 20% of the computation of the slow pathway by using fewer channels. So this pathway has around 8 times less channels, like the 80-20 ratio maybe from the neuroscience. And also the two pathways are fused with lateral connections between them. So for example, if you would like to detect this hand clapping that is performed by the person on the bottom right, not sure if it's possible to see that on the stream, you really need fast frame rate or high frame rate. But other things you can easily recognize from single image or a very low frame rate. Like, for example, there is a person, or they're holding a glass in their hands, and so on. These kinds of semantic cues you can also extract from a slow frame rate or a low frame rate. So that's the idea. Now, looking a bit more into detail how this architecture is made, or how it looks, is shown here in this table. Trying to get a laser pointer. So what's shown here is a table, is an example instantiation of the slow fast network, and it has a ResNet 50 structure. And what's shown here is the slow pathway. And as said before, the slow pathway is really just a 3D residual network that's applied to a low frame rate video input. What you can see here at the input at the top, slow pathway, then the first stage is a raw clip of a video, of the input video. And then the data layer is actually having a stride of 16, which is the temporal stride, and 1 is the spatial stride, 1 squared. So we subsample the temporal clip by a stride of 16, which means this one has low frame rate. And then the network, if you know a residual network, it's just a ResNet 50. So the rest is just a ResNet 50, only that it has temporal convolutions. And the temporal convolutions come in Res4 and Res5. Temporal convolutions 3 by 1 squared here are in the first filter of a residual block in Res4 and Res5. The reason why we filter so late in the network in time here is because if you have a large stride at the input and your frame rate is low, then you have potentially large motion. And therefore, you want to filter when your receptive field is already large, because otherwise your filter that goes over time, it cannot capture any meaningful correspondence if there is a large motion. For example, if a hand moves fast from right to left, then it will no longer be able to capture that at early layers. So for this network, filtering temporally late makes sense. That was our motivation. Otherwise, it's really just a 2D network. And the fast pathway is the same network, only with 2 differences. One difference is that the temporal stride applied at the input is low. So it's seeing every second frame, stride of 2. So if you have a 64 frame clip, it will see 32 frames. And then the other difference is the channels are, as said before, 8 times fewer. So here you can see the channels of that network, and it has much fewer than a typical residual network, and that makes it very lightweight. Next, shown here is just on the last column now, the activation size. So as you can see here, the spatial size shrinks. This is this number here, 2 to 4 is the input resolution, and then it shrinks like in a normal residual network. And in the temporal size, there is no pooling applied actually. So this full fast and full slow resolution in the time domain is kept throughout the network. Then there is a global average pooling at the end and a fully connected layer that classifies the input clip. And that's it. So in our experiments, the first experiment we want to see is like a training curves for the 2 different models. And we see actually what you see here is the training error vertically and the number of epochs. And in green is a slow fast model, and in blue is a slow only model, like the slow pathway alone. And you can see that the training error is lower in the dotted lines, and also the validation error is lower in the solid lines. So this is like what we want. We want to have a model that just works better, both training and testing, and that's the case for adding the fast pathway. Now, of course, you can think about what about just adding more frames to the slow pathway to make it like the 3D ConvNet shown in the first slide. You can do that, of course. That will be quite expensive because this pathway has a residual network structure, and every frame you add doubles the compute of this model if it doesn't pool in time. So here we show different models. The details are not important, but basically they increase in compute horizontally here. And also the accuracy increases vertically for increasing basically the number of frames in the slow pathway. And now this is what you get if you add the fast pathway. So it shows that for adding this cheap fast pathway, you always get a sizable gain in accuracy. But the other thing that's also important is this is very cheap. So it won't cost you a lot to add the fast pathway, which is because it doesn't have many channels. So what next? I'm maybe skipping some slides to make it for the time. Here is just a comparison to state of the art back then when we released the paper first time. It had a really nice gain on previous works that used 3D confidence with a similar residual network kind of design, like a 5% increase in accuracy. And also it was like the first work that actually works without ImageNet pre-training on highest accuracy. Back when we published it, that's also mostly attributed to the training recipe in the paper. Now I move on to some class level performance plots for the action detection task, where we want to see where does the fast pathway help the most. So when we look here at different classes from the AVA detection dataset, we see that the fast pathway actually helps quite a lot for these highly dynamic actions like dancing, running, jogging, fighting, hitting, hand clapping, and so on. And this makes sense because these things we already saw in this teaser before, you cannot recognize well in a slow frame rate video. So our architecture or our detector for this action detection task is very similar to a faster RCNN detector that's applied to video. The video shows here the qualitative results with the detected boxes in green and ground truth boxes in red. Our action detections are shown on the top with the confidence scores again, and the ground truth labels are on the bottom again. And the video really illustrates how difficult this task is. It's very challenging because you have multiple classes and you need to localize in both space and time. So in comparison to previous work, the slow fast model had a very substantial gain in detection accuracy. For example, we participated last year in this ActivityNet challenge on AVA, and we got a nice gain of 13 MAP from the previous year's winning solution for this task. And what was more pleasing to see is that the top 3 teams all used slow fast networks as a backbone, which shows that it's very general and well adopted by the community. And furthermore, when we look at this year's challenge, I just skimmed through the results, and it seems like slow fast models were backbones for 3 challenge winners or for 3 challenges. The AVA Kinetics challenge, which is a new challenge with a new data set following the AVA challenge from the previous years, the Kinetic 700 challenge winners, and also the HACS challenge, which is a new challenge, used some slow fast models. So this is really underlining that the method is well received by the community. Right, I can show some more qualitative results on the test set of AVA. As you've seen before, it's like there are several cases when the method fails and when it's still not like producing good results. Of course, it's a very challenging task. So for example, in this case here, the person is opening a door, right? And when we go back, here. When you go back here, you see that the detection actually is close and open at the same time. So it's detecting close and open with high probability. The model doesn't really know if it's opening or closing. So that's like one failure case. It cannot do the same thing. You cannot open and close a door at the same time. So yeah, model doesn't know it. And this is like one failure case. And yeah, there are more of these, of course. What we also saw in the curve before is like the model does especially bad when the classes have few training examples. So that's where you also have quite low per class performance. So this is just some insights or some look into qualitative results. Okay, so this is all about the slow fast work. Now I want to go into a different direction and talk about how expensive video actually is, and some works that tackle this. So expensive, I mean, what I show here in this is the training duration actually on ImageNet, which we all know very well, and the kinetics data set. And here you can see that this is not the largest version of kinetics. It's the smallest version actually, the 400 class version. And here you can see the training is around 14 times slower on kinetics. And that's because kinetics is much bigger actually than ImageNet. And if you think about the largest version of kinetics, like kinetics 700, this one has, if you count the number of frames, around 195 million frames. And that's like 160 times more than ImageNet has images. So video data sets are much bigger. And that's why we get larger training time, of course. So, and I will now go first on a model that's more efficient in terms of the floating point operations it requires than previous work. And then I will talk about a method about accelerating the training by using a multi-scale training strategy. So first about X3D, which is an efficient model that I want to highlight or motivate again from 2D way of dealing with the image classification tasks. So for 2D tasks in image classification, it's very common to use 2D filters to filter your input image and create feature tensors of size HWC. Now we already know for video, we do the 3D convolution and we get T times H times WC. Now, if you look into the literature and look for models and also the slow fast is one variant of that, usually you take a residual network or you take an inception network or a VGG network and you extend it with a temporal dimension. And that actually assumes that these HWC dimensions, which are designed for the ImageNet task or the 2D task, are also good for the video case. And that might be not the most efficient way of dealing with video data. You might not want to have your feature tensors HWC of the same size than for an ImageNet case. So this was one motivation, or maybe the main motivation for this work. And the claim in this work is that direct temporal extension is suboptimal for efficient video recognition. And our idea here is called X3D. And this is an architecture that's expanded from a very tiny model that's super small across multiple axes to achieve good computation to accuracy trade-off. And this tiny model is shown on the right. That's called X2D. And since we already looked at these tables before, we're quite, we can understand it, I guess, easier. And what you can see here, the resolution of the input is 112. So it's a very small spatial resolution. The model is actually very small. It has just one frame. So it's a 2D model. And it has very low channel numbers. So 24, 48, 96, and 192. And then the idea of X3D is actually to expand this model across multiple dimensions. And the multiple dimensions we expanded are shown with these different colorized gamma variables here. So like gamma S would be the spatial resolution of the feature tensors. Gamma T is the temporal resolution for the number of frames. Gamma tau is the temporal stride applied to the input or the frame rate. Gamma W are the width of all the layers. Gamma B is the bottleneck width of all the layers in the center of the residual blocks. And also what's important, this is now a 3 by 3 by 3 convolution, which is a spatial temporal convolution with a size of 3 in all 3 dimensions. And this one is a channel-wise convolution in this model. And that's following the MobileNet design of using these channel-wise convolution that are otherwise also called depth-wise separable convolution. Here I call it channel-wise because to not confuse it with the depth. That's also another factor that's considered in this model. So gamma D is the depth of the network. Okay, so we start with a super small model that can be expanded in 6 different axes. Again, with animation now, it's the frame rate, the number of frames the model gets for the input and all feature tensors, the spatial resolution for the input and all feature tensors, the depth of the network, the width of the individual layers, and the bottleneck width. And now, how do we expand this model? So to generate X3D, that is now expanded across the 6 axes. For good computation accuracy trade-off, there are these 6 operations. Each of them you can think about roughly increases one of these gamma parameters. So either you increase the depth, or you increase the width, or you increase the bottleneck width. And the expansion is done in the following way. So the expansion progressively increases the computation by, for example, 2x at a time. And only for each of these 6 axes at one time. And then you train and validate the model. And then you select the axes that achieve the best validation accuracy for the same computation increase, which is 2x. And this process is then repeated to get the final model of a desired computational budget. So summarized again, it's very simple. You have 6 different axes. For each axis, you increase it. You get one model. You increase it in the way that you get double the floating point operations. You get one model for that. You train and validate it. You do this for 6 axes. You take the best one, and that's one step in the algorithm. So it's very simple, a very greedy way of growing this model. Now, turns out what it's doing in experiments is that the expansion starts from this 2D model, the tiny image model with a single frame, and then it first expands the bottleneck width, then the frame rate, then the spatial resolution, then the duration, and finally also the global, then the depth of the model, and finally also the global width of the network. And since we do this progressively, we get different models from extra small to extra large capacity because we exponentially increase the model complexity in each step by doubling it, right? We double the floating point operations in each step, and this is what we get as an output. And what's interestingly from this expansion is only the last step shown here increases the width, the global width of this super small 2D model that we've shown before. So that's interesting. So it does not globally increase the width a lot for this small model. And that's answering the question before, like, do we need this many number of channels from the ImageNet models for the video case, at least for the kinetics task? Seems like we don't need it. We don't need so many channels. All right, skip the next slide. So in terms of results, we compare to previous work. This graph shows the slow-fast models in green and channel-separated networks in pink, and the temporal shift, channel-separated networks in gray, and this temporal shift module in, channel-separated networks in pink and the temporal shift module in gray. And these are some recent works that focus on efficiency from last ICCD. And you see there are different points for the slow-fast model. That's because I vary here the number of clips that I used for testing. Because testing, usually you take several clips from one video and you average the predictions to get the final prediction of a video. So this is varied here. That's why we see a curve for these models, slow-fast. And you can see here the vertical dimension is the accuracy, and the horizontal dimension is the overall floating point operations required for full testing of one video. And now here is the X3D model, which achieves quite sizable lower floating point operations, or has sizable lower floating point operations for achieving the same performance as these models. And here are, again, some tables comparing to the state of the art. And roughly you can say, compared to these channel separated networks, you can get the same performance for 5 times fewer parameters and roughly 5 times fewer floating point operations required. And here I want to note that X3D, as said before, has this advantage of using a channel-wise convolution for the spatial temporal filter, or depth-wise separable convolution. And this is common in mobile networks, but this makes a direct floating point operations and parameter comparison to the slow-fast model not 100% fair, because these depth-wise separable convolutions, they come nearly with very low floating point operation cost and parameter cost. On the other hand, this channel separate networks, they also use this work also uses these depthwise separable convolutions. So this comparison is, I think, a fair one here. The paper has further experiments on charades and AVA where similar observations hold, and also yeah, on these other data sets. Yeah. Okay, so this is on an efficient modeling perspective. Now, the next part of the talk, I want to talk about an efficient training method or an efficient training procedure to get quicker training cycles. Now, for motivation, another peculiarity of video recognition or video models is that we are dealing with large feature tensors again, like TW, T times H times WC. They can be very large. And therefore, we use a lot of GPU memory to train these models. And that means, for example, if you have a ResNet 101 and you have 128 frames at the input, you probably can only fit a batch size of 1 into your GPU. And that means training can be very slow because the GPUs exploit the parallelization across many batches, many examples in a batch. So in this work, the main idea is called multigrid. And this is the main result of the work, where we have a slow fast training curve for different number of epochs in blue here. And this produces a baseline accuracy of 75.6. Now, using the multigrid idea, we can reduce this training duration by roughly 4.5x. So we can train four times faster. And also the final accuracy is roughly the same, or in many cases even better. We think because of some training scale augmentation, extra training scale augmentation we have. Now, how does this method work? It's actually looking at this trade-off. Again, looking at these 4D tensors that we have, and what can we do? We could actually use smaller training resolution, which means smaller spatial resolution and also temporally less frames. And then we would get faster training, but the models would be less accurate because we use smaller resolution. Another thing we could do is get a super accurate model maybe, but use large resolution at the input. A lot of frames and large spatial resolution. That's the other extreme. So in multigrid, we exploit this trade-off in a cyclic training strategy. So what we do is we increase the batch size during training. We start with a small spatial temporal resolution, and then we increase the batch size in a cyclic manner during training and increase the spatial temporal resolution. So the long cycles have exactly this idea. We call them long cycles in the paper because they span like a long subset of your training iterations. And you start, for example, with a 4 times lower temporal resolution and 2 times lower spatial resolution. Then you can afford to have 8 times more samples in your batch. And then you progressively increase your resolution during training. And with this very simple idea, for example, with these 4 stages, you can think that you would be able to fit around you would be able to fit exactly 3.75 times more training examples in one iteration. So you get a theoretic speed up of 3.75 during training. Now you could also think about having so-called short cycles that we have in the paper. And these change in every training iteration, the input resolution. And what we do is we change them only in the spatial dimension for the short cycles. Empirically, we found that works well. And the temporal resolution is not changed for these. Now, if you combine these long and short cycles, you would have something like this for the batch size, right? You can increase the batch size of up to 16x when the resolution is very small. And then you vary through that during training. So recapping again, what are the different cases that we have? We have a baseline that has a fixed training shape in the temporal and spatial dimensions, and also in the batch dimension. Then we have these long cycles that reduce the spatial temporal resolution progressively over training. The short cycles that change the resolution at every iteration, and the combination of the two. Now, if we look at the ablation study, here is the baseline of a slow fast model that is trained for different number of epochs. So 1x is the default. That's the important point here. If you train the model longer, it doesn't get better performance because maybe of overfitting. If you train it shorter, it will perform much worse. So here's the performance, 70% is the accuracy here, and 75 plus is here. Now you could do the first naive case of just using low resolution input in XYT and train this model with just very much lower resolution, and you get much lower performance, of course. Now, if you use this short cycle that changes just the spatial resolution every iteration, you would get 3 times faster training and pretty much the same accuracy, even better accuracy actually, because you have maybe better training jitter. Another way you can do is do the long cycles, which change the temporal and the spatial resolution, and you get a 4 times faster training. And if you combine the two, you get 4.5x faster training, which is the result I highlighted in the beginning. So that's everything actually, and the idea is super simple. It's using multi-scale training, and it will accelerate video model training by a lot. In the paper, we have experiments on different data sets. The kinetics data set I talked about before, which is like the ImageNet of video classification, or then the charades data set, which is a long-term action understanding data set, or more long-term than kinetics, and then the something data set, which is about moving around different objects in different ways, which is different from the human action classification data sets. And in all cases, it seems to work similarly well. Also for different models, for slow, fast, I3D, non-local models, and also for different number of GPUs used for training, also for extreme cases of 1 GPU or 128 GPUs. Okay, so this is about the multigrid methods. Finally, I talk about multimodal learning. And since video actually comes with audiovisual input, it's very intuitive to process these modalities jointly, which has typically not been done in the past. And in this work, we try to do that. And I want to start with a motivation video. I don't know if this works straightforward to share, because the video is audio. I would like to share audio.
There is an option for sharing your computer audio.
Okay, I pressed on it. I hope it works.
And you can play the video.
Okay. Let's try. I will play it.
At any one moment, we are being bombarded by sensory information. Our brains do a remarkable job of making sense of it all. It seems easy enough to separate the sounds we hear from the sights we see. But there is one illusion that reveals this isn't always the case. Have a look at this. What do you hear? But look what happens when we change the picture. And yet, the sound hasn't changed. In every clip, you are only ever hearing bar with a B. It's an illusion known as the McGurk effect. Take another look. Concentrate first on the right of the screen. Now to the left of the screen. The illusion occurs because what you are seeing clashes with what you are hearing.
Okay, yeah, so I think this video is super interesting, and then the effect itself. So actually the sound doesn't change. You just see 2 different visual inputs, but you hear different things. So that means there is a lot of, there is a strong binding between the visual and oral input in the brain. And this is what motivated us somehow to perform this work. So the objective of the paper is to build an architecture for integrated audiovisual perception that we call audiovisual slow-fast. And this is going beyond previous work that typically did late fusion for integrating the audio information. So the audiovisual slow-fast networks is very simple. It extends the slow-fast model with an audio pathway. And you can think about this pathway as a faster pathway because audio typically comes at a very high frame rate, like in many kilohertz compared to the video signal. So now the model has a slow, a fast, and a faster pathway. If you would try this in the naive way, however, it will not work. And the reason is shown here. So actually, if you try it, it will even provide lower performance than the visual only model. So adding the audio will be harmful. And I think this can be explained by looking at the training curves here. So there are two curves. One is the green curve for a slow fast model, and the red curve is for an audio only model. And you can see that it's overfitting already the audio model, but it's trained much shorter. So audio trains much faster, and that's one important aspect. And if you train them jointly, this audio modality will be responsible for overfitting of your model, and then you get lower final generalization performance. So to overcome this problem, what we did in the work is using a very simple technique called drop pathway. And this is very simple. It just drops the audio pathway with 80% of probability. So a relatively high probability you drop the audio altogether. And this way, the visual information is used for learning in many more iterations, and therefore the network can no longer just overfit to audio information. In the paper, we used the model for several different tasks, and we showed that audio can improve the recognition across a variety of data sets and a variety of tasks. Sometimes improvements are larger and sometimes smaller, but improvements are consistent, and that's might not be surprising to any viewer, but the fact that audio helps is actually a good point. For example, there was an ActivityNet challenge in 2018 on this AVA dataset where I show the results here on the screen, and ActivityNet, they hosted two different challenges. One was for using audio information plus visual information or multimodal information for this task here shown. The other challenge was using just visual information. And in 2018, at least, turned out none of the challenge participants could exploit audio for this task. So none of them had a performance gain for using audio. So that's what's quite pleasing for this work for me is that audio was beneficial in different tasks and also in this AVA task, for example. And so this is the fully supervised case. I want to also briefly talk about the self-supervised case that we apply to audiovisual networks. And for this, another contribution of this paper that we have is that we use audiovisual synchronization to encourage the network to learn features that are generalizable across the audio and the visual modalities. And this is inspired by some audiovisual mirror neurons in the cortex. But specifically, what we do is very simple. We add an auxiliary loss that is tasked to whether classify that the pair of audio and visual input are corresponding to the same video and same timestamp, or if a negative, if it's from a different video to audio. So that's very straightforward. The loss has been used before in many works, and usually it's used just at the end of the network. Right, you have an audio network, you have a video network, you have this loss, or an image network, you have this loss. In our case, we do it in a hierarchical manner, like we do it at multiple layers. And of course, this loss can be seen as like a semi-supervised loss that we add to our supervised loss for getting better supervised performance, but we also use it for self-supervised results. And what I show here is just a snapshot of the results where we use this audiovisual model for a self-supervised application, and we can achieve state-of-the-art results for a self-supervised evaluation task with these off-the-shelf pretext tasks. So this just highlights that the model is very useful also for self-supervised tasks. Now, finally, I want to promote our codebase again, which is our PyTorch codebase for video understanding called PySlowFast. This is done together with my coworkers at FAIR, led by Hao-Chi Fan. And this codebase has and will have all reference implementations that for the methods that I shown in the talk. So if you would like to start working on this or related topics, please check it out. It's super simple designed, and it's very straightforward to use. And it's also has been very well adopted by the community we've shown with these graphs here from GitHub stars. Right, so in conclusion, I have 3 points here, or 3 pillars that I think are important for moving forward video recognition. The first is that I think video recognition is still significantly slower than image recognition research, and accelerating our training and our models like this X3D, SlowFast, and multigrid models, I think is very important for moving forward the field. Second, the world is multimodal and video captures this richness. I think our models should also hear and see, and audiovisual SlowFast is a first small step into this direction. And third, we this one might be obvious. I think the future will be unsupervised. We cannot afford to label everything, and video is the medium that allows us to learn from spatiotemporal associations across modalities, predict the future from the past, even perform high-level reasoning with causality. So I think video is the right medium to perform self-supervised or unsupervised learning. Thank you. I'm very happy to answer any questions during the Q&A.
Thanks so much, Christoph, for your nice talk. So let's see if we have any questions on the YouTube chat. We have no questions yet. So regarding first, I also have used your PySlowFast code. It's really nice code. Thanks so much for your great.
Oh, yeah, thanks.
Yeah, sharing everything, and just, yeah, it's a really nice code. So just a minor question regarding your SlowFast method. You said that you have designed 2 pathways with different frame rates input, somehow I can say, right? They're working on different frame rates, right? So how do you design it? How is it related to, for example, the norm of the videos, which is network is going to be trained on and have inference on, or how is the trick? How does it work here?
Oh, sorry, I didn't get everything. Is it related to what?
The difference between the pathways. One of the pathways is the frame rates they're working on, they're operating at are different. How do you design it? When you want to design your network, how did you come up with this setting?
Oh, how it came up. I see. Yeah. Yeah, I think the motivation is it's somehow also coming from the 2-stream works. So the 2-stream works, they use single frame in one path, and in the other path, a snippet of optical flow. So you can think about, like, probably the optical flow is a very low dimensional signal. So why not use a cheaper network for this part? Or maybe do we even need optical flow? Maybe we can just use high frame rate video. So that's like one way maybe of thinking of how you could design such a model. And yeah, I mean, the other pathway, if you think about 2-stream networks, in the 2-stream case, it's a single network, a single frame network. And in this case, it's a 3D convolutional network with low frame rate. So this is one way of thinking about it. Another way might be the neuroscience motivation, that, like, we have different pathways in the brain. We have more channels devoted to these slow cells, and less channels in the fast cells, the magnal cells. So yeah, I guess that's another way of coming up, I guess, with this idea. And I'm not sure how I came up with the idea anymore. Someone else asked me that today. Yeah, exactly.
Yeah, okay. Anyway, thanks so much for your nice talk. And
thank you. Yeah.
See you in the next event. So then, bye-bye.
Bye.
So we have Vondrick with us. So Let me unmute him. Okay. So Carl, can you unmute yourself?
Yeah.
Okay, now we can hear you. Okay, yeah, you can go on.
My screen too?
Yeah, we can also see your screen.
Okay, and you see the screen, you see the presenter view, or you see the main in slides?
It's a main slides.
Ah, okay, great. Okay, so should we get started, or should we? What time do we start?
We should start in 2 minutes, but it's okay. We can go on because it's just.
Yeah, sure. We can start now.
Okay, yeah. Okay, that sounds great. Okay, everyone. So I'm very excited to be here, and I've been checking out the tutorial on YouTube, and it just has been fantastic. So I sent the link to all of my students to check it out. So thanks so much to the organizers for putting this together. And thanks for staying to the end, right? I think it's Friday night in most parts of the world now, after a long conference.
Thanks for the appreciation.
I was just going to talk about kind of a variety of different works that we've been doing in video, and especially about learning from unlabeled video. And so I usually like to take questions kind of throughout the talk, but I guess on the online format, we'll just do questions towards the end. Okay, so there's been tons of progress in action recognition. I mean, Christoph's talk just before me is a great example of this, right? It's just incredible how well computer vision systems are at getting not just recognizing, but also detecting and localizing where action is, right, and classifying it. And it works across these really unconstrained scenes. Here I'm showing an example. It's pretty old. As my slides are a little old, I guess, right? This is from 6 years ago, right? And it was doing pretty well then, but a lot has happened then at trying to classify these actions. What we've been noticing in a lot of video data sets is that there's this bias in most video data sets, because most video data sets there's kind of a photographer's bias, right? Of the types of videos they have in movies, the types of videos that are uploaded to YouTube. People are, there's this bias for success. People are usually successful at performing their action, right? So there's an example, someone kayaking down a waterfall, right? And they survive, right? they are, they're succeeding at their action, right? And I don't know about everyone else here, but this is very much unlike my life, right? I am not able to do this. I am not this successful, right? I fail all the time, right? And I never quite managed to achieve my goals of being rich and famous, right? We're always stumbling through our life, and so we're interested in this bias, right? How come all the videos we have, people are always succeeding? So we're quite motivated by some really foundational work that has happened in the last 2 decades in developmental psychology. Here's a video I'm playing from Felix Warnicken's lab at the Max Planck Institute. What he found is that I think it's around the age of 2, kids are able to basically infer when action is no longer intentional, and even predict what the goal was, right? There's this basic capability that we learn. You can almost, I guess you could call this common sense, right? That we have this common sense to recognize when action is no longer rational. It's not rational action, and we can actually predict, hey, what did that person want to do? And so we're really inspired by this result, right? This seems to be a very important capability that we have. Right, this is something that a 2-year-old can do. Okay, a 2-year-old cannot play chess, right? It can't play video games. They can't drive a car. But we're thinking this seems like a fundamental capability that is just missing now from computer vision, right? They're not able to determine when an action is not rational. So this week at CVPR, we released this new data set that we're calling the OOPS data set. And this is a large-scale data set that basically shows unintentional action. And so it just shows, kind of people messing up in all kinds of different situations. We downloaded these videos from YouTube by specifically querying for fail videos. These are the videos that are popular online, right? Of failure. And so they cover all different types of situations. There's some sports, there's some sort of just people at parties, there's some people just playing pranks on each other. The dynamics are, there could be physical dynamics. Here's an example of a social one, right? Someone is trying to surprise someone. It's just, here's a physical one, right? There's kind of a slip. And so, here's another example of a multi-agent, right? In this game, that's a competitive game, right? And someone has to lose, right? Someone is not going to achieve their goal. And so we're thinking this will actually be a pretty interesting data set here for trying to learn about, what is rational action? What is action that is intentional? And we chose that one thing I like about this data set is that it's pretty obvious, right? What's going on, and it's pretty obvious that these actions are not intentional, right? There's very high level reasoning we could try to do. We could try to model in a movie, like did that person really mean to do that? And you could kind of go down this rabbit hole of really complex situations. This data set is not that, right? These are really clear-cut kind of basic atomic actions that are not rational. And so I think this actually is a really nice data set for trying to make progress on this problem. Okay, so this data set was collected by two students in our group, Dave and Bo. Their photos are up here on the top right. We've collected about 20,000 videos from the web. I think we could always collect more. We're an academic lab, so we can't collect a million examples yet, right? But so this is 20,000 examples, and we've annotated the videos with the point basically the temporal position in the video, that the video transitions from being intentional to unintentional, right? So all the videos in the data set are going to start off in intentional, and then they're going to conclude at being unintentional. But the point where this transition point happens is the variable, right? And so we've annotated the point in each of these videos when this transition happens. And so this data set's all online now. You can go download it online, or just check out more of the videos. It's really, I promise you, it's a really fun data set to work with. We had a lot of fun trying to debug our approaches on this data set. So it's online at oops.cs.columbia.edu. Here's just a couple of kind of basic stats about this data set. This kind of, I don't think there's anything too surprising here. The videos on average are around 10 seconds long. This is kind of consistent with kind of the state of the art in videos now, right? It's not these, and this goes back to the point about how these are very atomic actions, right? This is not a 2-hour film about someone not achieving their goals over 2 hours, right? This is someone not achieving their goal kind of within 10 seconds. So I think will give us important traction. So the middle plot here in B is showing the bias essentially in the data set about when the transition period is from intentional to unintentional. And so you can see that there's kind of this obvious bias that I think we'd all expect that the middle frame, the center of the video and time, that's going to be the mode of the distribution. So that's true here too, but this is fairly well spread out, right? If you were just to guess the mode, you would actually do quite bad. It looks like you get if you were to guess just the mode of the distribution, you'd just get around 3% on this task of trying to localize when the failure starts. And so this also covers just tons of different actions and scenes. And so the bottom plot here is just showing a histogram of the different types of scene categories and the different types of action categories. It's kind of this your standard long tail distribution here. So I think this is quite exciting because it's really unconstrained, right? This just covers very, very diverse situations. So the problem that we were interested in after we built this data set is, can we learn a representation about rational action from self-supervision? We're interested in this question, are there any just intrinsic perceptual clues in video or in motion that we can use to try to recognize whether something's intentional or not? And I think we anecdotally we do this all the time in our daily life, right? If we're trying to accomplish a task, we often look around and try to find someone who seems like they know what they're doing, right? And so we have this, and it's something that kind of comes automatically to us, right? This happens around 2 years of age in kids, and there's also evidence that some monkeys are able to perform on this task, right? And so they didn't have time to, by the time you're 2 years old, they didn't have time to have millions of examples of saying this is failure, this is success. And so we're really interested in saying, how can we learn this from limited supervision? Can we learn this from full self-supervision or even just a small amount of labels? So we are investigating a variety of different perceptual clues for performing this task. And these are kind of perceptual clues that are intrinsic in video. We investigated 3. The first one that we looked at is just the predictability. And this is a very common self-supervised clue now. Just about, can you predict the future? And what the hypothesis here, what this clue is going to be investigating is, maybe failure is hard to predict, right? There are many more ways to fail than there are to succeed. So it's going to be harder to predict failure than it is to predict success. And so perhaps this is one clue we can try to use to learn a representation of rational action. The other self-supervised clue we also looked at is the second one is just the temporal order. This is also a very, very common clue in self-supervised learning now, just by if you shuffle the frames, right? And so this looks at a high-level clue of, maybe you have to fail first before you can succeed. The third clue that we looked at that actually performed the best, and I think was quite interesting, is about trying to use the speed of the video as a clue for learning a representation. And so kind of what's really common in self-supervised learning is that you want to take some signal in the data that is available to you for free, right? And then you can use that to supervise your model. So this has been done a lot in, so predicting the future is one example, right? The future is naturally available in the data for free. Another one that is just naturally available in the data is the frame rate, right? How fast the video plays. And it turns out it's actually really easy, right, for us to perturb the speed, right? We can just drop frames from a video, and this is going to make it look sped up, right? And so when we drop the frames, we know what we've done onto the video, and so this provides essentially an intrinsic clue in order to learn representation. So specifically, what we do for this clue is we have these bunch of these videos. We drop frames from them randomly, right? Sometimes we drop 0 frames, sometimes we drop every other frame, sometimes it's every fourth frame, right? And then we can train a model to predict how much time has elapsed from these videos. And you can do this on a large scale, right? Because this is available in all videos. Our hypothesis here is that by doing this, the model has to learn some features about motion, right? It has to, if you take this example here, right? You have to learn some features about what are the typical dynamics that you would see in a scene, and how are objects typically going to move? What is their typical speed, right? We all know this video here is slowed down, right? Because people don't move that slowly, and water doesn't fall that slowly, right? So we think this is actually going to learn really nice features for motion. It turns out there's another link here, which I just want to bring up for context. And if you're ever on a jury, this is something to keep in mind. And so it turns out that at the speed of the video, if you slow down a video of someone's action, it actually looks much more intentional. Right, and so slow down video creates this illusion that a person had time to premeditate the action. And so there was a fairly famous court case. Boy, I'm forgetting how long ago this was now. I think it was in kind of in the last 20 years, where there was someone was on trial for murder, and there's a surveillance video of someone, I can't remember if they're stabbing or shooting someone, and the jury saw the video slow down, and so they had a harsher punishment for the person because it seemed like the person had more time to think about it, right? And so it is interesting to keep in mind about the speed at which we see things can actually change our judgment of the scene. Okay, but so we're just going to use this fact that duration is intrinsic to the visual modality to use that to learn, and we can train this model up on tons of videos. Take any video data set that we want. It could be in kinetics or AVA or any types of video data sets that we saw out here, and train the model to basically predict how much time has passed, right? How much time has passed, and we think this is going to learn nice features. So after you train this model, the first thing we can do is just to get a little bit of intuition is we can probe the representation and look at the nearest neighbors. And so we can, you take this representation, these features are trained that are predictive of the speed or the duration. You plug in a query and you look at what other videos are closest to that. And it turns out that it actually does pretty well here, right? It tends to find clusters of objects that have similar motion, right? This is learning good features for motion, right? So kind of in sports, people are going to move kind of the same way, right? Whenever someone picks up a ball, right, or the kick, that's going to have very similar motion, right? So those types of videos will be clustered. People are going to move kind of in the same way, right? A person's not going to move like a car or a ball, and so the model seems to be picking up on some types of these clues. So we kind of to go back to our original task of trying to predict whether action is intentional or not. We're just going to use these features as basically as a feature space for training a classifier to predict whether action is intentional or not. So the way we do this, we have this feature space induced by this self-supervised clue. We have a little bit of labels, right? We need a few. I think we need it's about a few thousand labels to say what is intentional, what's not, and we fit a classifier on those features to do this class classification task. Okay, so here's a couple of examples of the results. So here's a video of someone doing something that's clearly not rational. This is not something that they probably intended to do, right? And then the chart at the bottom here is showing the output from our model. And so the blue is saying what's basically what is the probability that the model thinks this is intentional. The red is the probability that the model thinks this is unintentional. And then orange is this transition period. So there's a third category, which is saying that it's transitioning from being intentional to unintentional, right? So okay, it's not amazing, right? It makes some mistakes here, but it's starting to learn some features for this task. Here's one that's a little easier, right? There's a lot of clear motion here that you can use to try to predict whether this action is intentional. Right, this is kind of an example where falling down, right? Most people don't intentionally fall down, so the model probably learns that here. Here's an example I really like, and I like this example because this is a case where the model gets it right, but for the wrong reasons. And so here it's like a person getting hit by a gate, right? And the model gets this right. It's kind of surprising that it gets this right. It seems like to really solve this problem, what we need in the model is we would need it to do something about theory mind, right? Truly, to really rigorously solve this problem here, it should be able to predict. This is not what it's doing, but what we'd want it to be doing is recognizing what the person's gaze is and reasoning that the person probably doesn't see the gate falling down, and therefore that's why it's unintentional. I don't think that this video speed task is able to learn that, right? Okay, and so we I should mention here as well, we experimented with a variety of different baselines too. So both this naive prior where you just predict the mode of the distribution, as well as other baselines like you can compute optic flow and compute a histogram from that, and just look at kind of global motion statistics, right? To try to do this task. The model that we have, where you predict the video speed first, and then you train this classifier on top of it, that performed the best, right? And actually outperformed this baseline. So these very low-level clues are not enough to solve this data set. It's not just about kind of trying to find what the dominant motion is. Okay, one of the experiments that we did was we annotated a diagnostic set here in the testing set of what caused the unintentional action. And then we could look at performance of the model versus what types of videos. And the hope here is that this is going to give us some intuition into what type of examples is it doing well on, what type of examples do we need to see more progress on. So the way you can read this plot is that lower is better. This is showing error. So the horizontal axis is error. The red bar is the error of our model that's self-supervised. The gray bar is if you use kinetics pre-trained features. And so what this is showing is that if you have a bunch of supervision, you have millions of examples of labels to train your representation, you actually outperform, right, this self-supervised approach, right? And so this is kind of a standard story in self-supervision, where having more labels, there's still no substitute for large amounts of labels. And then the dashed line here is showing human performance on this task, right? And so, we're far from human performance on this data set, right? All of the models here, even if you have a bunch of supervision, it's still not as good as a human here. And all of the videos in the data set we've annotated multiple times to ensure there's consistency, and there often is high agreement. Okay, yeah, like I said, kind of all the examples, the data is all available at oops.cs.columbia.edu. We also just put up some new annotations last week where we actually annotate the goal in the videos too. And we'll be trying to put a paper up about that on archive soon. So, sorry, how long do I speak for? Do I speak for an hour or half hour?
So you can speak for about more half an hour.
Half hour more. Okay, yeah. Great. Okay. All right. So I want to move on to another type of clue that we've been looking at for self-supervision. And there's, I think Chen in the morning may have talked about this kind of a similar idea.
So it was meant to be 45 minutes plus 15, but.
Okay, yeah, I'll just keep on going, and then when people get tired, I'll stop. Okay, so I want to talk about this other clue, and I think Chen's son in the morning talked about a variant of this, and this is kind of our take on the problem here. And the idea is that in video, there's free supervision from speech. So when people talk, right, in the video, that provides some incidental supervision about what's going on, right? And so the analogy I want to make here is like to a world traveler, right? When you travel the world, right, and you go to a country you don't speak the language, right? You have to figure out what different things are, right? Based off of just what are the people around you saying, right? And you start to notice these patterns, right? You start to pick up these patterns. If someone always calls a certain object by the same sounds, right? You start to make that association, right? We also have very rich abilities to reason here, right? If you know one word, and then there's a novel word to you, you can use process of elimination, right, to figure out, well, what could that word be in that scene? And so we're interested in creating a model that could try to learn a representation in vision and language, using this idea where you've gone to a new country, you don't know the language, and you have to try to figure out how to name things. So the state of the art in kind of word acquisition here is kind of these various different models for that stem from BERT. So I think probably as most people know, right, BERT was this model that Google produced, 4 years ago perhaps, and it just smashed state-of-the-art performance across different NLP tasks. Kind of shortly after that, there was a variety of different models that extended BERT to vision. And so this is basically using a self-attention-based transformer between both visual stream as well as paired text to try to learn a representation. And the way these models work is that you input the scene, you also input the corresponding text. This could come from automatic speech recognition or from a caption. And then you mask out some of the words and you train the model to fill in the mass word, right? And this turns to learn a quite good representation. There's a couple of problems with this approach though. And one of the problems is that it just requires huge amount of examples, right? BERT, the original BERT is trained on, I don't know, billions of examples, right? And so it doesn't have this data efficiency that you would want. We don't want to see millions of examples of a particular object to try to learn a representation or learn the name of it. The other problem with this approach is that it's not compositional. So the model is basically trained with maximum likelihood, so it's only going to fit to the same distribution as the training set. And if you change that distribution and test this time, the model is going to fall apart. And so this is a big problem in both language and vision tasks, because our world is naturally compositional. Right, we can combine words that we know into new compositions that we've not seen before. They're outside of the training set, right, of our own training set. And so how do we get this type of generalization? The third problem here is that it also requires hard coding the grounding. We basically have to hard code how do we do the language acquisition, right? And we're hard coding this task, saying, you know, the way if you train the model up on this particular example here, right, you're saying it has to fill in this mass word, right? And this is the task it has to do to solve this problem. And this is not going to be enough, right? This is the fact that we have to hard code this is what's requiring us to need so many examples and leading to representation is not compositional. So in the latest work that we've been working on is, rather than trying to learn what a word means, or rather than trying to learn what stir means, we want to instead learn how to learn words. So we don't want to hard code the process for word acquisition. We instead want to learn the process for word acquisition. And so we think that by basically changing this paradigm from just your standard supervised or unsupervised learning, and instead treating this as a meta learning task, right, where you want to learn the process rather than learn the representation, is going to lead to more robust models. Okay, so the standard way in meta learning, the standard way that this works is, rather than having a distribution of examples, we're going to have a distribution of episodes, and these episodes are basically going to show what an episode basically does is it shows you a data set, right? So rather than feeding in a single example to the model, what we want to do fundamentally here is we want to feed in a data set to the model, and which we can then learn from. So this is actually pretty easy for us to do here, right? We instead of sampling a single example, right, that we then compute the gradients on, we're going to sample several examples to form an episode, and that episode is going to be fed into the model. And I'll talk about how we sample that in a bit. Okay, so once we have this episode, right, what do we do with it, right? How do we learn to learn from these episodes? So the idea that we had was that we can actually treat a transformer as a model for meta learning. One of the advantages of the transformer is that it's actually able to capture very complex pairwise relations between the elements in the input, right? So instead of just putting in a single image, right, we can actually put in several images as well as their corresponding captions, and this representation is going to be able to find all the different types of relationships between the inputs, just because it's based off of attention, right? And so the output of this transformer is going to be basically a vector corresponding to each input, right? So H0 is going to be a vector H0 is going to be a vector corresponding to an image. H01 is going to be corresponding to a word, and so on. They're each going to be vectors. But importantly, these vectors are going to be contextual, and that they're going to depend not just on the single isolated example here, but actually going to contend on they're going to depend on the entire episode. So what we can do for meta learning is actually, once we formulate this way, it's actually quite easy for us to perform meta-learning task where we have in the input a test example, and there's a word that's been masked out, right? And here the word is chair by the question mark, right? This word chair has been masked out, and we want to train the model to try to predict that word. But rather than just synthesizing that word as you would in a standard BERT-based model, what we're going to do instead is train the model basically to point to that word to another across examples within the episode, right? So to actually fill in this masked word, it has to point to another. It has to point to another example within the episode and pick up the right word and put it in the right place. And so we can think of this basically as a meta learning task because it has to learn how to acquire a word from other examples in the episode and then use it to describe a novel image. So one thing I like about this approach is that we can be very explicit about what types of generalizations that we want. So the types of generalizations the model will be able to perform are going to just be dependent on how we construct these episodes. So in this work, we considered two different types of episodes. One type of episode is acquiring a new word. So if there's a new word at test time you've not seen before, can you actually learn a representation for that word and then use it to describe a new scene? So this is actually very easy for us to construct these types of episodes, right? We can synthetically always withhold some words. The other type of episode that we considered was a composition, where maybe it's seen both of the words before, but it's not seen their composition. So in this example episode, during training, it will have seen the word stir and the word paneer before, but it's never seen the composition stir paneer. So this is an example where the model is going to have to do compositional generalization, right? It has to generalize new composition it's not seen before. And the idea here is that by constructing episodes that show this type of generalization, it can learn a representation that will be robust to new compositions. So at test time, the model supports two different types of modes. One mode is just your standard language modeling task, and the second mode is this new task of word acquisition. And I think this is actually kind of an interesting advantage of the model. Because the transformer is flexible and it doesn't require a fixed number of examples in the input, you can basically adapt the number of inputs that you feed into the model at test time. So if we just construct an episode with a single example, right, the model will still work and it will still create a representation for the elements in that episode. Of course, it won't be able to acquire new words, right? This is just if it just has a single example, right? It's only able to use the vocabulary that it already knows. It can't acquire a new word at test time. In mode 2, right, you can feed in an entire episode now, and the episode can contain new words, and the model is able to solve this mass word task by actually pointing to the other examples within the episode. Okay, so you can evaluate this on a variety of different tasks. The task I'm going to show you is the language modeling task. And so here we're going to compare a couple different models versus baselines. So this is showing accuracy on the vertical axis here versus a couple of both two baselines. One is the BERT off-the-shelf model, and the other one is one of these BERT plus vision. And so this is looking at the accuracy at this language modeling task for both scene compositions and new compositions. And what I want you to see in these examples here and for the baselines is that when you test it on new compositions it's not seen before, there's a huge drop, right? You get this almost 20% drop, right, in performance, right? And this makes sense, right? The model was not trained on these types of compositions, and so there's no data, there's no evidence, right, in the training set to support that this composition exists. And so it's not, it basically learns the bias in the data set instead, right? So here's what our approach does. If you meta-learn this model instead, but then evaluate on the same task, right, this language modeling task, you get these green and blue bars on the right. And so what you should notice from this is two things. Firstly, meta-learning the representation leads just to performance gains across the board, right? So it outperforms even on compositions that are old, right? That have seen the composition before, you still get a gain. But the other point is that when you see a new composition, when the model sees a new composition, the drop is much less. Now there's still a drop, you know, it's still a hard problem, but that drop is much smaller, right? This is basically the drop is half as small, right? So this is supporting this hypothesis that, you know, if we meta-learn the representation, we're gonna get better generalization. Okay, so the second task that we can look at is the word acquisition task. So this is where at testing time, we show the model some words that's not seen before. So these are new words. And so in this example, so in this episode here, there's two words that are new that's not seen before. It's never seen avocado and it's not seen skin in before, right? So these are two different words that are new. So the training set are these first three examples, and then the testing set in the episode is the example on the right. And so the model should basically fill in what word should go here by pointing into one of the words in the training set. And this is hard, right? Because it's never seen this avocado before. The only example of avocados that it's seen is the one here on the right, right? And so we can visualize this pointing mechanism, right? And it points to the right word here. Here's another example. Right, so cupboard and oven are new. And then we ask it to use, so basically you can think of the model as learning on the training set, and we ask it to use it in a sentence at test time. And so the model has to fill in the right word here, right? And so even though it's only seen this single example in the episode, right, it often points to the right word. I should say that we tried this on a couple of different data sets. I'm showing you the most challenging ones. So we tried this on both Flickr 30K as well as Epic Kitchens. This is showing Epic Kitchens, which is just a really challenging data set. I think you've probably seen it throughout this tutorial, right? There's lots of different complexities here, both in vision and language. Okay, so we can also analyze this model about how well does it perform as we show it more and more challenging episodes. So when there's more new words in the episode, right? If there's not just 2 new words, let's say there's 10 new words in the episode, right? How well does this perform? And so this is the plot showing this. So the vertical axis is the accuracy. So higher is better here. And then the horizontal axis is the ratio of new words to old words, right? So if you're at 1, right, that's actually quite easy, right? For every new word, there's 1 old word. And if you're at 10, right, what that means is that there's for every old word, there are 10 new words, right? So that's quite hard, right? And so of course, as this ratio goes up, your performance is going to drop. The point we want to make of the plot is that it stays fairly robust, right? More robust than the baselines here. Okay, since we're doing a meta-learning task, what's interesting is we can actually visualize the process that it learns, right? It's learning this model for word acquisition, right? And so we can visualize, well, how does it, like, what type of process did it learn, right? Rather than this handcrafting process, right? What is the process that emerges? And so the way we can do this visualization to try to answer this question is we can take the transformer that's learned, right? It's learned on this episode, and we can start cutting out different connections. And we can see what happens if we cut that connection, how much does the performance drop? And so the more performance drops when we cut a connection, that's going to suggest that connection is actually more important, right? If there's a large drop, then probably that connection is important. And so what this figure is showing here is it's showing which connections are the most important. And so the thickness of the line here is indicating that it's more and more important. So the way you can read this is that at the very left is basically the input to the transformer. And so there's going to be text examples in the dark blue here. Right, this is going to be text examples in input. The image example for the first example in the episode. And then the same thing, the text here, right, for the second example, and the image for the second example. And then for the target example in green, right, is going to be the text and the image. And what these curves are showing is how information is flowing through the model. And so what you can see what's going on, the type of process that's learned is it's learned to first take the text or the speech here and basically move it to the image nodes. That's the first thing this thing learns for processing. Then in the second layer of the transformer model, it kind of mixes everything up, right? It kind of all different connections are activated. And then in layers 3 and 4, everything's going to flow back to the text node, right? And so I think it's an interesting visualization of what type of process the model has learned. So we also, one of the things we can also look at is we can visualize what types of visual regions does this attend to when you perform this task. So if you do this word acquisition task where it's not seen the word before, does it actually attend to the right region, right? So if you're trying to teach it this new word, tomatoes, right? Does it actually attend to the tomatoes in the scene to learn that word, or does it attend to some other part of the scene? And so the way we can do this is actually very similar to what we did before, is we start cutting out different parts of the scene, and we can see where it attends to the most. And so the green here is showing the region in the episode that if you were to remove that part of the image, the performance would drop the most. And so this is actually very reassuring for us, right? I mean, if it's trying to learn the word tomatoes and we remove the tomatoes, then the performance is going to drop the most. Same for the spoon here, right? As well as for the container, right? If you remove the pizza, right, or the avocado, it doesn't impact the performance at trying to predict the tomato here, right? And so this is a good sign because it means it's learning the right grounding, right? It's not learning some spurious grounding in the data set. Okay, so all of the code and data is online at expert.cs.columbia.edu. And yeah, it's all in PyTorch code. So I think it's actually a quite cool model. The transformer seems to be quite powerful as an architecture for learning different types of representations. And so I'm excited to see, and of course it's not the end-all solution, and eventually there'll be something better, but I'm excited to see how far we can push this, and you know, what are the limits here. Okay, so I think I have about 15 minutes more. So I guess I can talk about one more work. And this is another example of incidental supervision. And the supervised clue that we're interested in using here is basically the coherence of color across time. So when you record a video, the one free signal in the video is that objects are not really going to change color over time. As they move through the scene, the color is not going to change that much. And so there's very, you know, kind of one very clear, I guess one example of this, right, is that whenever you're watching TV or watching on YouTube and your video codec breaks all of a sudden, right? And the video is no longer in color, right? You're not all confused, right? Here's two different frames from a video. The left is in color, the right is in grayscale. And we're not confused about what the color of the balloon is, right? We all know the balloon is red here, right? The arrow is pointing to a red pixel, right? And the reason why we know this is we have this prior assumption that color is going to be temporally coherent across time. And so, this is, if you just take a random video off the web, right, from YouTube, this is just going to be a general property, right? As objects move, the color is going to be fairly stable. I mean, it'd be very surprising to us if this boy's shirt in blue were suddenly changed to red, right? That would be very surprising to us. So there are, I mean, we're all computer vision folks here. I mean, of course, there's a variety of exceptions, right? You turn on a green light, everything's going to turn green. There are very well-known illusions, right, about color. And it's also just ambiguous, right? We don't know what the color of this dress is. But for the most part, if you just take a random video off the web, there's going to be this coherency. And so the hypothesis that we had, this is a paper we published at ECCV 2 years ago, is that color is going to provide self-supervision for learning to track objects. So we can formulate this self-supervised learning problem where once again, we just kind of splice up our data and remove something from the example and then try to predict that. And so the way we're going to spice up our data here is we're going to take video and we're going to remove color from all of the frames except the first one. Okay. So it's basically, there's this video where the first frame is in color, but all the others are in grayscale. And we're going to train the model to try to recover the color for all the other frames. And the hypothesis is that in order to perform this task, the model has to follow the object, right? In order to know what the color of this car here is, right? In order to correctly predict it, it has to follow it from the first frame and propagate that color red throughout the video. So, I mean, colorization, has become a popular problem in the field. There's been a variety of work that we were, heavily inspired by, especially in doing colorization for images. Here's one of my favorite ones. This is a photo of Ansel Adams in grayscale, right? And then when you run an image colorization on it from Richard Zhang and his co-authors, right? The predictions for color are actually quite good. So in this work, instead of asking this question for a single image of what color is this, we're asking a slightly different question, which is where should we copy the color from, right? If we want to predict the color for what that red arrow is pointing to, where in the other frame should we copy and paste it from, right? This is the question we're going to ask. And by doing this, we think it's going to learn a model for tracking. Okay, so right here, we all would of course want to copy it from the same person, right? If we were to take this and try to copy it from the bed, right, we would get the color wrong. Here's another example. I mean, I think color is actually a pretty interesting signal because it's robust to occlusion, right? So color does not demand that we get point-to-point correspondence, which I think can actually be a good thing. Sometimes the point-to-point correspondence, like you might have an optic flow, just might not exist, right? And so if an object is to rotate out of plane, then there's not going to be a valid correspondence, right, point to point, but color is going to be generally temporally coherent. So, okay, so the way we formulate this problem is we have an input frame in grayscale, and what we want to do is basically colorize by pointing. So for each corresponding pixel in the input frame, we want to point into a reference frame that's also in grayscale, and then copy and paste the color back, right? And so right? We basically want to learn this copy and paste mechanism. What our model is going to do is we're going to write each patch in the video here. So each location in the frame is going to be written as an embedding that's going to be learned by some convolutional net, right? So Fi is going to correspond to some particular location here, and Fj is going to correspond to another location in the input frame. And we're going to have a similarity matrix between these embeddings, Fi and Fj. There's a variety of different metrics we could use for a similarity matrix. We just use kind of a inner product normalized by a softmax. And what this lets us do is that our prediction for the color here, for what this color should be, is written as C hat J. That's just going to be a linear combination of all the other colors in the reference frame, right? So there's a linear combination of all the other colors in the reference frame weighted by the similarity matrix. Okay, so our prediction is just going to be this linear combination weighted by the similarity matrix. So what's nice about this is very easy to train this, right? Because we actually know what the true color is, right? We know what the target color is because we were the ones who removed it, right? We can just train the model to try to recover what this color should be from this linear combination. And we can backprop all the way through this. Okay, so one example I like to show here, just as kind of historical context, is videos have kind of historically how videos were colored, where the very first movies in color are actually made manually by basically the equivalent version of Mechanical Turk, right? So rather than us paying people around the world to annotate data to produce film, you have a sweatshop or studio, I guess, as they might call it, but really it was a sweatshop. And each person would paint basically one frame, right? It'd paint a frame with a paintbrush, and that's how color came about. And if you got it wrong, this was one of the very first color movies to come out. If you got it wrong, it looked quite funky, right? It's right. And so when you violate this color coherence, right, it doesn't look right. We all know there's something wrong. So here's an example of the model that we trained up on trying to predict the colors here. The reference frame is on the left column, and then the grayscale video as input is in the middle column, and the colors that it predicts are in the right. And so you can see it does a pretty good job at doing this colorization, right? Even as this person dances, right, it's able to predict the right colors for the dress. It makes some mistakes, right? I mean, so here, the hands, for example, you don't see, or the skin, right? You don't see that in the reference frame, and so that's why it gets those wrong. I love the egg example because this is an example where there's no valid flow, right? The optic flow doesn't really exist here. It's not a valid point-to-point correspondence, but color is actually fairly robust to that. Okay, I want to move faster here. Okay, so the key result here, though, is that by doing this colorization, we can show that tracking emerges automatically. And so after you train this model up to do colorization, what you have is this pointer, essentially, pointing between frames, which we can use for tracking. And so the way we can do this at test time is rather than, even though we train on colorization, we can then use exactly the same model, but instead of propagating colors through time, we're going to propagate a mask. And by propagating that mask, that's going to give us tracking. And so what we're going to, kind of the assumption that we're going to make in the model is that we need to know what the object of interest is in the first frame. And so we have to have that type of annotation, but that's all we need. We don't need any other type of annotation. We just need to know the first frame, what object we want to track. And so there's no supervision beyond that. Okay, and so you can use exactly the same model for doing tracking. So here's a couple of examples of the results. These are you know, two years old now. So there's, but I think it did it did remarkably well considering it, you know, was not supervised. So this is showing examples on the Davis data set. Excuse me, where the colors are corresponding to different instances. So you can see it actually does pretty well over fairly complex transformations, right? You know, even there's multiple people wearing about the same color coat, right? It's actually still able to track them separately and keep the identity. If there's a mild occlusion, it does okay, right? Here's a ball going under a partial occlusion. You know, if there's very extreme occlusions, this does not work, right? So this is still area for improvement here. Here's some more examples. You know, I think the reason why it does well in these really complex scenes is just because it's trained on such complex scenes, right? It's trained on the kinetics data set, which shows the realistic diversity of dynamics. And so, you know, I think that's why it does this so well. It can track other things as well. So for example, it can also track pose. So instead of propagating a mask, we're going to propagate key points. And you know, it does a reasonable job. Okay, so you know, of course we evaluate this. I'm running out of time. Of course we evaluate this. You know, 2 years ago when we wrote this paper, it was outperforming optical flow based off of flow nets. This was actually very exciting, right? It's an unsupervised model for tracking, and it's outperforming this you know, highly engineered models for optical flow. Since then, there's been a lot of development in this area, especially from Oxford and Berkeley, on improving these models using cycle consistency and memory. And so this performance continues to improve. And so with that, I think I'll stop. So thanks very much.
Okay, thank you very much. It was a really nice presentation. So we have some questions on live chat on YouTube. I'm going to ask them so quickly as we are running out of time. Santosh has asked, I think it's about this OOPS dataset. He has asked that are the videos in which there is a transition back from unintentional to intentional. One can imagine a person who recovers from a fall and continues walking, for example.
Yes, that's a great question. So far, we've not considered that. So in the assumption that we make right now is that once you fail, you stay failed. But I think this is a very interesting direction to go, right? If you can recover.
And another question Santosh has asked again. He has asked, have you tried your methods in the OOPS paper on other anomaly detection datasets, for example, UCF crime?
No, we have not. I think that would be interesting to try.
Okay, and G, he or she has asked, why do you design to only give color for first frame? What if give color to some middle frame or even multiple frames?
Yeah, that's a great question. You know, I think you certainly could. So one limiting assumption that we make here is that you can only track objects that you've seen in the first frame. So if another object appears that you didn't see in the first frame, it would not be able to track it, right? So I think that's definitely, it would be an interesting extension is, you know, if there's new objects appearing or they're entering and leaving the scenes, how do you use color beyond just the first frame? That's a great idea.
Okay. So, thanks so much again. And Vivek, do you have a question?
I have like two questions, okay? So like the first part, the OOPS paper that you spoke about. So the difference in future that you have been considering, right? Was it uniformly drawn between a certain time range or was it always a fixed step size?
You mean here on the distribution?
Yeah, when you're training a network, like were you uniformly drawing it from like a given time range while training, or you always use a fixed step size?
Yeah, so in the training of the self-supervised model here, we're actually changing the frame rate, right? So by dropping frames. So I don't remember exactly. I think Dave would know the exact answer here, but you know, it was something like we either dropped no frames, we dropped every other frame, we dropped every fourth frame, or every eighth frame.
And okay, and like the second question, like is so with respect to the last paper that you spoke about the color patches, like how accurate were the correspondences for the same color patch when considering a patch of a smallest like resolution or when higher resolution? So do you have any thoughts on that?
I don't understand the question actually.
So like if you are doing this correspondences matching, right?
Yeah.
And if you have a smaller patch size, then the correspondences might be more. If you have a higher patch size, then your correspondences might be more accurate. So in that aspect, did you learn something from there?
Yeah. So that's a great question. In fact, the one thing that's really missing from this model is it's not multi-scale. So it only assumes there's a single scale, and a lot of the failures are when the scale will change. We did not optimize that very much. It was kind of a fixed resolution, and we just tried out one particular combination. We didn't really tune the hyperparameters on this, on what the.
Okay, like in the final thing, like, so do you think it would be scalable when it comes to images rather than videos? Because you have a huge correspondences, right, in videos, but what if we apply the same technique in images? What do you think, what would happen, or if you have any thoughts on that?
Yeah, I mean, I think it'd be very interesting. So this model basically is pointing it within video, but you could also do it pointing within an image. And I think that could be quite interesting. I mean, maybe it learns rules about grouping, right? I don't know. It'd be an interesting experiment to.
Okay, great. Thanks. Yes.
Okay, thanks, Carl, again. It was a really nice talk. And I hope to see you again in our next events. And have a nice evening, I guess.
Thank you. Thank you.
Okay, bye. So David, he's with us now. Let me see if. So David Ross is going.
I'm here. Can you see me?
Yeah, sure. We can see you. Okay, you can go for it. I'm not going to introduce the talk. You can just go for it. I can see you. I can hear you. Yeah, you can share your screen and go on.
Okay, great. Can you see the slides?
Yeah, we can see the slide really well, and we can hear you really well.
Okay, great. Thank you, and thanks everyone for sticking around for the final talk. I know it's been a long day, and for people in Europe, even longer. Great. So I'm David Ross from Google Research, and today I'm going to talk about context and attention for detecting objects and actions in video. So detecting objects in images is a really well-studied problem, and the community has produced a number of strong models to address it, such as faster RCNN and any number of really amazing other architectures for addressing it. So suppose we're considering the problem of detecting in video. Can we solve this simply by applying an image-based model on each frame of the video? Obviously, that'll work. It's possible, but I'd like to argue that video is actually quite different. So simply applying image models on each frame leads to problems and missed opportunities. For example, false positives reoccur in video. So consider this scene of a camera that's attached to a tree in the wild. I'm showing here 2 frames that it's captured of this video. Suppose the detector thinks that this pile of rocks in the bottom is an animal, and it triggers a false positive. So if it's pretty confident, this false positive will trigger in every single frame of the video, making any sort of analytics or alerting system or anything like that really just useless. So since this video is recorded over time, we should realize that these rocks have been there and they haven't moved in a month. So they're probably not animals and we shouldn't be detecting them. Another problem is that detections can be missed in adjacent frames. So the animal here is spotted on the left, but maybe the next frame comes an instant later, and because it's a little blurry, it's not detected. But if the time elapsed is very small, the animal's probably still present, and so we've missed an opportunity there by doing independent detections. And thirdly, classifications can be inconsistent. So again, if these frames were taken nearby, maybe we can correctly detect that it's a deer on the left, and we incorrectly classify it as a dog on the right. But if the moment is just changed, like just a small difference in time, then it's probably still a deer, and we should be leveraging that to be able to do more correct classification here. So how do we resolve these issues? These problems can all be solved by leveraging the additional context that's made available in the video. And so the key to resolving these issues and the missed opportunities is how we actually leverage the context that's available in the video to us, particularly from other scene elements in both time and space. So in this talk, I'm going to go over 2 lines of work. On the left, detecting objects, or in this case, animals, in camera trap data. And also on the right, recognizing actions and detecting actions in YouTube videos. And we'll show that the models that work well for both are actually very closely related. So to begin with, let's consider passive monitoring cameras. These are used in a wide variety of settings, such as wildlife conservation, this camera trap attached to a tree on the left, traffic monitoring cameras present in just about every city, or home monitoring cameras that you might have set up in your own home. Since these cameras only record when they're triggered, it produces a sparse, irregular frame rate. And much of the data that it finds is empty or repetitive due to this false positive detection rate. So it's a very interesting type of data. It's video, but unlike the sort of video that we use every day that we watch on YouTube. The data produced from these cameras is challenging. So specifically, like in these wildlife cameras, we've strapped the camera to a tree. There's no photographer there operating the camera. So the objects of interest could be partially observed because we're not trying to center them in the frame. There could be poor image quality due to time of day or weather conditions. Or there could be background distractors, such as the 2 images in the right, I believe, have sticks that are triggering the capture, even though they're false detections. So how do experts label images like this? If I was a biologist who's working on wildlife conservation and one of my cameras produced an image like this, how would I go about labeling it? So let's focus on one potential object here. There's a blob in the image, and it seems like it might be an object, but it's kind of hard to tell. From this image alone, is it a foreground object? Is it background? What is it? It's pretty much impossible to tell. So humans that are looking at this look for context in other images that were recorded from the same camera location. Because we have this camera strapped to a tree, for example, it's there for a month, 6 months at a time. We can scroll backward and forward in time to see what other things might be relevant. So these experts can look over a very long time horizon for the images that have been captured by this camera. And then they'll look for cues like, what's the size of the object? Does it seem about animal sized? What sort of animals have we seen in this location before? And those animals, did they appear individually or as part of a herd? And all of this context is useful to help humans label the images. So in this particular instance, that context that I described can be used by human experts to identify that this blurry blob is in fact a wildebeest. In particular, for this instance, they can be confident because there's a herd of wildebeest that would migrate past this camera every day from a grassy plain to a watering hole. So humans are able to do a lot of, high-level deductive reasoning based on image data spanning months to be able to reason about what these things are and produce detections that would otherwise be impossible. So is it possible to put machine learning systems on an even playing field? Like, can we provide them with the same context that's available to human raters? So that's the premise of a new work called Context RCNN, long-term temporal context for per camera object detection. This is by my collaborators at Google Research and Caltech. So the idea here is to look at the entire stream of images that are available for a camera and then do a first pass through them to extract relevant contextual features. Then we take these features and we process them, we curate them, and we store them in a memory along with the spatiotemporal location information so we know where they came from, when and where they came from. So in this particular work, the feature extractor is an object detector that we've pre-trained on some unused training cameras, with specific locations. And then we froze this detector after training it on those cameras. So we take this frozen detector and apply it on our test camera, the stream of images there. And we get all of the detections that we see and use this to create our memory. So from the point of view of the test camera that we're looking at, the memory creation is an unsupervised process. We don't have any labels on the test camera about what is and isn't an object. So effectively, we've built up an unsupervised representation of what the camera typically sees, this particular camera sees, and then we're going to provide it to our detector, which is going to be able to make decisions based on the full context of imagery and video that's available to the camera. So we built up this memory from the scene. Using it is actually pretty straightforward. So we're just going to use attention here. I'm going to assume that most of you know about faster RCNN. It's a two-stage object detection system. The first stage looks at the image and comes up with bounding box proposals of where it thinks objects might be. And then it crops out the features from those bounding boxes and provides them to a second stage, which classifies the box as, wildebeest or lion or nothing. So the memory here is going to be inserted in between these two stages. So from each of the proposals that we get back from stage one, it's going to be a set of features related to a specific bounding box. We're going to take those features and relate them to the contents of this memory that we built up. And if we find anything relevant in the memory, we're going to inject these features into the feature representation for that particular box proposal right before we pass it into this second stage classifier. And so we'll be able to classify it based on the features of the box and what we were able to find that is contextual and relevant. The memory retrieval mechanism is the well-known dot product attention, which you'll probably be familiar with from the transformer model. The idea here is that the input features are from the box proposal that we had. The context features are from the detections that we ran on an initial pass over the data. And then we're going to compare derived features from the box to the memory, and then add anything that we have from this back into our feature representation for our candidate box. So that's the simple story, and I'm just going to complicate it a little bit more. In this project, they found that it's useful to include two memories here. So there's the long-term memory, kind of what I've been describing, which uses context provided from the entire stream of video for a particular camera. And there's also a short-term memory. And this one's populated just based on very temporally local context. So it takes all the proposals from the current image and from the two adjacent images. And that's formed into a memory. So how do we populate these memories? Two different strategies. On the short-term memory, we're only dealing with 3 frames here. So we run our region proposal network here, and we find, for example, up to 300 proposals for each of the image. And then we take all of those proposals and we add them into the memory. The long-term memory has potentially many, many more images to consider. So instead of taking all the proposals, we just take the single highest scoring proposal from each of the images in the camera's video stream. And this can be thousands of images, so we're only taking one. It's important to note that many of these images don't contain anything, but we're going to include at least one bounding box worth of data into the memory from each of these, even if it has a relatively low score. And we don't know a priori if these boxes that we found are animals or not, because we're doing this in a unsupervised process to create the memory context. So how do we use this? We tried this on 3 different data sets. 2 of them are these wildlife camera trap data sets, Snapshot Serengeti and Caltech camera traps. And the third one is a traffic camera data set called CityCam, which is different in character. It's urban rather than wild, but it has many of the same characteristics in that it's fixed in a place. The movement of objects through it is habitual. Buses will go down certain lanes and cars will take certain things. There's repeated patterns through time, and it can be hit by the same problems of like a false positive that just keeps repeating. So the results of using this context RCNN model are pretty striking. So if you look at the MAP, mean average precision detection performance on the Snapshot Serengeti data, it's a really big improvement, 46.7% relative improvement in detection. And if we break down the performance by class, we see that it's leading to strong performance improvements across the board. And this is particularly important for wildlife conservation because the rare classes might actually correspond to endangered animals, where we're particularly interested in being able to detect them. So it's good that this isn't doing something like simply focusing on the head or a few of the classes. These improvements that we saw for Snapshot Serengeti also hold for the other data sets. The win on CityCams is a bit smaller, but it's still a fairly significant 4.5 points increase in mean average precision. So now some qualitative results. You can see that it's able to detect objects that were really challenging before. For example, due to occlusion, in the top right, there's a truck that's moving out of frame. It's partially occluded. It's able to detect it. Or I guess probably an elephant that's in the midst of the trees there. It can find objects that are very small or due to poor lighting conditions. And we're able to see that on the CityCams data set, it is able to prevent one of these false detections, this median in the lower right, which would usually detect on every frame. It's able to identify that it's not actually an object and eliminate it. So it's able to correctly label objects in very challenging scenes. So going back to our wildebeest example, it's able to use context much like people were able to be able to identify that this is the animal in question. It's also interesting to look at the patterns of attention that the model places over the various elements in the memory when it's trying to make the decision. And we can see that it's not doing, one thing, it's adapting based on the needs of the particular image in question. So on the top example, there's a warthog that goes by this camera every single day. And you'll notice that the attention, these blue lines here, are spread out over many days here. So it's attending to different times where this warthog was visible. On the bottom, by contrast, there's a gazelle that appears in front of the camera and just lingers in front of the camera for a period on one specific day. And here the attention weights are focusing all of its attention on this particular day, images from this one day, which is proved to be most useful for doing the particular classification. So I want to dig a little deeper into the false positives. So it's interesting to note that when we include contextual features from empty images in the camera's set, it actually improves the performance quite a bit. So these two lines here, the top line here is the false positive rate of the context RCNN, where we only include positive detections from when we're constructing the memory. So if we have very high scores, we're confident that there's actually a valid object there. And the line below it is if we instead include one detection or proposal from every single image in the context, it's able to use these and identify that these are negatives that shouldn't be detected. It's very interesting to see the false positives actually are lower for this single frame model, but that's actually a mistake if we dig into it a little bit more. So after you run context RCNN on this particular data set, and if you manually examine the top 100 highest scoring false positive detections, you'll see that they were actually misannotated by the raters who created the data. So it's actually highly effective at filtering out false positives. Now to the important question, how much memory do we need? From the experiments, the conclusion is that bigger is better. So the more temporal context, the higher the performance. That's the graph on the lower left here. It shows how big is our temporal window that we're considering in seconds, and what is the MAP performance on the detection task. You'll see if we go from 1 minute, we get 50. But if we go to 1 month worth of context, we get 55 MAP. It's also interesting to look at the patterns of attention, and they show some interesting periodicity. So the charts on the right are all given a central frame, and we've constructed a memory that spans the range of this camera. If it's trying to do detection in the particular central frame, how much attention or detection, how much attention does it distribute amongst the other images in the memory based on when they were taken? So you'll see that the bottom two here are the time difference in days and the time differential in weeks. And you'll notice that there's a periodic pattern here. And this corresponds to like day-night periodicity, because certain animals will have periodic behavior. You know, maybe they'll only come out at night or only during the day. So the model is attending to relevant annotations or relevant proposals within the memory. So to recap here, context is really useful for generalization in this object detection problem. Static cameras have a really high degree of intra-camera context. So it's really useful to incorporate the image from the context from the other images and video produced by the camera to do this animal identification problem. So attention is a very effective way to use this contextual information. And as far as these experiments have shown so far, the more context we incorporate, the better. So that's it for context RCNN. If you're interested in the code, it was just released in the TensorFlow object detection API, so you can check that out and try it out if you think it might be interesting for your problem. Okay, so just pausing here to check in. Context and attention can be used to get really dramatic improvements in a specialized video setup, this camera traps wildlife conservation use case. But they're very atypical. So these are static cameras stuck in one place for potentially a month-long horizon. The frames that they're producing in terms of video are sparse, and they produce a non-uniform frame rate. And the actors that we see in them are engaging in periodic behaviors that maybe not what we're expecting from TV shows or movies. So can the same ideas that worked so effectively in this camera trap setting work in a more traditional video setting? For example, movies from YouTube. So to address that, I'm going to start by introducing the Atomic Visual Actions dataset, which I've been maintaining and developing for the past few years. In AVA, the goal is to identify 80 basic human actions and localize them in time and space wherever they appear in the video. So you can see on the video right here, each video will contain multiple actors performing multiple actions. So it's like multi-label, multiple actor. And this is a particularly interesting problem because it means that scene level classification can't solve the problem. So we can't apply our favorite clip level classification or image level classification model and get away with coming up with the action. For example, if you had a scene that contains a birthday cake, you can't say that, oh, obviously the action is blowing out the birthday candles, because there could be multiple people in the scene. You know, someone would be blowing out the candles, another person might be taking a photo, someone might be, you know, bringing over the plates and forks and things like that. So you're going to need to do a much more nuanced parsing of the video scene to be able to identify each of these atomic actions. As I mentioned, the AVA label set contains 80 different actions. Some of these are based on the pose of an individual, the ones on the left. Some of them are based on how a person is interacting with another person. So talking to, watching, hugging, fighting. And then some of them are based on a person's interaction with an object. So picking up an object, touching an object, shoveling, taking a photo, things like that. So many of these classes are person-person or person-object interactions. So this is a data set where leveraging context is going to be key. Further, an interesting characteristic of AVA is the way we constructed it was to label 15-minute contiguous segments of movies. So we took these longer movies, took a 15-minute chunk, and then we labeled 1 frame per second densely throughout them. Every person that we got there got a box, and every action that we saw was annotated. So that is great from a, context point of view, but it's challenging in that it leads to an extremely long tail distribution of classes. Because we labeled it this way, we weren't able to say, oh, we need a few more handshaking examples, so we'll search image search or YouTube to get some of those. So we're at the mercy of like the real distribution of classes as they appear in videos. So it's a more realistic setting, but it also makes it more challenging because some of these classes have fewer examples. So AVA has been in the wild for about 3 years now, and there's been some significant progress on it. The action detection performance has gone up from 16% to 40% MAP over the last few years. I'm going to discuss some of the major milestones in that progression that got us to 40%. And I want to explain how these models have improved, many of them by leveraging context more efficiently. Okay, but first I'm going to do a brief digression. As an aside, so we recently made a major update to the AVA dataset. The AVA set has dense atomic labels, but we focused on longer movies, so it covers a relatively small set of unique movies. There's only about 400 movies that we annotated, but it contains 1.6 million labels. On the other end of the spectrum, you're probably familiar with the kinetics action classification dataset. That includes 700 different classes and at least 600 or 700 different clips for each class from different movies. So it covers a really wide diversity of scenes. The big difference here is while AVA provides dense labels for each box and multiple labels, kinetics only provides one classification label for each clip. So we thought, well, what if we took the strengths of these two and combined them? And that inspired us to create this new AVA kinetics data set. And we did this by augmenting the original AVA by annotating a whole bunch of clips from the kinetics data set with the AVA bounding boxes and atomic labels. So you can see here, these are clips from kinetics that we've annotated with bounding boxes and the corresponding labels. And you'll note that in addition to the AVA labels, we already also have the original labels that come with kinetics. So as a result, the dataset has 60% more annotations, but it covers about 500 times as many unique videos. And as I said, because the data now has both kinetics classes and AVA action detection labels, this opens the door to potentially co-training on multiple tasks on both the detection and classification tasks. So hint, shout out here. If you're looking for a data set for your next large-scale holistic video understanding project, I encourage you to check out AVA, which you can obtain from this URL. Okay, digression over, let's get back on track. Action detection. So action detection as it's posed in AVA, the problem is to detect 80 atomic actions in space and time on the keyframes from these videos. And the metric is the mean average precision at 0.5 IOU. So how to do this? For the really basic approach, the baseline, we go back to faster RCNN, which is also our baseline for object detection in images. Here we're going to have some slight modifications. So instead of running an image specific backbone network, we're going to swap in a 3D convolutional neural network model like i3D to pull in signal from adjacent frames and possibly leverage optical flow. But in essence, it's the same approach. We take a clip, we do some bounding boxes, we extract the proposal boxes, and we feed those into a classifier to identify the action. So how does it work? Faster RCNN uses some very limited context. So as I mentioned, it only uses features from the cropped bounding box around where the actor proposal was. So context is only focused on the particular person that we're trying to recognize, or whose actions we're trying to recognize. So we're not looking at any relationships between the actor and the scene and things like that. This model focuses on the single keyframe that we're looking at. Although because we're using a 3D CNN, it does pull in context from adjacent frames by sort of cutting out a, spatiotemporal rectangle from this feature. But that covers, maybe 2 seconds worth of time. So it's a very limited temporal context and restricted spatial context. The resulting performance of this model is 15.6 MAP, and we'll use that as our baseline. It's okay, but it's not great. So let's dig into that a bit more and see, where does this model, this faster RCNN model, fail on AVA? Here are 3 representative cases where it's going wrong. So on the left, we see 2 people together, one's reaching out to the other, and it's incorrectly saying that the person on the right is doing handshake or shaking hands. But it neglects the fact that it takes 2 people to shake hands and the other person isn't participating. So clearly this isn't shaking hands. In the middle, it thinks that this man in the car is smoking because his hand is near his face. But if you look in closely, you'll see that it's not a cigarette he's holding. So it's not smoking. And on the right, there's a man who's sitting at a table. It says that he's writing, and clearly he's looking down at something in front of him. But if you look at the context, you see that there's a dining table with plates. And if you're able to use that, you'd be able to tell that he was probably eating and not writing. So the first approach to address this problem on AVA is this actor-centric relation network that came out in ECCV 18. the idea here is to create essentially a contextual memory by extracting scene features from a rectangular grid of locations over the keyframe. So we'll see this global feature map. Essentially, we take the scene, we grid it up in space, and we're going to extract a feature representation for each of these. And then we're going to compare the features from each of the actor boxes to each of these locations. So here's another diagram of what it's doing. So we computed a feature map over the keyframe, and extend your keyframe through time with a 3D CNN. So we have a box proposal there. We're going to do ROI pooling to come up with a feature vector for this particular actor. Then we're going to collapse the spatial dimensions by average pooling. So we have one feature vector for the actor. And then we're going to tile it here and compare it or concatenate it with the features from all the different locations, spatial locations in the image. And then we're going to get a connected feature vector that has both the features of a particular location in the image and this actor that we're looking at. So that gets fed through a network which is effectively performing attention with a slightly different machinery. So it's sort of doing a memory style lookup to use context from these locations and see how they relate to this particular actor. So this Acorn model contextualizes each of the actor proposals with scene features based on a dense grid. So you can think of this as a sparse to dense contextualization model, because the actors were only using the proposals that the first stage of the model produced. And the context, we're looking at a dense, if low res grid of the image that we're going to compare it to. The relationships are first order. So we're looking at actors to scenes, and that's the comparison that we're doing. And the temporal window, just like in the previous example, focuses on the current keyframe with the caveat that we're using 3D CNN, so we get a little bit of extra temporal context. The result here is a pretty healthy 1.8 point increase in MAP, taking us up to 17.4. So you'll see that this is actually a pretty good way to leverage the context available in the same scene to boost action recognition performance. But this model is only focusing on the relationship between specific actors, which we detected sparsely, and scene locations. And we're just focusing on the central keyframe here. So the next model builds upon this by expanding its context and memory further, incorporating scene context from more distant time steps, and actually incorporating some higher order relationships between them. It does this at least implicitly. So the idea here is fairly similar. We're going to use a faster RCNN model to produce actor proposals. And then we have a feature map that we've run over this particular clip. And we're going to construct a grid of context locations in the clip that forms the basis of our memory. A slight difference here is that we're going to use it in space, but we're also going to have this grid expand in time to have 16 different nearby frames. And so we have these features from the actor proposal and these context locations, which effectively form our memory. And we're going to use pretty standard multi-headed dot product attention here, which is familiar from transformers, to relate the actor boxes to these context features. And there's actually an elaboration here. You'll see that there are 3 layers of transformers here. So we apply a transformer to contextualize the actor features, and then we apply it again, and then we apply it again. So this allows us to get higher order relationships. So as I said, focuses on actor to scene relationships, and it's sparse to dense, sparse actor proposals to dense scene grid locations. And it does this implicit higher order by stacking transformers here. So effectively, you could think of each feature representing an actor cross a scene location, and scene location. And the temporal window expands to 16 frames that we're going to consider for our memory. And the performance here is a pretty solid plus 7.6 MAP. And this gets us up to about 25 points MAP, which is pretty good, but still a ways to go. So we've used short-term context to identify other elements in the scene that are useful, but often short-term context isn't enough. So here's an example of a bunch of people sitting in a room. It's not really clear what they're doing if we just look at the 4-second clips. But if we expand our time horizon to a much longer stretch, then you can see that these people are actually sitting in a place where there are a bunch of musical instruments. Looks like a concert's going on. So these people here are probably listening to music, but we were only able to figure that out by looking beyond the 4-second window that could be fit in a typical 3-dimensional convolutional neural network. And this may be seem like a simple example, but it's actually pretty common in movies. You notice that a lot of the times the way things are directed, people will create establishing shots where they first take a wide angle view of the scene. So you'll see, oh, they're in a bar, or they're in a tennis court, or they're in a, I don't know, Baroque era music hall or something like that. And then the people will carry on in these zoomed in shots. So if you're able to figure out what the corresponding establishing shot is, maybe that will provide you the extra context that you're usually able to disambiguate these actions correctly. So how do we capture this? That's the goal of this long-term feature banks for detailed video understanding paper, which came out last year at CVPR. So here, they again have a proposal network that comes up with a set of potential actor locations in the short term. And it again uses a long-term memory that it's created by doing a first pass over the video and detecting all the people that it can, and then extracting those features and putting them into the feature bank. So in the first pass, we run over the video, we construct these feature vectors, we create a memory bank, and then we use that in our second pass to contextualize all the proposals that we get from the first pass. And again, they're going to use dot product attention, which we've seen before, in a thing that's very similar to the action transformer or context RCNN. So this one's a little bit different from the previous two. Here, we again start with actors, but the context that we're comparing it to are other actor boxes. So we're not just doing a dense grid over space. It's sort of a sparse comparison. And they again use higher order relations implicitly by stacking transformers using either 2 or 3 layers. And because the memory is sparse, we're not using every dense grid in the image. It allows you to expand the temporal window to be wider. So here they're able to incorporate 60 seconds of context around the particular image to use it in this long-term memory bank to improve their performance. So this leads to a 2.2 points increase in MAP, which is another really significant improvement. So yeah. Checking in, I guess, long-term feature banks. So it makes big improvements by expanding the contextual search space to 60 seconds. And another improvement is comparing sparse actor detections to sparse actor detections. But in this, it sort of lost the idea of the previous approaches, which allows relating a particular actor proposal to just scene context that may be objects in the scene that don't necessarily correspond to actor proposal boxes. So this leads us to the latest and greatest model, this actor context actor relation network, which just won the AVA challenge at the Activity Net workshop just a few days ago. So congratulations to the authors here. To me, this model is sort of a greatest hits approach, which uses the actor context features from this Acorn model, as well as the long-term memory from these long-term feature banks. And it adds explicit modeling of the higher order relationships, this actor-context-actor relationship, which is something that wasn't included here. So I guess the motivating example that they have here is the person highlighted in red is riding. And how do we know that he's riding in a car? Well, we can maybe see the steering wheel, which is some context to indicate that he's in a car. But how do we know whether he's driving? So we see that there's another person who's seated by the steering wheel. So if we say that the actor, there's one actor who's driving because he's related to the steering wheel, and then the second actor is riding because he's not the person in front of the steering wheel. So that's sort of the value of using higher order relations. So how do they make this work? In essence, if you boil this down, really oversimplify, you take the actor features and the context features from this acorn model. So we concatenate actor detectors, detection features to the densely sampled context features. And then we use that as our memory to which we relate further actor features. So you could think of this as our long-term feature banks had memories that were constructed by running a person detector on the video and extracting all of the features from the person box. So in actor context actor, the things that get stored in the memory is actor cross context. And yeah, so we're including actor, scene, actor features. So this is in the taxonomy that I've been developing here. Sparse, dense, sparse. And they're going to explicitly model higher order relationships. Their temporal window is going to be a little bit smaller here, but I mean, that seems reasonable if you throw in a dense contextualization with scene features. And the performance here is 5.4 points above the previous year's winner. It gets up to 39.6, so just about 40 here. And the reason why we did such a big jump in between was two differences. First, we released this Ava Kinetics data set and used that for the challenge this year. And just using the larger data set alone improves the performance by about +2 MAP. But also, this team used a much better backbone network from the slow fast network from one of our previous speakers, and that gave them a higher initial baseline to start from. So if you're interested in learning more about Ava and the ActivityNet challenge, I encourage you to go to the workshop website. You can find a video that includes an explanation from the winner of the Ava challenge and how they used this actor context actor model to get really significant performance improvements. Okay, so that's it for action detection. And just for completeness, I thought I've been developing this taxonomy for comparing different methods of contextualization used in the actor action recognition space. I thought I'd circle back to context RCNN from our animal detection and see how that relates. So context RCNN, if you remember, takes detections from the entire set of video and uses that or proposals to populate the memory. And then it relates them to, uses as keys in this memory, the proposals that we want to try and classify. So this is a sparse to sparse model, very similar to the long-term feature banks. And it's second order here in an interesting way, because it first takes the actor and it connects it to the short-term memory bank, which is sort of actor to actor. And then once it's contextualized with that, it compares it with the long-term actors here. So it's kind of actor to actor to actor. And what's distinctive about context RCNN is that the time window here is really enormous in comparison to the others. It includes data from months worth of images. Yeah, so wrapping up, conclusions here. When we're performing detection in video, whether it's objects or actions, leveraging context is really critical. For example, it allows us to identify these false positives and suppress them, which will be critical for any sort of video detection metrics. It allows us to resolve ambiguity about what's happening or what we're seeing in the scene. And it allows us to integrate cues from across space and time to improve our detection. And it's interesting to see that similar methods work for both multi-class object detection and action recognition in video. In particular, like a variants of transformer attention are highly effective here. And another observation is that integrating more context helps a lot. You'll see that with the context RCNN, expanding the time to even a month is useful. And in the development of models that worked on AVA, we started with a relatively simple comparison between actor and things in the same scene. And if we expand out to include context from 60 seconds away, it can help a lot. So how can we expand further? And what's the limit? I think in many cases, we're limited by GPU memory right now. But if that wasn't the limit, how much context would remain being useful for these particular tasks? And the ways that people populated the memories right now, and particularly with context RCNN and the long-term feature banks, they're created by pulling data from a long part away in the video. So it's not really something that we can, the mechanism for populating isn't something that's differentiable. So is there some way to create learnable mechanisms for how to select what to store in the memory and how to represent it? I think that could be a significant step forward. References. I'd also like to thank Sarah, Chen, Yuao, and Siyu for sharing their slides and let me using their figures in this talk. And thank you. If you have any questions or comments, feel free to reach out to me over email, or I guess follow up in the question period now.
Okay, thanks so much for your interesting presentation. It was really nice, and thank you for your effort. So it seems that I don't see any question on YouTube. Actually, I expected it because
okay,
most of
I
the
guess my
work
talk is perfectly clear. That's great.
The point is that it's midnight in this most of the so yeah, here in Germany it's somehow 3 a.m. So I need to not have much people here. So we wanted to ask you to have a visual group photo for the ending of the tutorial. And I'm also going to ask Christopher, I think he's still online, if he can join us. I'm not sure if he's still online or not.
Yeah. I'm still here. Yeah, I'm still here. Hi.
Still around? Hi.
Okay, so
nice talk.
Thank you.
Yeah, thank you for staying with us. And so,
wait for a second. So I still had like a question, David, for you. So like the initial part of the talk that you spoke about, where you spoke about like you're detecting animals right in the wild. So I know that Google AI for social good, you guys are still working on this, where you want to help coming up with the algorithms such that you could help rangers such that they could use AI to fight against poachers in order to save endangered species. So I recently know that like there's a professor Milind Tambe from Harvard, and he's also with Google AI, I guess, and he's also doing things like this. So they recently like saved like 60, 70 elephants from poachers. And
That's
they
amazing.
are saving a lot of animals in Africa. So I was wondering, like, when you're doing this thing, so what is the goal behind it? Why are you working on detecting animals?
Right. I can't take much credit for this. Sarah Beery, who's our intern, she's also a student at Caltech. She is deeply involved in this. I'm just someone who's spectating this conservation work, and I think it's amazing. Any questions about this, direct it please to Sarah Beery, who's the expert on this. She was recently on a trip in Kenya setting up camera traps and recording it, so she'll be able to provide details in a way that I can.
No, I was curious because now Google AI has started AI for social good in India. So they're doing all this. So I was just wondering, so if it actually is for sure it has something AI for social good. So just curious. Yeah.
Yeah, right. yeah, I mean, I think it's awesome work. I'm glad to hear that elements were saved from poachers. I think that's great. But I can't take too much credit for it.
Okay. Yeah.
We've got one question regarding your talk.
Yeah, great.
Anshul has asked, he first said great talk. And so apart from context, what else do you think is missing in current approaches? He says he or she says this is regarding AVA kinetics, the AVA data set and the kinetics.
Yeah. No one is really effectively using audio. We had a challenge 2 years ago. We had a separate track where we allowed people to use audio features in addition to video features. And some teams did use audio, but it didn't improve their performance at all. So it was like a coin flip, whether their performance went up or down when they used audio features. And then there's dialogue as well. Like you could probably deduce a lot by running ASR on it and doing, approaches similar to maybe what Chen or Carl were talking about to relate the text to the video. I think that could be very effective. And yeah, I also think that motion isn't necessarily being captured quite as effectively as it can. Most of the approaches that want to capture motion just use optical flow or 3D CNNs. And there's been some papers, I have one that shows that 3D CNNs trained on action recognition problems don't really do an effective job of capturing motion signals. So I think those are a number of different axes that could be explored. But I'm ready and willing to be surprised about what will make a big delta in the performance on AVA.
Yeah. Okay, and I think Christopher wanted to say something.
No, I was just laughing because I was saying the same thing in my talk about the audio performance, that there was this AVA challenge and no team could like squeeze something out from the audio. We have in this AV slow fast paper, we got some small improvement, 1 AP on AVA for using audio, but it was hard to get any improvement there. Like we did have to tune a lot on the hyperparameters. So I think it needs to be utilized in the right way, because if you have this localization, this extra localization effect in AVA that you need to do, and audio usually doesn't come with location. Usually you have maybe stereo, but usually you just have audio. So it's hard for the network probably to figure out where the audio corresponds to which person, to which box. So maybe more advanced approaches could help there, because I think some of the classes definitely could benefit from audio, like talking or listening and so on.
In that aspect, like this data set, LSMDC, large scale movie description data set from Max Planck. So they basically, like, we use that data set in order to do retrieval or like finding the same kind of scene. So you had like a scene and you had multiple shots in the same scene. So now the task is that given a shot, you want to retrieve all of the shots which have the same sequence using multimodal information, either like video, image, or like audio and also dialogue. So we found that, I also published a paper on this. So we found that audio, when you are doing retrieval, audio, if you have like a joint representation between images and audio, it turns out to be much more effective when it comes to retrieval. Dialogue is not necessarily always helpful, because it's not necessary that the dialogue that is being spoken about is actually what is being seen about. It's not necessarily relevant because it's perceptual and human-centric.
Right.
And Christopher, one question regarding, because we were started talking about audio and video training, because also there was another paper, I think last night, we had the same discussion. They were also working on multimodality. And one of the problems I've seen a lot in training this multimodal models, mostly the ones which are working on video and audio, is that they cannot easily train everything from scratch and end to end all together. Most of them are training each stream or each pathway or whatever we call it separately, and then they have some sort of late fusions, and by just somehow controlling the learning rate, I can say even they are not being trained end-to-end, and just the final classifier layers or the fusion layers are being trained. So what's your experience on this training?
I think that's a great point, that I'm struggling with that for the past years. I think like even early work on two-stream fusion, when you think about like there's optical flow network and there is an RGB network, it never really worked well for training it jointly. Usually you train one stream, you train the other stream, then you connect them, and then you train both together. And I think like, in this case, it's just flow and RGB. But even for flow and RGB, the differences are very large, because one, like RGB networks, they trained about 8 times faster than flow networks. If you train them alone, a flow network takes 8 times more iterations. At least back then, that was like in 2015. And I think that's the case for all modalities. Like in the AV slow fast, we saw it again, like audio trains much faster than RGB, and maybe text has its own like peculiarities for this. So I think like clever ways to treat these different learning dynamics could like have major impact in this direction to train, because I think conceptually it makes a lot of sense to train all these models end to end and jointly. The question is just how to make it work, and that's.
And another question, actually, it's from I have a master's student. She's working on explainable AI and mostly focused on this multimodal models. So the point here is that one of the hypotheses she's going to just investigate if it is happening or not, is that to check if these multimodal input data to the networks how are they affecting each other. For example, one of the hypotheses she has is that if we have a really discriminative input, for example, just go for optical flow and RGB. If we have an RGB input, so it's really discriminative. It helps in the classes in which we need the motions. So, you know, the motion is the discriminative signal there. And on the other hand, RGB is helping the other classes, which we mostly need the context or objects or whatever. So do training these together make the other stream lazy or not? Do you think that when we have a really discriminative signal in another stream, the other stream, for example, when we have the optical flow, then the RGB stream, the 3D kernels do not converge to where that they should capture the motion, you know, just they do nothing, just they mostly focus on the context or just the spatial information. Do you think it might be right, or do you have any suggestions?
Is the question directed to me or David?
It's to you and Ross, both of you. Okay. Based on your experiences you've had with multimodal networks, it's mostly 3D networks, and
I can just give my take. But I think, I think these different modalities, they have their different ways of also like just driving the loss lower. If you think like RGB, we know that neural networks are very good on remembering things. Now, if you think about a video, of course, there is an action happening and the network is tasked to discriminate this action from the others. But the models are very good at remembering things. And since we train with short clips from the same video, like we do multi-scale jitter in the spatial and also temporal domain, if the network sees a video from a clip from a video once, and then it sees again a different clip from the same video, it probably can already produce low loss without actually trying to discriminate the action, just looking at RGB values. So in this way, I think about optical flow is just a much stronger form of regularization. And if you train with raw optical flow information, in that case, the network has a much harder time of just trying to remember one clip and another clip from the same video. So that's my intuition for why this takes much longer to train. It's just a stronger regularization. And I think this also explains why audio is so fast in training. Sometimes audio is very correlated across the video. Like you crop you temporarily clip audio from a video, it's maybe some background music, the network will just easily get low training loss in the next iteration when you clip another temporal snippet from the same video. So I think it's related to this multi-clip training that we're doing, or this like the training clipping. Yeah.
Okay, so going back to the question about whether training together can make one modality lazy or something like that, because it's relying on the other. This sort of thing has come back, and this is like going back a while in the development of mixture of experts, right? Like in mixture of experts, you train them competitively, and each is sort of trying to solve the problem, and it gets weight or prior weight to be selected as the expert based on how well it's doing. So they're competing to sort of win here. I believe that people tried doing cooperative mixtures before, where they're allowed to cooperate on this, but then it doesn't learn nearly as effectively as when you actually pit them against each other, these different experts to try and explain the data.
Yeah, when they're learning against each other, yeah, it might help. But in just, for example, two streams that you have some late fusions, and then you just put signals coming from two streams to just some classification layers, then they are not actually competing, they are just helping each other.
Right. So is there some way to inject competition in there?
Yeah, then yeah, that's a solution, I think. Yes.
But I think like it's totally task specific, right? All these problems are task specific. If you would do classification, of course, you would like to suck certain information coming no matter where it comes from, as long as your task improves, right? So the problem is like SoundNatic is a perfect example. So they are trying to do the image and audio representation learning by showing the same type of information. And they end up learning like a super nice representation for audio, which correlates very well with the visual images. And so SoundNet provide that. And nowadays, like SoundNet is very well used for like extracting features for audio, like audio features and which very well correlates with the images also. So like in that direction, so that the goal was transfer learning more or less. So it did its job. But like, I think like it totally depends on what task we are trying to solve. Like mixture of experts also, if you would have it, you would need a certain objective, right? That you want to minimize. And what is that objective then?
Yeah. But I think the competition is the right way to do. Okay, so it's really late. It's somehow finish the tutorial. So let's have a sort of virtual group photo.
Yeah.
Here I'm going to just take a screenshot. So then 1, 2, 3, and yeah, there we go. Okay, so thanks so much for your attention and just attending our tutorial. You had really nice presentations, and yeah, I hope that we can see you in our next events. And yeah.
Yeah, thanks a lot for organizing. I found it really nice.
It was fun. Thanks for being here. And like, I think it's the last session, right, for CVPR? It's the last hour.
I think so, yeah.
Yeah, I think so.
Okay, so really running up the clock here.
Okay, cool.
Okay, then bye-bye, take care, and stay safe.
Bye.
Yes. Yes, Mohsen, we did
We are
it.
still streaming.
Huh?
We are still live on YouTube.
So maybe we can take a photo also, and then we can just stop it.
Yeah, okay, this is the organizer photo. And so 1, 2, 3. Okay, do you have anything to say? Just there are still 24 people watching us on YouTube, and
so I certainly think it's amazing that we finished this. So just one question, would you be able to, so it will be recorded and it won't be deleted, right, this video?
It's just let me end this stream on YouTube.
Okay. Yeah.
Moment.
Right.
Okay, bye everyone who are watching us on YouTube. Thanks for being with us. and hope to see you in our next events, and stay safe and stay well, actually, and bye-bye. Bye.